data. Maybe you run a wind tunnel experiment for a new airfoil, you measure the lift coefficient. Okay, that's labeled data. Unlabeled data would be more like the self-driving car example, where you just have a camera and things are happening and you don't have someone expertly labeling what's happening. Okay? And so if you have labeled data, if your data has tags telling you the features that you care about, then that's supervised learning. Makes sense. And there can be continuous or discrete labels. So for example, if I'm trying to build a classifier to tell pictures of dogs from pictures of cats, there are only two labels, dogs and cats, category 1 and category 2. That would be a discrete classification. And there's lots and lots of methods for discrete classification. Support vector machines, decision trees, neural networks, so on and so forth. If you have continuous data, like the lift coefficient example, then this would be a regression problem, okay? So all kinds of different regression models. The Cindy model I told you about yesterday is a regression model. Gaussian process models are regression models. And so lots and lots to choose from. And one thing I'm gonna point out a few times, I'll probably say this more than once, is that I want us to not get confused. Machine learning is not just neural networks. And don't let people tell you otherwise. There are going to be people, when you say you do machine learning or you have data, they want you to train a neural network, and that is the only worldview they have on machine learning. That's not what machine learning is. Bernd, yeah. I'm sorry? So what I want to do is I want to separate tasks from how we solve these tasks. None of these tasks are going to be build a neural network. A neural network is a tool that you can use to classify. It is a tool you can use to build regression models. There are many others, okay? So another categorization, if you have unlabeled data, so you do not know what data you're seeing, this is kind of the older, one of the older branches of machine learning is unsupervised learning, okay? So this is classically called data mining. You have a bunch of data, you're trying to find patterns and extract meaning from this data, but no one tells you what you're looking for. So this is like searching for a needle in a haystack. Again, you can have discrete or continuous. Discrete unsupervised learning is called clustering. You're trying to find groups of data that behave similarly to each other and differently between groups. Okay, and you can also have continuous unsupervised learning, which generally I'm going to call embeddings or dimensionality reduction. So POD, proper orthogonal decomposition, and principal components often fit into this kind of unsupervised world. Okay, and I'm only listing a very few of the methods here. For example, 10 years ago, people didn't use neural networks for classification much. They weren't the best. Amazon used decision trees, random forests, support vector machines. Those are the industry standard methods. Yes?
So now you say that discrete data is classification data, but you can also have discrete data that does not belong to basically classification.
If your labels are discrete, it's a classification task. I mean whether or not your labels are discrete or continuous.
Because if I have lived discrete time, it's not classification, right? Can you repeat it for everyone? So my question was, if I measure lift, for example, in a discrete time, I wouldn't classify that as classification problem, right?
So I don't mean discrete time or continuous time. I mean whether or not your labels are discrete. If I am only trying to classify between pictures of cats and pictures of dogs, there are two distinct labels. If I'm trying to classify or predict what the lift will be on an airfoil at an instant, that can be any range of a continuum of values for the lift coefficient. That is not a classification, that's a regression task. Let me point out also, nothing I say, so maybe I should just say in general, a third of what you hear in machine learning is gonna be bullshit at the very minimum. And so you get the fun job this morning of trying to figure out which third of this. If I get 80% of the way there, I'm pretty happy. I'm gonna oversimplify. That's my job today, is to oversimplify things for you, okay? Good. So the middle block I think is particularly interesting. This is where a lot of the most cutting edge research is happening in machine learning and there's actually a really interesting dichotomy between the successes of machine learning in industry, think Facebook, Google, Amazon, they have mountains of labeled training data. And it's billions of dollars, literally billions of dollars worth of labeled data that they got us to label for free, okay? It's much harder as scientists for us to collect that labeled data. That costs money, okay? And so a lot of work is going into what's called semi-supervised learning, where you have limited labels. You have an expert kind of semi-supervising your process. And it might be too expensive to label all of the data, so you label 1% of your data, okay? And there's a few different kind of big categories here. I'm classifying them based on whether or not you want to model your data or actively modify your data, whether or not you are a free agent that can change the world or whether you're purely a passive observer in the world. And so some of the really exciting ones are these generative models. The Mona Lisa picture I was showing earlier, that's a generative model where you basically have two kind of, in this case, neural networks or learning algorithms that are fighting with each other. One is trying to trick the other one. And so it's semi-supervised in the sense that the neural network itself is supervising another neural network, okay? Reinforcement learning is a really interesting class of optimization where you are actively trying to change how you interact with an environment. So you can think about the game of chess, okay? You are learning the rules, you're learning your opponent, and you're trying to design a control strategy to, in some sense, maximize some objective function, okay? And so you can also then take what your model of the system and make decisions that then change the system. Okay, that's a pretty interesting perspective, and that's something we should all be thinking about because we're not just going to be classifying images, we're trying to manipulate our system. And you can also do this with fully supervised learning with just generally optimizing and controlling your flows. Okay, good. Okay, so that was like about as shallow as you can get in terms of classifying machine learning algorithms. Again, I want to point out there are tasks, there are the quality and quantity of your data, and then there are methods of actually solving the optimization problem you're trying to write down. And those are three different things, okay? So when I talk to like executives about machine learning, I always give them this little spiel on what's easy, medium, and hard, because that's probably the hardest thing for people to figure out when they're just learning about machine learning. You see all of these examples, and it's not obvious what is possible and what's not possible. What would take one afternoon in TensorFlow and what would take 5 years with a concerted research team and millions of dollars, okay? So it's this nice XKCD. Maybe some of you have seen this. So telling whether the photo contains a bird, this was actually pretty old because it's now easy. This was hard a few years ago, labeling what's inside of an image. But you know, if your data has a geotag, it's pretty damn easy to tell where it came from. Okay, like it's all about what's in your data and how hard your optimization problem is. Okay, so image recognition, facial recognition, this is one of the original successes of machine learning. This is kind of why, honestly, it's why we're in this room today. It's why in the last 10 years so much attention has been given to this, is because finally machines can classify images about as well as humans can. Maybe not in every circumstance, maybe not as reliably or robustly, but it really is approaching human level performance. Facebook can tell if two people are the same or different about as well as you can. Okay, pretty remarkable. Interestingly, they don't do it by just taking two-dimensional images. That gets you about to below 95% classification accuracy, but humans are upwards of 97, 98% ability to tell who's the same and who's different. Any ideas how Facebook cleared that last 3%? Which is always the hardest. Sorry? Okay, so that's a great one, is they have some idea, some prior of who you would possibly be taking pictures of based on your network. That's definitely true. But they do this test on, so the same different test is for complete strangers. People you don't know, can you tell if they're the same person or a different person? So what would get Facebook up to that 97, 98% accuracy? And again, this was 5 years ago. So yeah, so they're already using color depth. So they do a few things right off the bat. The first thing they do is they will take your face, and there's pretty good algorithms to find corners of the eye, corners of the mouth, and corners of the nose. And what they'll do is they'll stretch your face onto a regular grid, because everyone has different geometry, and you can't compare people's faces if my eye is where your nose is. So you have to stretch everyone to a common grid. That's step one. They've been doing that for a decade. Step two, they actually estimate the geometry, the structure of your skeleton, the three-dimensional spatial geometry. That's how they cleared that last 3%. It's a little creepy. They're modeling your skull. So you see this picture here. You as a human have a pretty good idea that that is a three-dimensional nose that casts a shadow, and that's extra information that you can use to classify. Okay, so that's this additional understanding of the world that was very, very difficult to learn. But that's what got them to clear the gap. Okay, so image classification is a huge deal. This is just a tiny, tiny, tiny excerpt from the ImageNet database. So how many of you have heard of ImageNet? ImageNet was this, I forget how many, 10 million labeled images, hand-labeled images, something like 10,000 categories of images with thousands of examples for each, like 1,000 pictures of broccoli, labeled broccoli, 1,000 pictures of tractors, labeled tractor. Humans did this. This was one of the most impressive data sets collected. And that large data set was what allowed these new neural networks to be trained with such high accuracy. So again, machine learning does not start with a neural network. It starts with a mountain of quality data, usually. Okay? You can zoom in and see there's all kinds of stuff in this, and there's thousands of examples of everything. Okay? And so image classification 15 years ago was very difficult. Now it's almost trivial. We take it for granted. Okay, you can hold your phone up practically and classify an image. This one's really cool. This one actually fooled me. I thought I gave this talk a few times before I realized that these were actually misclassified. Like, these are generated images that were generated to trick a classifier. So these are pictures of my broccoli, my tractor, some purple flower. These are generated images from that same statistical distribution. I don't know if you can even tell the difference between some of these tractors if you're sitting in the back. Maybe you can tell that this broccoli looks really not edible. But it's kind of amazing that you can now generate images. That's pretty cool. Okay? But it's not perfect. This is the cutest blueberry muffin I've ever seen. I mean, it's not difficult for you to tell the difference, right? Everyone in this room, I see some people squinting, everyone in this room can tell the difference between a blueberry muffin and a Chihuahua, okay? My sister just got a fried chicken dog. He's adorable. But this actually still is challenging because machine learning algorithms build models based on the features that they have. They don't have legs and arms and a body to go carry them through the world and build experience. They do have ancestors now, but they don't have, generations of knowledge and modified neural networks like we do. We have an understanding of the world that goes much deeper than what our simple machine learning classification algorithms understand the world in. Now these algorithms are being deployed at scale. This is another thing you have to think about is just because you can demonstrate that something is possible, can you make it robust? Can you make it streaming, real-time, scalable? So now, with self-driving cars and surveillance, these image classifications are running concurrently in hundreds of thousands of platforms all across the world right now. Okay, so it's a little scary, but that's the world we live in. Is that this is now ubiquitous. This one's pretty cool. Image captioning was for a long time thought to be impossible for machine learning algorithms. And I think within the time I've been giving this talk, this became possible. So this is image captioning. You can give Google a picture of a scene, not just a piece of broccoli or a tractor, but a guy playing a guitar, and it will caption that image for you. Pretty neat. Of course, it's never perfect. This is probably my favorite one. This looks like where I'm from in West Texas, and you can see that there is no horse. But it's pretty remarkable, and the performance here is surprisingly high. Okay. Atari games. This one is really neat. You can use these reinforcement learning algorithms to build models of whatever virtual world they're given data. So this is the Google DeepMind reinforcement learning algorithm. They're given the pixels in classic Atari games. Okay, so just like when we were kids, we played games until, we couldn't see straight anymore. So does Google now. This is Blockout, and you can see this is literally it just learning how to play the game. It has some idea that what it wants to do is make these numbers big. Okay, so someone tells it what the objective is, and now it knows that it has some control input, and it's just gonna futz around until it can figure out what to do. Okay, after 2 hours of training, it's actually quite impressive. It's playing better than I could. It's a very simple game. This is its entire world. Its entire existence lives inside of this box. So that's a little sad. But something amazing is going to happen. So after 2 hours, it learned to play, but after 4 hours, something really, really special happens. It learns the trick that only, ooh, what happened? Yeah, you're gonna have to wait. This is the suspense. This isn't. So I've been making fun of machines for years, and I think they know. Good. That's okay. Let me skip to the actual part of the movie so you don't have to watch this again. Okay. Good. Okay, so it's playing like an expert, and after 4 hours, you're going to see the transition. So remember when you were a kid, and I don't know, this was before the internet when I was a kid, or before everyone had it. There was one kid in the neighborhood who could just destroy everyone. Okay? That's this Google DeepMind. Look what it's doing. It's going to find a weakness. It's going to dig a hole. Come on. There you go. And now it's all, the game plays itself. Did you see that? It's amazing. It learned something. I mean, this is a simple world where there's one trick and it learned it in 4 hours. It's pretty impressive. Now, there's actually a really great paper. I forget if it was a science paper or not, but you can download this original Atari deep learning Min paper. And there's a list of which Atari games it could totally destroy and which ones totally destroyed it. And it's really interesting to start thinking, does everyone remember Asteroids? Simplest game ever. You turn right, you turn left, you fire, and try to destroy asteroids. It could not play that to save its life. For some reason. I suspect it's because of rotational and translational invariance, which is really hard for machine learning. Okay, but it's not all about playing games. You can also teach robot machines how to do human tasks. So this is the catch in a cup task, right? You swing a ball on a string and you try to catch it in a cup. So when we were kids, we played this game. And this robot, you can see it's trying. It has to have a white background and a high-resolution camera trained on it at all times to learn anything. After 15 trials, after 25 trials, close. Probably can't untangle itself. But this is about how long it would take a kid. If you had a 10-year-old trying this, it wouldn't take them, it would take them between, 50 and 100 trials probably. There you go. It learned how to catch in a cup. Now this is its entire world. It's not doing anything else except for this. But, and this is interesting. It requires some knowledge of physics. I believe they probably baked in some rudimentary laws so that it could learn the physics it needed to. This one I think is pretty fun. This is a video my friend Ed Lazowska showed me. It's a DARPA video just showing how advanced our robots have become. I mean, robotics is really hard. We take for granted how seamlessly we walk. This wasn't that long ago. This is 2015. So Ed likes to joke that in the robot uprising, all you have to do is hide in the bathroom, but you don't have to lock the door. Yep. So it's still quite challenging. Yeah, Bernd.
You throw at them a gun, take from them. They see how the soldiers, they who they can shoot and who they cannot shoot. And they can fall and they can stand up again.
So this is actually a really interesting point. So my friend Nathan Kutz shows a version of this, which is the Boston Dynamics robot. Everyone's seen the Boston Dynamics Big Dog. Incredibly impressive four-legged robot. They also have their Terminator-looking robot, the two-legged, super big, terrifying robot. We're talking about how these robots are now, it's inevitable that they'll be used for, be weaponized. And so in general, everyone knows about the Boston Dynamics robots. Google bought Boston Dynamics, sold it right back. Why? I would argue, and this is a bit, speculative, it's because their generic machine learning didn't work at all for Boston Dynamics robots. It's a case study. Their self-driving cars, a lot of this is built on machine learning and deep neural networks. The Boston Dynamics robot is a physics-based, hand-tuned model with control. You cannot just give it a bunch of data and learn how to move a robot. It did not work. Okay, very interesting. So we do have a lot of robotic capabilities, but it is not using the same technology. Like Google sold it back, and you can make your own conclusions why they didn't find it profitable to keep Boston Dynamics. And it forces us to ask the question, what is the next thing that will be possible? Okay, so what was difficult 10 years ago is oftentimes not difficult now. And so it makes us wonder, what are the things that are truly unique to a human? Okay, and this is actually quite relevant for the young people in the audience. If there is something that everybody can do, I think at some point we will train robots to do something similar. Not always. That's a broad generalization. Like, for example, walking and catching and picking up an egg is easy for humans, and it's still very hard for robots. But eventually, I think they'll figure this out. But things that require real expertise, where it is not something that everyone can do, not everyone can write the next great American novel. I don't think machine learning will ever write the next great American novel. I would love to be wrong, but I don't think that will ever happen, okay? And so you have to think about what is unique and requires an understanding that you can only get through a unique lifetime, okay? Machine learning is never gonna be able to build those capabilities. It might be able to make a American novel. There's actually a really fun machine learning paper where they generated Harry Potter fan fiction. It's not too bad. It gets pretty bad. Starts off good. I mean, in Hagrid's hut, there were disdainful shrieks of his own furniture. You could totally imagine that happening in Harry Potter. Okay, it's really interesting. Some of the texture they get really well, but their sentences don't all make sense. Okay. There was a group of MIT that basically created a bullshit paper generator. Okay, and they got a bunch of papers accepted and made fools out of a lot of leading peer-reviewed journals. I was just seeing on Twitter a couple of days ago, someone generated a GAN for all successful ICML papers. They basically generated a network trained on all of the 1,000 successful papers that got accepted, and they can now generate their own papers, you know, pseudo figures and pseudo titles and things like that. So really, you know, like you can create things that are remarkably good at fooling someone who's not paying any attention at all. But there are some things that are fundamentally difficult, right? So we live in the world of uncertainty and chaos and dynamics, right? So yesterday we talked about how nonlinearity can give rise to this sensitive dependence on initial conditions. It is very, very difficult to predict where a hurricane is going to go. With models, with machine learning, from the data we have, there's only so much information, and the uncertainty you have amplifies in time. So there are fundamental limits to what information you can extract from your data. Okay. I like this one. I think this is really kind of a fun example. So for a while, Amazon would suggest what else you might want to put in your basket. Okay. And so if you bought whatever this person bought, it might suggest that you want ball bearings, magnesium, and gunpowder, or you know, in this case, I think this is the material for making thermite, aluminum and magnesium. Okay, so it thinks that whoever is purchasing whatever they're purchasing also wants to make thermite, and it would suggest you know, shrapnel bombs and thermite and all kinds of things. It was very embarrassing because, and this is scary because this means someone was actually like, this is not Amazon just making this up. Someone was actually putting these together in carts enough that this was in the database. Okay, so you know, it can go wrong, and I think this is interesting for us to think about what could go wrong. I mean, what could go wrong with, you know, a pervasive machine intelligence everywhere guiding and suggesting things for us. So for example, I saw a really interesting talk from a professor at Harvard who took legal case studies from the city of New York over decades and decided that they would train machine learning algorithms to basically robo-sentence people. Okay, so the judge gets a docket and they get some suggestion based on, okay, well, I've seen this case before, this age group, this crime, this record, you know, blah, blah, blah. What is the chance that they'll repeat offend? What's the chance that they'll become violent, and so on and so forth? And they get to decide on what sentence. Is it a fine? Is it, you know, do they set the bail? Do they have to go to jail? Things like that. And so you can build a machine learning algorithm to basically automate that and give a judge a packet that just shows them the distribution, shows you where this person is, and gives a suggestion about what they should do. We have to decide whether or not we are comfortable with that and what are the moral implications of that. What they found, what was interesting about the talk was this was basically an example of why you should never do this, because if you have a historically prejudiced system, you are going to bake in prejudice into all future decisions. Okay? And you have to be worried and careful and cautious about this. This is a new slide I just added this morning because this wasn't around the last time I gave this talk. This is, you know, pretty brand new. With these generative models, you can take a static image, in this case of the Mona Lisa, and you can transfer that over to, I mean, this one is just incredibly expressive. Right? You can now generate fake movies from like one image. That's impressive. So it's constantly a moving target. You know, every day there's 100 new papers in machine learning. Every year there is at least one major advance like this, something we didn't think was possible that is now possible. And so, you know, you have to be thinking about what's easy, what's medium, what's hard in machine learning when you're applying this. Okay, but there is a big difference, of course, between industry and their resources and their motivations and our resources and motivations as scientists. So for example, if Google wants to train a network for some task that it, you know, spends billions of dollars on, if it gets a 0.1% improvement in its performance, that translates to a tremendous amount of money saved. And so when they, I mean, a lot of these companies, when they show you their brand new natural language algorithm or their brand new image classification algorithm, what they don't tell you is that they had a wall of graphics processor units, maybe 10,000, maybe 100,000, And they trained the same model with slightly different parameters on every single one of them. And they cherry-picked the one that gave them 0.1% better performance, cross-validated. Because they don't give a shit about interpretability. They just want it to work a little bit better and make them more money. And that's not usually our goal as scientists. And we don't have those resources. We don't have that capability. It's a completely different optimization where we live. And I don't think that they often tell you kind of where they're sitting in their optimization landscape. They'll make their code open source. You have to train it on 100,000 GPUs for 2 months to reproduce their results. Okay. Okay, good. Any questions?
I have a question. Yes. So I think there is also something which is very important is to point out that there are some function evaluations whose output is not important. So if you if Amazon tells you that you have to buy termite, you don't care. I mean, you don't. I mean, even if it's not. Even if it's a wrong suggestion, the impact of this wrong evaluation is not important. But if you design an airplane and it falls, this function evaluation is important.
This is such an important point. I hope everyone heard this. There's a whole scale. There's many shades of gray about what decisions matter and how much they matter in machine learning, how dangerous a wrong decision is. If Facebook misclassifies a face, not a big deal, right? If Amazon tells you how to make thermite, slightly bigger deal. If an aircraft manufacturer makes an unsafe system and people fall out of the sky, that's a huge deal, right? It would rock the industry. I'm trying to be careful. So, I mean, it's a big deal. There are safety critical applications. So in kind of the next part on machine learning and fluids, that's something we absolutely have to be thinking about, is that 0.1% cannot be at the cost of all else. I will point out, we don't trust our models now. Like our models, there's no model for how an aircraft is going to fly except an aircraft flying. We have uncertainty in every step, and there's a whole field of uncertainty quantification about managing the known issues in our models. And so it's not inconceivable that that will be how we handle this in machine learning too. So I think we have to be asking ourselves, why now? You know, a lot of the younger people in this audience kind of, you grew up professionally in the world of modern machine learning. And so, you know, that's just where you come from. A lot of us didn't. A lot of us saw this massive sea change in how we interact with data and how we build models. Again, I'm going to oversimplify. This is, again, that ImageNet data set. So why now? It's partly because of this incredible, almost Herculean effort of this labeled training data. It's also because our computational hardware is incredibly fast and powerful. So I don't know, how many of you track Moore's Law and where we are, but in my lifetime, I've seen the speed of individual cores basically level off because it's hard to make smaller dies. And so now we have thousands of cores, okay? And that has allowed us to, and these are not great for, tree logic, but it's really, really good for linear algebra. And so we have better computational hardware to train these algorithms, which means we can fit larger and more complex models into memory and train millions and billions of degrees of freedom with this large amount of data. It's also, there's been a huge investment from industry, billions and billions of dollars of investment from industry into open source software and kind of these community efforts. So there's a lot of things at play that are making this kind of as successful as it is. Okay, it's not just neural networks, it's not just GPUs or open source or ImageNet, but it's really this kind of combination of all of them. It did start in 2012 when a group used the ImageNet database and a modern deep learning architecture to destroy previous classification results. And then it was so profoundly better that that's where everyone started pouring in the resources. And in every major task, it's just been getting knocked out one by one by these deep learning architectures when you have enough labeled data. Okay, good. So I'm about halfway through. I'm going to talk a little bit just about neural networks in general. How many of you feel pretty comfortable with neural networks? How many don't know that much about them? Okay, good. I don't either, but I'll tell you what I do know. So neural networks, I do like to say that machine learning is not just neural networks. They are not synonymous. There is a world of machine learning out there. I use lots and lots of techniques, and when it's right to use neural networks, I use neural networks. When it's not, we don't. I heard a respected figure in our field recently say that this is the 21st century and machine learning is neural networks. I don't agree with that, but I will say that there is some truth in that. Like, that is where a lot of the opportunity is if you have massive, massive, massive data sets. Yeah.
At the moment you are using neural networks, you are looking at an epsilon cubed error between images, for instance. Suppose Google looks here at the faces and tries to recognize the people. If I would be a mass killer, I would say, okay, person, 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 person. So I would not make the distinction who is who. And so if we are in fluid mechanics, we are typically working on much coarse distinctions. So we are not interested in a male or female vortex and where it came from and so on. So we are willing to tolerate much larger differences. And if you and for these type of say causal classification, other tools are much simpler tools are much more efficient. And I would say for many applications which we have in our community, k-nearest network, nearest neighbors, will probably beat neural networks.
So, I mean, I would not disagree. There are so many other techniques, and many of them are better suited to problems than neural networks, depending on the problem. Honestly, for those of you who have programmed in TensorFlow, a lot of the reason people use neural networks is because it is so easy to use them. They have made it trivial to build a network and train a network and cross-validate it. You don't have to really think about anything going on under the hood. It's easier to build a neural network model than Tickler can project. A lot easier. Yeah. A little bit. I'll present a little bit of a kind of a dichotomy of networks. But why are neural networks so popular? So I'm not going to just trash neural networks. They're super useful. They're incredibly impressive. And the major advances in the last 10 years have mainly been in neural networks, at least at scale, at industrial scale. Facebook, Amazon, Google scale, the advances have been in these deep neural networks. They are extremely expressive. You can represent, there's something called the universal approximation theorem, okay, from the 80s. You can represent any function, no matter how nasty, with a sufficiently deep neural network. And really, that's how I use them. Whenever I have a problem, and I think to myself, oh, this is a really nasty function I need to approximate. Think Koopman eigenfunctions. Remember yesterday? Those Koopman eigenfunctions were a mess. Once you have a Koopman eigenfunction, your world is simpler forever after. But finding that eigenfunction might be incredibly challenging and complex. It might be horrible to write that function down. That's perfect for a neural network. It's a really nasty function, and you like the expressive power of neural networks to represent that function. So anytime you have a terribly nasty function, and you have a lot of data, that's actually a great time to be thinking about neural networks. Okay? And again, it's this arbitrary function approximation theorem. So these are quite old. People have been developing neural networks for over 50 years. The perceptron is one of the earliest ones. I have a picture of a brain here. They're not called neural networks for no reason. Neuroscientists started, understanding how animal brains worked, and they realized that it was this loose confederation of individual processing units that could talk to each other in a network. Okay? And they started trying to understand how this information processing works. And there's still a vibrant community that's kind of at the interface of neuroscience and machine learning. So the NeurIPS conference, this was created by machine learning and neuroscience professors, computational neuroscientists and machine learning researchers. So we're still trying to understand, you can think of it in two ways. We're trying to understand how animal brains work by simulating them in silicon. And we're trying to improve our algorithms by what we learn from biological processing systems. Okay. Now, if you think about what's different between a human, or an animal, even like my dog, which is a dynamical system, and an artificial neural network, what are some key differences? This is why I'm still fundamentally a skeptic. What's different between your neural network and an artificial neural network? So size is a big one. You can plot this log scale, and we're probably getting close to like, a bug. Our computers are not near the size scale of a human neural network. So size is definitely one of them, but I would say size is not, we will someday have a neural network that is as large as a human brain. And I don't think it'll have the capability.
So we are conscious, and as such, we can have a fantasy, we can ask questions. So what the neural networks can only do, they can only make an optimization or solve a regression problem in a well-defined setting. And we can have a fantasy and can choose our focus of our consciousness.
So I think an imagination is a huge part of it. Now, there are actually some very compelling examples of deep neural networks that have things that look like dreams and imaginations, right? Google's Deep Dream are these just wild fantasies that this network, if you just put in random noise into these generative networks, they create dreams. So, but they're not motivated the same way we are. I think motivation is a big part of it. That's your objective function. They're purely motivated by the objective that a human specifies. What are you motivated by? Depends. Like, I want coffee. I want to get through this so I can tell you the next thing. I mean, we're motivated by so many things and so many scales, it's hard to even compare. We also have bodies. I think this is going to be the fundamental distinction forever. It's going to be materials. Like, I can feel with my fingers. Do you know how hard that's going to be to make something that's even close to as good as a human hand? Let alone legs and a heart that lasts for decades. And I mean, the whole system so that you can carry yourself through the world and get this richness of experience, that's going to be separating us for much longer than the gap between just the raw size of our neural network. Okay. Okay, good, ImageNet 2012. So these neural networks are based on neurons. Neurons are individual processing units. This is basically just a nonlinear function or a linear function. Okay, it's just a function, some little block function. It takes an input U and it gives an output Y. You have lots of choices for what this function can be. You can have a sigmoid. This is basically what biological neurons do when you make a decision to spike. There is some input, and based on some probability, there's a sigmoidal response curve of whether you fire or not. Increasingly today, we use these ReLUs, these rectified linear units. These are very useful for kind of building these piecewise functions up in deep architectures. So ReLUs are super popular, but there's a whole zoo of these functions. Okay, and what you do in neural networks is you stitch these together. Okay, so you can take little functions and you can build big functions. You can take one, set of sigmoids and ReLUs, and you can build these very, very complicated cost landscapes for optimization. Okay, you can build layers, so you have these intermediate layers. You can have multiple layers, and the real advance in recent years, in this last decade, is that now you can have very, very large, very, very deep architectures that all fit into your graphics processor unit memory. So you can train all of these parameters with the massive amounts of data you have, okay? So the deep architectures are pretty interesting. And actually, we were talking about this last night over dinner. The advances in neural networks have been pretty profound. There are, this is a zoo of neural networks. There's something called the Asimov Institute, and they have this catalog of all of these different network topologies that people are using, and it grows rapidly, all of these designs. But I think we take for granted how important the advances in the algorithms are. So Peter yesterday was talking about automatic differentiation. Automatic differentiation is, the unsung hero of a lot of these training algorithms. Backpropagation. There are these fundamental algorithms that have made it possible to train these networks that is just as important as the network architecture. And now it's pretty much abstracted for us. You don't really have to think about that most of the time when you're using TensorFlow. It just does it for you. Okay, the Atom optimizer is really, really good at optimizing. Okay, so I'm going to walk you through a couple of different network architectures. This is, again, not at all complete. So convolutional neural networks are really good for images. Okay. A convolutional neural network, basically what it does is it has a little, so let's say you have an image, this is a smiley face, and what it does is it takes a little patch of a filter and it slides it across the image, just like you would do in a convolution, and it creates another layer, and then you might have another convolution that slides across that and creates another layer, and so on and so forth. And this is nice for extracting multi-scale patterns that might be in different places in the image. Okay, that's actually one of the major advances in neural networks for image processing, is being able to tell who's in a picture even if they're in a different part of the picture. That sounds really trivial to us. It was really hard for computers until convolutional neural networks. So invariance is translational symmetry. If I see a picture of a truck, it doesn't matter if it's here or there, it's a truck. We as humans fundamentally deeply understand three-dimensional reality. You understand the symmetry of camera perspective. If I get a little closer, you don't even take for granted that all of my pixels are a little bit bigger now. Or if I go a little farther back, or if I rotate a little, like, you are completely factoring that out constantly. We've trained computers to factor out translational symmetry and scale invariance. Rotations are still quite challenging. Okay, there's still a lot of symmetries. It's very hard to train machine learning algorithms to respect and understand symmetries in your data. That's one of the open problems. Okay, convolutional neural networks are good for images. Recurrent neural networks are good for audio and temporal. I realize now that this is a slide that I use when I have my light board and I can actually draw. This is when you can connect back. I forgot my arrow, so this is a really lame recurrent neural network, but if you can connect back to previous levels and feed information back, you can create these memory loops. Okay, and that's really good for things like speech processing, dynamical systems modeling. So you have these LSTM, long short-term memory networks, for feeding back information. The ResNet, these deep residual networks, have jump connections that allow you to carry information over longer periods. One of my favorite networks for fluids for this community are autoencoders, because it fits in so naturally to what we already do on a daily basis with POD and DMD. Okay, so I'm taking for granted that basically all of us already do POD and DMD and feel very comfortable with taking high dimensional data, recognizing that there are patterns in that data, and then extracting kind of a low dimensional representation. In the 80s, it was shown that the principal component analysis, or the POD, could be written as a simple linear neural network. Okay, if I have a big neural network with a big input dimension and a big output dimension, and this is my image of a flow field, and I'm trying to reconstruct that image of a flow field, but I'm choking it down to maybe 3 nodes in the middle, that's a 3-state, that will pull out your 3 most significant POD modes. Okay, and what's nice about this is that you can relax those conditions. Now you can allow your network to have nonlinear activation functions and a deep architecture. And so instead of pulling out a linear POD subspace, you can pull out a nonlinear manifold that your data lives on. Okay, so remember in the fluid flow past a cylinder example, your flow lives on this parabolic manifold. POD would pull out the 3 coordinates that manifold lives in. This deep autoencoder would pull out the 2-dimensional parameterization of the manifold itself. Okay, and this has been used in fluids since 2002. I'll talk more about this. Milano and Koumoutsakis, I think, were the first to use this deep autoencoder architecture for fluids, but now it's becoming pretty pervasive. It's a generalization of POD. Okay. So I like to give a caution. Maybe I've already given enough caution. Neural networks are very prone to overfitting, especially when we build neural networks based on our puny data sets. Google has massive data sets and massive resources to prevent overfitting, but we have to worry about that. Generalization is a big problem. Neural networks are, if you take one thing away from what I'm telling you about neural networks, they are really good for approximating nasty functions and interpolating between data you've already seen. They are the best interpolatory algorithms out there today. They're no good for extrapolation. If I train my data on my network on data collected here, it will not be valid out here. Because whatever the shape of the function is here, the network does not make any assumptions that would generalize out here. Okay? As physicists, we care about generalizable models. F equals ma is a great example. Okay? It's a big problem with neural networks, a huge problem. Interpretable and explainable. If your neural network has 10 billion parameters, how are you going to interpret it? How are you going to make sense of what decisions it's telling you? Okay. And incorporating physics is one of the really, really active areas of research. So in the US alone, I was writing down some numbers. I think in the last 2 or 3 years, there's probably been about $200 million of grant funding just on incorporating physics into machine learning. I know that there's similar efforts in Europe for this. It's a very, very challenging, so I think of this as the second wave of machine learning. The first wave were these kind of low-hanging fruit image classification static data set problems. The next wave is going to be physics problems and engineering principles. Okay, and it's not exactly a caution, it's also kind of an opportunity, right? There's a lot to be done still, it's not a solved field. Okay, cross-validation. Remember yesterday we had our accuracy versus model complexity? I just want to point out you have to cross-validate your models. You cannot train a model on training data and believe anything you get. Does everyone know that in your heart? Does anyone have any doubts that you shouldn't be cross-validating? If I shake you awake at 2 in the morning, you should know how to cross-validate your models, okay? Hold out some of your data for testing. And in the next lecture, I'm going to give you some examples of where cross-validation is not as easy as it sounds. So in the ImageNet example, cross-validation makes sense. You just hold back, 10% of your images and you use those to test if your algorithm was any good. That's fundamentally relying on the idea that your task is an interpolation task. That in those, whatever, 10 million images, I've seen basically everything I care about. It's not good for extrapolation. So I'm going to give you some examples in the next lecture about training and testing and cross-validating on interpolation problems versus extrapolation problems. Okay, there's a difference, and it's a subtle difference. So you've already seen this. You have to cross-validate because then your models might well be overfit. Okay, good. Okay, good. Does anyone have any questions? I've just got a few more vignettes I'll go through. Yeah? Overfit, yeah, sorry. Good. What do I mean by overfit? By overfit, I mean, so there's this great quote that, with 3 parameters, I can make an elephant. With 4 parameters, I can make it dance. Forget who said that. Anyone know?
There was Gauss who said with 7 parameters I can make an elephant walk on the rope, and with 11 parameters I can make him dance on the rope.
Yeah. So the idea is with these highly expressive functions, a deep neural network might have millions or billions of free parameters that you get to tune. We know that we can over-parameterize our model to fit. So for example, if I gave you, I'm going to do an example right now. I'm going to give you data points. My finger is going to be the data points, and you're going to tell me what function I'm approximating. Okay, I'm going to give you data, 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 data. So I've heard parabola, sine, those are logical. Okay, maybe a cubic. But there might have been some noise. I might have, had some beers. So if you allow your machine learning model to fit that with a polynomial, and you're just trying to minimize error, it will use a 10th order polynomial, and it will go through exactly every single one of those points. And it'll be a garbage model unless you had some extra points that you held out to validate. Okay, that's what I mean by overfitting. Okay, good. Neural networks are very commonly used now in dynamical systems. This is one of the areas of active research in incorporating physics. I think Bernd's going to talk about machine learning for reduced order modeling, which is definitely in this vein. I'm going to talk about this for fluids later, but I'll just give you kind of an idea of what I mean here. So you can also build a network that, given some state vector x, will predict x dot. You can train a network to do that. So you can build some representation of your dynamics f. Again, it will only be valid as an interpolation where you've already seen data. You can then use that to iterate using something like a forward Euler or a Runge-Kutta scheme. This is pretty common. You can also learn the time step flow map itself. You can learn an integrator. This is super cool. One of my former PhD students with Nathan Kutz, Sam Rudy, learned how to incorporate Runge-Kutta time stepping into this. That was pretty neat. You know, on the training data, it does really well. You can, you know, this is for the Lorentz system. You can integrate this forward and you get these trajectories. Some test trajectories, though, fail, and they go to these limit cycles or fixed points. So you have to be pretty careful about training with a richness of data so that you've seen everything that you will see in the future. Okay, so you know, on a tractor, sometimes it works, but sometimes it doesn't work that well in testing. There's a pretty nice kind of zoo of machine learning algorithms for modeling dynamical systems. These long short-term memory algorithms, these recurrent neural networks that have been used for a long time in recognizing speech. So like your Google Translator is using something like an LSTM or an RNN. You can use those for modeling dynamical systems. So Pantelis Vlachis at ETH built a nice network to do that. These reservoir computing networks are pretty cool. These are like really shallow networks where you basically have just this big reservoir of nonlinear functions and you get to train how to connect them up. That's been pretty interesting. And then also people are doing a lot with autoencoders and building models of the dynamics in these latent variables. That's just a couple of examples. This is that paper using reservoir computing. I think this is pretty cool. So they're running this on, I believe, the Kuramoto-Sivashinsky equation, which is a chaotic spatial PDE. So this is space, and this is evolving in time, and it has these kind of chaotic fingering. And this is the true high-fidelity numerical model. This is their reservoir model. So it's actually, it gets the right qualitative behavior, and it agrees quantitatively for some period. And so this error takes a long time to grow. It's pretty cool. If you change the color bars a little bit, you can actually see it already has error early on. So you got to be careful about how you color your plots. But it's a pretty impressive algorithm. Okay, good. Does anyone have any questions at this point? Yeah, in the back.
Okay. I have a very basic question about, like back to the beginning of the lecture about definitions and where does the term deep learning fit into the classification? It's just related to deep neural networks or can be extended to other methods or algorithms?
So deep learning refers to machine learning using neural networks that have many, many hidden layers that are deep in the number of layers that they have. And that's a modern trend that has been enabled by advanced GPUs, better training algorithms, and enough data to fit those many millions of parameters. But it's a deep neural network, many layered neural network. And you know, everyone's having competitions to see who has the deepest neural network, and it's a moving target. Yep. Good question. Any other questions?
As a follow-up to his question, how would you classify deep neural networks as supervised, unsupervised, semi-supervised, or they're applicable to all class of problems?
Yeah, so this is something that we have heated debates about sometimes. It's a little hard to pigeonhole it too much. A lot of deep learning applications are supervised learning applications. Image classification is a supervised learning application. A lot of deep learning applications are semi-supervised. So these deep generative networks are semi-supervised. Google DeepMind is deep reinforcement learning. So that's, again, semi-supervised. The deep autoencoder, the one that does the nonlinear principal components, that's not exactly supervised. You're using the data itself as the label. So it's hard to even know what that is. I would call that an unsupervised learning. So it's a little hard to say. Any other, yeah.
Have you heard of neural ODEs?
Neural ODEs, yeah.
Have you compared how they would work against your Cindy model?
Yeah, I mean, so people are definitely making those comparisons. I think neural ODEs is really exciting. You know, it's interesting if you, so there's no method that's going to be kind of a panacea or a silver bullet for all problems. So there's some problems where you're going to want the arbitrary function approximation of a neural network because the vector field is that messy. There's other problems where you're not going to want that. You're going to want it to be faster. If you want to do model predictive control, you're going to trade some of that accuracy for computational flexibility and efficiency. But there is an interesting point. Some of these kind of deep residual networks that are now being shown to be quite good for ODE simulations, oftentimes, if you take a task that you think is going to be trivial and you try to train a neural network, 6 months later, you realize that it's not as trivial as you thought. Okay, that's been every paper we've written on neural networks. There was 6 months where we could not figure out why the thing that was obviously should work didn't work at all. Okay, and we tried this. We tried to build a neural network that would essentially learn the identity map. We were trying to build a deep autoencoder to learn the Fourier transform to solve the heat equation. Okay, that would be like we were trying to learn the Fourier transform, and then we were trying to learn the Cole-Hopf transform to transform Berger's equation into heat equation. And at some point, we realized that there was, a part of that where we needed an identity or something similar to the identity, and it was actually really, really nasty to build out of these ReLU units. And the residual network is nice because all of these jump connections are basically carrying the identity with you. And if you think about your favorite ODE integrator, like think about, I don't know, RK4 or on Euler, it's built on, actually, I mean, I just had this up, right? Your integrator is basically an identity plus an epsilon times your vector field. So that's why these residual networks are so good, because they're carrying the state forward and you don't have to like build a network to learn how to carry the state forward. So I think that's why they just have the same structure as integrators. So that's very, very natural. Okay, good. I'm going to talk about 2 more things and then we're going to have coffee, okay? So there is a debate in machine learning, especially for physics, about whether or not you want end-to-end solutions or whether or not you want to focus your machine learning on very specific subtasks and then piece them together like an engineer would as a machine, okay? And so I'm going to tell you about work in what we call discrepancy modeling, and this is work with Nathan Kutz and also Cardi here. You can ask him. It's this idea that instead of trying to learn everything from scratch with a neural network or whatever machine learning algorithm you like, we often have a lot of partial knowledge about the system. So for example, when I'm building a controller for a robot, I know that that robot has joints, and I know that there's basic conservation laws and symmetries and things like that. That is extremely hard for machine learning to learn symmetries and constraints. It's very hard to teach an algorithm that energy is conserved. Okay, I haven't seen it happen. But if you know that, you can bake that in and save it a lot of trouble. Okay? Similarly, there are things that are hard for us to model physically, like wind resistance and nonlinear friction, those are perfect for these arbitrary function approximators. Okay, so you start with this imperfect model of the world. Instead of trying to model everything from data, just try to model the discrepancy between your observations and your model. Okay, so here's a nice example. This is the one I used to demonstrate this. This is Cardy's work, and he's here, so you can ask him about this. But we had a pretty good model for our double pendulum experiment, right? This is textbook Euler-Lagrange. But, you know, we measured this thing as accurately as we could, but we have some uncertainty in our measurements. There's nonlinear friction and bearing chatter. It's not perfectly described by that Euler-Lagrange model. And when you use that idealized model for a control law, it doesn't quite work for the swing-up stabilization. Whereas if you can learn some of the discrepancy between your observed data and your ideal model, you get kind of the best of both worlds, and you get to focus your learning only on the part that you don't already have. Okay, so we think this is nice for physical modeling. You can also use this for like digital twins and robotics for high precision manufacturing. So this is work we're doing with Boeing that I think is pretty neat. Okay, so the last thing I'm going to tell you about, and this is kind of a natural segue into the lecture on machine learning for fluid mechanics. Oh no, what happened? There you go. In physical systems, in systems where we're going to put this technology on aircraft and in cars, we need our models to be interpretable and generalizable. Now, I struggled with this. Should I try to define interpretable and generalizable? In fact, I am almost certainly using this in not the way that a machine learning or statistician expert would use this, and I am not going to apologize for that, because these words mean something to us, and we had these words first. You know when a model is interpretable and generalizable when you see it. So the example I like to give is Newton's law, F equals ma. So F equals ma is the quintessential model that is interpretable and generalizable. It only has a few terms, and you can learn it from an apple falling on Earth, and you can use it to put people on the moon. Okay, that is generalization at work. Okay, you didn't have to you didn't have to collect data from failed missions to use F equals ma to land people on the moon. Okay, so a great quote from Einstein: everything should be made as simple as possible, but not simpler. That, again, that goes to our principle of parsimony that we talked about the other day. You fundamentally want the simplest model, not just the one that has the 0.1% better error. Right? That's not for us. Oftentimes, we're going to promote these models with sparse models, low-dimensional models, and robust statistics. So that matters a lot for fluid mechanics. And what I'm going to do next is I'm going to talk a little bit just about trying to understand modern machine learning advances in the context of historical scientific discovery. Okay, I think this is really fascinating. I know a lot of us are interested in the history of science, and kind of, you know, it's very exciting, all of these great discoveries, triumphs of humankind. And we can learn a lot by just asking ourselves the question, what would happen if we gave the data that Kepler had to a machine learning algorithm? Things like that. Okay, so we're going to work through some thought experiments of classical discovery contrasted with modern data-intensive discovery. Okay, and there's going to be three pieces. So we're going to start with the Ptolemaic system. So Ptolemy was a Roman astronomer who created this extremely accurate model of planetary motion and the motion of the stars. So if you think about it, right, our planets are named after gods, right? Because they're the only objects in the sky that had free agency. Everything else has a very prescribed path across the night sky, but the planets are strange. They have agency. They do whatever the hell they feel like. Sometimes they turn around. They didn't decide they don't want to go that way. And so understanding where planets came from and are going and what they are, I mean, this has fascinated people forever. Okay. Actually, I was talking about this with my kids. If you think about astrology, so astrology is a great example of overfitting. seriously, 10,000 years ago, astrology was extremely useful. When do you plant your crops? You use the moon, you use the stars, right? That's astrology. Had a very real use in the development of human civilization. And then we just kept fitting it and fitting it and fitting it. And now people have kids at particular times of the year because that's what the stars tell you should do. Okay, so that's kind of overfitting. The Ptolemaic system, this is a beautiful armillary sphere in Florence. I would recommend everyone check this out. This is Sartucci's armillary sphere. It's absolutely beautiful. And it has this, 7-layer model of existence of, the solar system and the planets. And the idea here is that with the Ptolemaic system, you could model the motion of the planets as circles on circles. So you would take a big circle, and then you'd add a little circle, and then you'd add a littler circle, and if you added those all up, you would get the motion of the planets. Okay, does that sound familiar? Sounds like a Fourier transform. Okay, this is basically a crude Fourier transform, extremely accurate. There's a reason it took 1,500 years to knock down the Ptolemaic system. It's because it was actually more accurate than Kepler's model. Kepler could not make a model that was more accurate than the circles on circles until like kind of the very end of his trials with this. Anyone remember where this is from? Just pop quiz for... No Jim Henson fans? This is from the Dark Crystal. This is a model of their universe. So this is a great video from 3 Blue, 1 Brown. I don't know if any of you follow this, but I would strongly recommend it. This is kind of illustrating this Fourier series of circles on circles on circles. This is showing you that you can just take your astronomical data and fit it using circles. But this was not a physics model. This was a descriptive model of the data. Okay, this is what machine learning would do. They would give you the Ptolemaic system. But it would not tell you that fundamentally there are objects called ellipses, and it would certainly not tell you that F equals ma is the reason we have ellipses. This one's great. Fourier transforming Fourier. And you can see how many circles on circles and circles. I mean, if you have enough, you can fit this, right? Okay, so I think that's pretty interesting. There's another parallel that has been we've been thinking about recently. This is work with Brian De Silva and Nathan Kutz. Is this view of Aristotle versus Galileo? Okay, so we've all heard the story of Galileo dropping, 2 spheres from the Tower of Pisa, one made of, I don't know, something heavy and one made of something light, and then falling at the same rate and touching the ground at the same time. Right? This is probably a fiction. That's not how he discovered this, probably. So we started thinking about, actually, the way that he probably discovered this, if you read about this, he was sitting in church, and he was bored to tears, and he was looking at this clock swinging, just trying to figure out how many more swings of the clock he'd be in here, and he realized that there was kind of this universal relationship between frequency and length, and it didn't matter what the mass was, right? It's a relationship between the length and this universal constant of gravity. And so he actually developed these extremely intricate ramps in still rooms where he had these little bells, so you could actually measure distance by time. Really interesting experiment. So this is where he actually distilled the universal gravitational kind of idea. But we did this thought experiment, and we actually started doing real experiments with collaborators where we have data of different balls being dropped off of a 5-story parking garage. We have like literally position measurements in time of 13 balls of different density being dropped. And we're not trying to be really, really careful here, and some of them are basketballs, some of them are bowling balls, some of them are baseballs. We took that and we ran it through some machine learning algorithms. And what we find is that we don't at all get Galileo's model of a universal gravitational constant. We find that the rate of fall is proportional to the mass. Because that is what's in the data. that is the Aristotelian model. And again, 1,000+ years to turn this over because the data doesn't support Galileo's model. It takes a conceptual leap. You have to somehow fundamentally step away from your data and make a conceptual leap to get to Galileo. Okay, the data, if I throw a ball, obviously if I throw a beach ball, it's not going to go as far because it's big and light, because of wind resistance, because of extra physics, extra discrepancies that are really, really hard to model. Okay, so this is just a point you have to be careful when you're doing these models. The third, oh yeah. So I could build an extremely accurate model of how balls move through the air if I had enough data. But if I used a neural network, I would never come up with a constant gravity. That's maybe our point, is that like the simple answer, like machine learning is not typically built to promote parsimonious solutions, the simple solutions. Usually we get into this realm of overfitting and doing Fourier transforms and making things far too complicated because that's what fits the data the best. So the last kind of vignette is about Kepler and Newton. This is one we've been thinking about for a really long time. I mean, Kepler, based on the vast amount of data from Tycho Brahe, revolutionized our model of the solar system. So he was the one that finally broke kind of this Ptolemaic system, even though it wasn't as accurate, by figuring out that these planets move in ellipses around the sun. Okay, that's a really, really good model. Again, I actually think that machine learning would give you something much more like the Keplerian model, but not the Newtonian model. Okay, so we observe these planets in some kind of a steady state on ellipses. That doesn't tell you what would happen if you tried to launch a rocket from one planet to another. That's a transient. That's an extrapolation. Okay, so most machine learning models, like the best you can hope for is something like Kepler, which would model the steady state attractor and interpolate what you've seen. But extrapolating these transients, that's what we want, okay? And that's kind of the cutting edge of research in this field, is trying to go from Kepler to Newton, trying to go from Aristotle to Galileo, okay? That's really what matters for us as physicists. It's not that 0.1% extra accuracy that you can get from a deeper neural network. It's some kind of a parsimonious solution or some kind of a generalizable solution that actually allows you to extrapolate to new regimes. Okay, that's all I have for now. I'd be happy to answer some questions. And after the coffee break, I'll talk about how to use some of this for machine learning.
Question?
Yes, at some point in your talk, you mentioned that the difference between a neural network and a brain was the body. But the robot that you had falling early in your talk had a body.
The what?
The robot. I mean, this robot.
Yeah, the robot does have a body.
And had an interest in not falling.
No, I mean, this is almost a science fiction idea that, I mean, the robot, imagine 100 years from now, we have robots with artificial intelligence. They'll probably be much smarter than us, but their bodies will still be, I think, not nearly as rich in terms of sensory modalities and function. And so, yes, we have robots. Yes, they have sensors. They don't have the type of sensing and feeling and kind of interaction that we have. They're still fundamentally limited by their bodies.
As a mechanical engineer, I think this is much easier to build a body than to build a brain.
I disagree completely. I think there are unique challenges in both. I don't think building a body, I think that's massively oversimplifying how kind of exquisite our mechanical sensory systems really are. Okay. One here or one there? Yeah, maybe start there. Yeah.
are recurrent neural networks.
Yeah.
So, do you see that the possibilities to adapt it to learn from a high fidelity CFD simulation, for example? Is it computationally efficient to use this kind of temporal data for RNNs?
People are trying really hard in dozens of labs and making various degrees of progress. So I've seen a lot of examples where it's not obvious why we're doing it and what the benefit. So did everyone hear the question? Can we take a high fidelity CFD solution and learn kind of a neural network model to step this forward? The answer is definitely yes in some cases. In some cases there's a benefit, in others there's not. There's a really nice work by Michael Brenner and some of the Google folks who have shown that with some modern machine learning architectures, you can simulate systems with shock waves much more accurately and efficiently than you could with computational schemes. And essentially it's like learning computational stencils that are better and higher order than what we have right now, things like that. I would say that it really boils down to how clever the group is in formulating the objective and tying that to an architecture. The really good ones are able to do it. I think it's not obvious how to do it though. Yeah. Oh, yeah.
Yeah, I'm sorry. I would like to come back actually to the example from just before. For the gravity, for example, when you speak about the ball that you throw, could it be that just because, speaking about the quality of your data, we are all subjected to the same gravity? So if you would have some sample that you could give to feed to your neuronal network of the same ball but on the moon or something like this, well then you would be able then to, as you said, to interpolate, not extrapolate, but interpolate thanks to the new information that you get from your data.
Yeah, that's absolutely a great point. So this whole history of science is something Nathan Kutz and I spend a lot of time kind of talking about together, and I think he was the one who found this in Principia, I think in book 2, are these accounts of Newton doing these painstaking experiments where he has balls on the end of pendula in different fluids of different densities so that he can start to disambiguate the effective fluid resistance from the gravitational effects. Because even then, they still had these debates about, was gravity constant? Were these motions consistent with the data? And so, in lieu of going to another planet, he created a different atmosphere for his experiments. And so, you absolutely need that kind of richness of data to make these hypotheses. Yeah.
So you have made a very good point that with machine learning, you can only do interpolation and not extrapolation. And you need a lot of data to fit a complex model. And I would say that most of the the fluid mechanics problems have only sparse data. Let's take the talk of Stefan Goertz on Friday. So he will talk about an Airbus. And the Airbus has different, you want to know the flow at different Reynolds numbers, at different Mach numbers, at different ground heights, at different angles of attack, and so on and so on. And if you look how much data you would need in order to fit your mapping x to x dot, it's impossible. Yep. And now the next thing, and I could give many of these examples, I would argue that most of the fluid mechanics problems will never generate, or let's take the actuators. At some point we talk about flow control. Will we ever learn where we need to place which type of actuator with what amplitude range, frequency range, location, and so on? We need to have the most effective flow control. Now we need millions of experience in order to guide us and in order to do the interpolation.
So this is such an important point, and I mean, we'll talk more about this in the next segment. But I hope everyone is paying attention. This is critical. The quality and quantity of data we have in fluids is fundamentally different than the quality and quantity of data Google has for images. Okay, we are data rich in some dimensions. In fact, we have too much data right? You run a simulation. I literally have people physically mailing me hard drives because they have so much data and we want to transfer it for one Reynolds number, for one Mach number, right? So we're data poor in the dimensions we care about, where we want to know what's the effective Reynolds number, what's the effective geometry. Those are expensive to get data that's rich in those dimensions. And so this is a fundamental problem that we have that we're still wrestling with. We're still figuring this out. And I think, Bernd and I have talked about this, kind of what is the extrapolation, what is the data set we need in fluids that would be like the ImageNet data set for fluids? And it's bigger. I won't spoil it for you, but it's bigger, and it's a lot bigger. Okay, we probably want coffee. All right.
Then, thank you.
are you?
Good. So far, so good. Just wanted to ask you, will you explain a little bit from the basics of functioning of neural networks? Because I'm really a noob in that matter, and I don't know if it's implicit or not.
Unfortunately, this is about as much as I was going to talk about.
Okay, okay.
There are that's not even oversimplifying. That's all it is.
Right, okay.
And then, the architecture tells you what kinds of functions are easier or harder to make.
Okay, well, I'll have a look at it.
Cool.
Thank you.
Thanks.
You curse a lot when you're.
Oh, do I? right, welcome back, everybody. Hopefully you had lots of coffee. Can everyone hear me okay? Okay, so this has all been building up to discussing how machine learning and data-driven optimization can be used in the field of fluid mechanics. This is why we're all here, okay? This is very rapidly changing. People in this room are redefining the art of what is possible every day. So, you know, this will be different in a month. I don't need to convince you that fluid mechanics are important. Okay, we're all here because fluids are awesome. I was a mathematician before, and you know, I drink a lot of fluids and I eat soups and I live inside of a fluid. And I remember I was looking at a bowl of miso soup, and I thought to myself, this is so much more interesting than what I'm studying right now. Fluids are amazing. They have patterns that are beautiful and useful, okay? This is a picture from a review paper Bernd and I wrote a couple of years ago on flow control. And if you don't need more motivation, we literally work and live inside of a working fluid. All of our machines do. Pretty much many trillion-dollar industries have a working fluid at the heart. And better ability to model, predict, control, and optimize fluids, even small improvements, percentage point improvements, would have a tremendous impact in enabling future technologies in energy, in transportation, and health, okay? And again, I sound like a drum that's broken. All of our tasks are optimization tasks. Everything you've been working your whole life towards is an optimization that's high-dimensional, non-convex, multi-scale, and nonlinear. Okay, those are the problems we have. And that is the set of emerging techniques that is growing out of machine learning, is optimization-based models from data. Okay, good. So we wrote a review paper, Bernd and Petros Koumoutsakis and myself recently, on machine learning for fluids. So a lot of what I'm going to talk about is going to follow kind of this discussion. And I'm going to have some material from kind of all three of us in here. This is just a really pithy schematic of kind of how we see things working together in this kind of fluids data. There are the classical fields of theory, computations, and experiments. And now there's this fourth paradigm of data-driven inquiry. We now have data generated, vast amounts of data from these experiments and simulations. And in some sense, machine learning is a common data processing architecture that can kind of unify these classical modes of interacting with fluids. And this actually just goes to show you how I'm not that much of an engineer in a daily life. The first time I made this diagram, the gears didn't turn. And so I had to put in this little gear in the middle. Okay, so we're going to follow this basic progression. And actually, the way that this review started was in independent discussions with Bernd and with Petros. I heard this really interesting history of how machine learning, some of these ideas of evolutionary algorithms and genetic algorithms came out of fluids dynamics labs in Berlin in the 60s and 70s. So Reichenberg and Schweifel, there were these great experiments where they were trying to, in this case, minimize the drag on a 5-section plate. So you could change the angles of this plate to change the lift and the drag. And they basically developed a crude version of a stochastic gradient descent algorithm to optimize the system through an iterative kind of evolutionary procedure. And I'm going to kind of butcher the history a little bit, so good thing Bernd's here. But the idea was, at the time, even though this was groundbreaking research at the time, this was kind of laughed at by the establishment. This was not fluid mechanics. This was not what this institute was all about. And it's only by kind of good luck and the support of others that they weren't run out of their institute. Yeah, Bernd's going to fill in.
So the reward for Rechenberg was he was thrown out of the institute. So he was 3 years unemployed in the institute of Rudibert King because before Manfred Eigen, so a Nobel Prize laureate, rescued him, and then he was promoted immediately to a professor from being unemployed. and Schwefel was also thrown out of the institute. So both were accused of not doing fluid mechanics.
So this is how this review came about, was kind of just, discussing with Bernd and with Petros this rich history that machine learning and fluid mechanics have grown up together. Kolmogorov is one of the founders of statistical learning, which is a major branch of machine learning research. We are one of the original big data fields. A lot of the modern computational architectures, data processing architectures, and algorithms were developed to solve fluids problems. So a lot of the advances in principal components analysis, how we compute the singular value decomposition. Sirovich in 1987 wrote the snapshot POD paper that changed how we compute proper orthogonal decomposition. In the same year, he showed that you could apply this to images of human faces, and he invented the eigenfaces algorithm. So that launched these two massive initiatives, but this was based on advances in fluids data. Another thing that's kind of interesting is this AI winter. So those of you who are students of history will know that artificial intelligence and machine learning is not new. And in fact, this had been there have been hype cycles before. And the AI winter in 1974 was largely due to the great fluid mechanician, Sir Lighthill, who essentially held 3 computer scientists and statisticians on trial. This is the trial of machine learning or artificial intelligence, and he essentially eviscerated them. They massively had overpromised and under-delivered, and Sir Lighthill, was largely responsible for the funding being cut for a decade in artificial intelligence. What's interesting is that one of his main points was the failure of human speech recognition, and you see this is auto-translated in Google right now. So it's kind of funny that a lot has changed, but some of his original points are still quite valid. You have to be careful about the hype cycle and not over-promising, but you also have to be, respectful of limitations of the time are not always going to be limitations. Okay, so really interesting and rich history. So in this lecture, I'm going to go through a couple of different aspects. I'm going to talk in general about what makes fluids interesting from a data perspective and challenging, and what are some of the challenges in machine learning. So I'm just going to talk about the incompressible Navier-Stokes equations. We have a Reynolds number. This is essentially how we get our complexity, is by modifying the Reynolds number. I love this picture from the Feynman book, just showing as you crank up the Reynolds number all of the kind of rich behavior that you get in your system. And again, Bernd's point is excellent that if I have one experiment or simulation, I have a tremendous amount of data, but I might only have that at a very small handful of cases here. So, for example, Feynman distilled these 5 Reynolds numbers as being the pillars that you can interpolate between or extrapolate through, however you want to think about this. But that's only 5 kind of data points in that dimension. Okay, that's not enough for neural networks to really learn based on. And you have a really interesting set of phenomenology. This is just the drag coefficient as you go through the Reynolds number. This is actually why those ball drop experiments don't work, is because the constant gravity argument is not really sufficient. You have this massively velocity dependent drag profile. It's extremely nonlinear. It's not a constant. Okay. Good. This is a picture that I got from Sam Tyra from UCLA. I love this this picture of our Reynolds number 100 flow past a cylinder. This is our favorite benchmark. And then this is a satellite image of the flow over Rishiri Island in Japan. So even though you have this extreme complexity in your fluid systems, this massive range of scales, oftentimes you still have these dominant patterns that emerge that actually look relatively simple and low dimensional. So pattern extraction is one of the key areas of machine learning research in fluid mechanics, and then modeling how those patterns evolve. And in fluid systems, I remember hearing this from Lex Smits, who basically said you can tell a low budget movie by how many scales their turbulent explosions have. And so that's one of the hallmarks, is that anytime you zoom in, you get this kind of self-similar structure, and maybe self-similar is an abuse. You have, every time you zoom in, there is more structure to look at in these highly turbulent flows. And that makes them very challenging to model and to simulate, because sometimes these little scales, maybe they don't matter instantaneously, but their bulk effect does matter. Okay, so we have really rich planetary data. So this is a simulated satellite image from the Gulf of Mexico. So this is a really, really rich fluid flow. I think we have decades of this collected every hour over the entire globe. This is a tiny, tiny fraction of the data we have. This is the Ocean Next project. This is an incredibly large circulation model that the Europeans have been developing and trying to model kind of these fluid dynamics over large time scales. And this is just a set of videos I picked out to show. We had an IPAM workshop, a 3-month workshop on machine learning for physics, and these are just videos I decided to show a bunch of non-fluids people to get them excited. I love this one. Right, you see kind of just this massive range of scales and complexity in this Rayleigh-Benard convection. And this will just keep going. This is like a 5-minute video, and it only gets better. Yeah, question in the back? How can you tell what a fluid is doing from a satellite image? Oof, okay, good question. So, so the measurement is not my strong suit. I'm assuming they measure something and then they infer something. I know that around airports you can use LiDAR to measure things. I know people use radar, Doppler, velocimetry. Yeah, measuring ocean currents is actually still a pretty big problem. A lot of people drop buoys in the ocean or drifters and floaters. It's expensive. So you're constantly assimilating data from different sources, satellites, and on passive and active tracers and robots on the ocean. So a lot of data streams for assimilating this, but that's not I'm sure other people know better than I do. Isn't that great? I mean, really interesting. You should download this video. I'll make all the slides available. This is a fun one from the KTH group that's been inspiring a lot of work for quite some time, is just trying to understand kind of this rich multi-scale behavior in these boundary layer simulations. So this is, you can see these hairpin head vortices forming in this long developing boundary layer. And this just gives you some of the idea of the complexity and scale at work in some of these problems. And we're probably still decades away with Moore's law from simulating flows at industrially relevant Reynolds numbers, even with the biggest supercomputers, let alone being able to simulate them in real time or multiple, an ensemble of simulations for design optimization and control. Okay, so getting reduced representations of what's happening here, the things that, that matter for an engineering objective, is extremely important and extremely challenging. I mean, this is just so cool. Okay, I've always been inspired by this set of quotes from the Feynman lectures. This is kind of, I think, a really profound view on fluid mechanics. It's a lot of text, I apologize. But the basic idea is that, when you have a new situation, you try to make analogies to an old situation you've seen before. And he makes some comments about fluids. Have you never visited the Earth? Could you predict the thunderstorms, the volcanoes, the ocean waves, the auroras, and the colorful sunset? The basic idea here being, yes, we have governing equations. Yes, we know Maxwell's equations and Navier-Stokes equations. You would never predict thunderstorms from those equations, just if you had those equations. Okay? And there's this huge conceptual gap between having equations and having understanding or knowing what is possible. Okay? And that's something we struggle with. We don't know how effective of a flow controller we could possibly design. Like there's no theory for what the upper limits are in some of these situations. And so he says the next great era of awakening of human intellect may well produce a method to understand the qualitative content of equations. And I think this is really important. We get stuck often on this idea that we have the equation so we understand everything. And that's certainly not true. Okay? We don't believe that's how a moth interacts with a fluid, through equations. Okay? Good. And so how do we study flows? And this is how we are going to be studying them with machine learning. We study them through canonical flows. We find simplified examples and analogies. We work through analogies, and that's how our machine learning is going to develop. You're going to be developing models for different scenarios. Okay, so there's all kinds of cool examples. You have bluff body flows and wakes, which has one type of behavior and physics. You have mixing layers and shear flows. That is a whole, kind of different can of worms when you're modeling, right? So, for example, run DMD on flow past a cylinder and a spatially evolving mixing layer, and you'll find very different challenges in this modeling procedure. Yeah, and then all kinds of other problems. So one of the big ones is acoustic noise generation and turbulence and shock waves. And, scramjets are really important. We want supersonic transportation, hypersonics. And currently our models are too slow to really be useful. So we build experiments and we run these massive simulations. We need to accelerate these. Okay. Remember, the big change in machine learning in the last 10-ish years started with a data set. Okay, it did not start with a neural network. It started with a massive data set. This was essentially a service that someone did. They had the vision that this was what was needed, and they put tremendous resources into generating this library. And so that is the only way we as a community are going to move forward in machine learning research for fluids, is to have canonical, agreed upon benchmark problems and data sets. So for example, Bernd and team have been working on the fluidic pinball, which you've probably seen, the 3 cylinders. That is one new benchmark problem that has additional complexity that people can work with. There's some great ones out there. The Johns Hopkins database has really been pretty useful. I mean, how many of you have used the Johns Hopkins database? A lot of us. Very useful. This was not designed with machine learning in mind, I don't believe. Right? This is a bit older, and so there are some modifications that are going to be necessary for this to be useful for things like closure modeling and some of the modern tasks. Flow control. You can't just do flow control on a static data set that you download off the internet. Okay, you need a simulation or an experiment. But this is a commendable effort. This is where we need to be working, is to have agreed upon benchmark problems that we can compete our algorithms on. Okay. Yeah, this is just one example from this kind of turbulence data set. Is you see these kind of scales within scales of vorticity. So every time you zoom in, you kind of see additional scales. This is probably the Q criterion. I'm not entirely sure what's being plotted here, but I'm guessing it's Q criterion. And when you zoom in, you can see kind of additional structures. So, I mean, this is not a toy data set. This is not flow past a cylinder at Reynolds number 100. This is much more sophisticated multi-scale fluids data. Okay, but this is a challenge. I mean, someone in this room hopefully is gonna be developing the next kind of version of this that we can all use. We should be doing this together. Okay, I'm gonna talk about some interesting examples of machine learning in fluid mechanics. And this is gonna be highly biased to work that we've done and work by collaborators. So I'm just gonna tell you our perspective. And the idea is not at all to be thorough or comprehensive, because that would be impossible. I just want to give you a flavor for some of the cool things you can do. Okay, so machine learning is just optimization with data. So I'm going to start off with something that has nothing to do with neural networks. Okay, because I think that's healthy for us all. I'm going to talk about the robust proper orthogonal decomposition. This is work by Isabel Scherl. So she has a poster outside, and you should talk to her about this. And it's really, really interesting. So we all are familiar with the POD. We use it all the time. How many of you have done POD on experimental data? Okay, are your experiments clean? I mean, probably you hope so, but like, do you have Gaussian white noise on your experiment? Do you have outliers and corruption? Every experimental data set has outliers and corruption. It looks like TV static on top of a flow field, okay? Even the good ones, yeah. Same is true for CFD. And so we had this idea, there are really powerful techniques from statistics to robustify these algorithms. And these are really simple modifications to our classic algorithms. So of course we know about our POD, we can decompose a very high dimensional flow field into a linear subspace spanned by a small set of orthogonal modes. That's very useful for taking something that was large and intractable and bringing it down to a representation that's finite and manageable. You can build models here and do control and all kinds of stuff. But when you have experimental data, you often get corruption that messes up your modes, okay? And so there's this really cool algorithm, Candes et al. And others in the field of robust statistics have been developing these algorithms over the last 10 years, maybe 20 years. This one is called robust principal components analysis. And remember, anytime I say PCA, you should be thinking POD, they're basically the same thing. So this is the Yale B data set, where you have 36 individual human faces, and for every single human face, you have 64 images of that person with different lighting conditions. It's a really cool experiment. They built a geodesic dome with a bunch of lights and a camera, and they just flash them in 2 seconds and take 64 images, so you get all the shadows, okay? And so with this massive data set, what you can do is you can learn what are the statistical features of a human face. Like, we're not as different as we think. We all are an oval with some circles and some dots, right? Like, we're basically the same. And so once you learn the statistical features of what makes up a human face, this is literally just doing POD on a library of human faces, you can use that statistical knowledge of what makes up a human face to subtract off large occlusions or outliers or corruption. So you can put a mask on this person, this funny mustache, and the algorithm can say, based on what I can see in the algorithm, this is consistent with the low rank dynamics, with the low dimensional dynamics observed in the data, and this is all of the stuff that is an outlier, a sparse set of outliers. You can literally like pull a disguise off of someone. You can't rob a bank with a hoodie anymore, because if any part of you is showing, they're gonna correlate it and figure out what your face looks like, okay? So the idea here is you can use this for corrupt flow field data. This is, I'm going a little fast. Does this make sense what I'm saying? There are statistical features in the data. This is not random data. These are human faces. And so even if I see a human face with something messed up, I can figure out what's under that based on the statistical correlations with what we have in the database. Now, again, this is an optimization problem. I haven't shown you how you solve for L plus S. This is a non-unique problem. There are many L's and S's that add up to X, right? This is a massively underdetermined problem. There's infinitely many solutions to splitting X into L plus S. So you have to set up an optimization problem so that the solution you want is the one that comes out, okay? And this is the solution that this is the optimization problem you would want to write down. You want to write down X is split into these two matrices such that the rank of the low rank part, the number of POD modes is minimized, and so that the L0 norm of the sparse corruption part is minimized so that there's as few kind of outliers as possible. But this is a non-convex optimization. This can't be solved in polynomial time, so you relax it. And that's a huge theme in machine learning, is you add these penalties to promote unique solutions in underdetermined problems. Closure modeling, it's an underdetermined problem. What is the prior, what is the regularization you're gonna add to pull out the solution that is most physical? Okay, and in this case, sparsity tends to be a good regularizer for corruption and robustness. And so this is the convex relaxation that Candes came up with. Isabelle has applied this to lots of interesting flow data. So this is our favorite Reynolds number 100 cylinder that we've massively corrupted with salt and pepper noise. I mean, this is real. This is a real movie from the method working. Okay, so you run this movie, you build a statistical kind of understanding of what a flow field is, what the low dimensional structure of a flow field is, and when you run it through this optimization, what comes out is a very clean low rank structure. You can see that there is a little bit of a shadow of the noise in the wake, so this is, we're not cheating here, this is really data, and all of the outliers got pulled out. Okay, so you can do pretty amazing things with, yeah, question in the back.
Can you wait that I
Just
bring
1
it?
second.
So the S matrix, it's sparse in what sense?
Sparse means, sparse literally means it has mostly 0 entries. It is only a few non-zero entries.
But like
Yeah, it
seems
doesn't
like
look
the
that
noise is
sparse. It's a little
everywhere.
hard to see. I think this is probably about 20% corruption, but we're computing vorticity from it, so it corrupts its neighbors too. So it's a little hard to quantify, but sparse just means you want it to have as many 0 entries as possible. It doesn't mean it has to be 1%. It could be 30%.
So is in general noise usually sparse or localized in certain
Okay.
regions of the flow?
So this is really important. If I had contaminated, if we had contaminated our data with white noise everywhere, regular POD would have been optimal for filtering that. If I had enough data, the SVD is the best thing you can do to filter white noise. Okay? That's like how it was developed. Principal components filters white noise, Gaussian noise, okay? This is not white noise. This is salt and pepper corruption. You like manually take the pixels and make them +10 or -10 at random, okay? So this is more like the kind of corruption you see in experiments from PIV imaging. You could also do something like you could have this movie and then one of the frames, the back part could have just been blacked out. And what that does when you do a POD is a linear regression, and that's gonna tilt the whole regression plane because of that one outlier. And this will robustify it and get the modes back. Okay, good. And so this, you know, these are the true modes from the clean data. This is what you would do if you ran POD, just vanilla POD on this contaminated data. And this is Isabelle's robust set of modes. So you get a massive cleaning of this. And we only have a few periods of this data. I think we have 5 periods of shedding, something like that, 2 periods. You can use these modes to build models. And when you do DMD before, these white circles are kind of the truth. And you get this terribly contaminated model here. And after RPCA, you almost nail the correct eigenvalues here. You can actually quantify how much noise reduction there is based on this really nice work by Shervin Bagheri, who quantified kind of how noise would mess up these eigenvalues. So that's, I think, a really cool connection to some classical theory of Koopman and DMD. And so Isabelle applied this, you know, if we had just applied this to our toy data set, it would be cute. Isabelle applied it to 2 experimental data sets that are actually of interest to us and are actually corrupt. This one is data from Jessica Shang's PhD work. This is flow past a cylinder at Reynolds number 413. This is more like what I'm used to seeing, right? It's pretty noisy. It looks like there's a lot of TV static on top. And it's not Gaussian white noise. You see these like bright spots just kind of flare up at random. Those are occlusions and outliers. And so when you run through this optimization, and this is something interesting, that regularization term, that L0 term that we added to make our solution unique, you get to decide how much to weight that term. And that's, again, just like in the Cindy algorithm, you have to choose how important sparsity versus accuracy is to you to find the right solution. The Candes paper has a guideline for how to choose lambda, given some assumptions, and it turns out to be a pretty good assumption. So if we have lambda too small, we overfilter, and a lot of the coherence goes into the sparse part. So this is overfiltering. If the lambda is too high, we are not being aggressive enough, and we are catching some of the massive outliers, but this is still pretty crummy. And so there's this Goldilocks zone in the middle where you get kind of just the right amount of lambda, and it's inevitable that you're going to filter some structure and you're still going to have some contamination because this is real data, but this is still significantly cleaner. I mean, look at the difference. This is what you want. And it's a little subjective. You have to make a judgment call about about what you want. So we've also applied this to the Johns Hopkins turbulence database, actually, where it is multi-scale, and we know the truth of all of the scales. And Isabel carefully quantified, as you change this lambda, how do high-frequency structures get filtered. Okay, so you can really use this algorithm right now. Question there? Yep. Yeah, so I'm going to repeat the question. Does this matter where you apply the RPCA algorithm in the PIV processing pipeline? Because there are lots of steps going from raw images to velocity vectors. That's the last section of the paper Isabel wrote, is all about analyzing that pipeline and what happens when you put RPCA in different stages of the pipeline. I hope I don't get this wrong. The basic takeaway is that in principle, you can apply this in lots of places in the pipeline, but there are some places that are better than others. The figures are on her poster, so check it out during the poster session. Yeah.
So is there a way to use some physical informations on the length scale or time scales of the problem to choose the filter? Let's say you know the Kolmogorov scale or can estimate from the Reynolds number so that you choose at least not to cut over the Kolmogorov scale or to be aware of it.
I think that's a great idea. There are so many other ways we could have regularized this problem. We could have done a total variation regularization. I know that Bernd and I talk a lot about total variation. Regularization seems to be an extremely physical regularization term, and that one does have kind of tunable length scales in some cases. So yeah, absolutely. This is the first step in this direction, but there's lots of regularization you could add to these problems. Absolutely. And I'll just emphasize, like, for physics, that's where a lot of the human expertise comes in machine learning, is choosing your regularization. You have most machine learning tasks, inverse problems, most of the optimizations we want to do are ill-posed, underdetermined problems. They have infinitely many solutions or no solutions. And so you choose a regularization to promote the solution that is most physical based on your understanding of the world. That's where your human expertise and creativity comes in. That's why we are still valuable in this process. Great. Okay, any other questions?
Maybe just a curiosity.
Yes.
You tested over the vorticity field. So vorticity means computing derivatives, so it means amplifying the noise.
Mm-hmm.
How does it compare if you do this in the velocity field with standard PIV methods?
So Isabel has looked at both velocity field and vorticity field. You can do it on both. Yeah, you definitely have to be careful about computing derivatives with these things, but she's looked at both of them. You can apply it in either stage that you like. Cool, yeah. So another one I'm going to talk about is super resolution. This is just incredibly fascinating and useful for us. So, we want to solve real turbulence problems, and we work on these toy canonical problems that are oftentimes laminar, oftentimes massively simplified. And so there's this idea of large eddy simulations and trying to infer what's happening at subgrid scales. It's very closely related to the super resolution problem in imaging. Okay, super resolution is a hot topic. Again, this came out of robust statistics, leveraging the patterns in the data. If I know that this is an eye, I can figure out based on the neighbors how to fill in. This is, I'm sure, a dramatization, but you can use the statistics of the data sets you're working with to infer what's happening below the resolution that you're measuring, because the data is not random. That's a robust statistics idea. And now this is possible to do even better with deep neural networks, super resolution. And this is a very plausible path forward to have super resolution as a method for turbulence modeling and closure modeling and things like that. So I'm going to show you one paper. I know there's lots and lots of good work on this. I know Sam Tyra and collaborators have done this and many others. This is work by Ben Erickson, who's at Berkeley now. And this is a shallow decoder network. So he chose shallow instead of deep, basically to show that you don't need it to be that deep to do this task. And you can take either sensor measurements from a flow, or you can take a downsampled low-res image, and you can run it through this trained network and reconstruct the high-res flow field, or the high-res flow field from this low-res image. Okay, pretty cool. I think the Tyra algorithm has some nice features that go beyond, in some dimensions. They have some convolutional layers so they can get some multi-scale phenomena. It's really interesting too. But the basic idea here is that, again, from the statistics of our flow field, this is, again, the Johns Hopkins database. It's been invaluable for us. You can learn how to kind of boost the signal and get the super resolution. Okay? But there is a cautionary tale I have to tell you about this. You can use this for interpolation, not for extrapolation. Okay? So here's how I train, not I, here's how Ben trained this network. Is essentially what you do is, this is a flow field that's evolving in time, right? This is the isotropic box turbulence, I think, data set. It's evolving in time. And so you have your data at time snapshots. And what he does is trains it on these dark gray time snapshots and then tests it on the blue ones, which are fundamentally between things we've seen. It's an interpolation task. And on an interpolation task, he absolutely nails the reconstruction. It's like almost indistinguishable. You have to zoom in to see the differences. Okay? But that's not what we're often doing in fluid mechanics. Like if I want to build a model for the climate, it is not going to be the same in 10 years as the last 80 years, right? There's no way we can expect that to be true. We're not doing an interpolation task. And so we decided to try this on an extrapolation version. So we trained it on the first, whatever, 80% of the data and tested it on the next 20%. And here's what you get. So this is the truth, and this is our reconstruction. For very, very near future, you get almost perfect reconstruction. And then soon after, as you evolve in time, your prediction starts to degrade and break down because it fundamentally has not seen enough richness of training data to extrapolate the model. Now, that's not to say that it is not possible to learn more generic features from a limited training set. It's just that with this shallow decoder, the simplistic architecture, this does not generalize. You have to do more to make that work. Okay, that makes sense? It's an important cautionary tale. You can absolutely use this. You have to be careful how you use it. And this is not something that any machine learning person would argue about. They know that they're building interpolators. That is, like, they have, if your training data is not statistically representative of the task that you want to perform in the future, you should stop trying with basic machine learning algorithms. Okay? And so you can ask yourself why we had so much trouble predicting the future here. So here is just a range of interesting flows of increasing complexity. This is low complexity. This is actually medium complexity. The sea surface temperature is very periodic. And then high complexity and super high complexity. This is work by Jared Callahan and Kazuki Maeda, where basically we were looking at how much data do we need in varying complexity fluid flows to build a statistical picture of what's in the flow. Okay? And if you only train your models on the cylinder flow, which we're guilty of in many cases, it's not a complete picture, right? It's easy to reach statistical stationarity in the cylinder flow. You see one period, you've seen all periods. That's not true in the mixing layer. You need thousands and thousands of snapshots, tens of thousands of snapshots in time to even approach statistical stationarity in this problem. Okay? And so, I mean, we're just looking at the singular value decomposition, the POD, you can see, the cylinder flow drops off very rapidly. This is on a log scale. But some of these flows take a long time to decay, and we really haven't even begun to reach the stationarity for the Gulf of Mexico and the mixing layer flows. Okay? Now, you could do better dimensionality reduction. You could do these deep autoencoder networks and probably get a better representation, and a representation that would generalize maybe more, capture more of this rank. But the idea here, and this is something I didn't know until working through this problem with these guys, is this idea of a decorrelation length. So how many of you have heard of decorrelation length in fluids? Yeah, I mean, I didn't know about this before, but it's really interesting. So the mixing layer is a perfect example of it. The mixing layer, the spatially evolving mixing layer, goes through these various regions where it's basically linear, basically nonlinear with some kind of a nonlinear resonant, and then chaotic down here. And so if I just take a snapshot of the flow here, it is pretty predictive of what the flow will be right here. If I see one set of structures here, I can kind of infer what will happen here. But if I take a snapshot of the flow here, I could see any number of things down here. It is statistically decorrelated from this upstream region. And that's something really profound in this data set, is like human faces don't have this problem. If I see your left eye, I can tell what your right eye is going to look like, probably. Not every detail, but largely. Your face is not statistically decorrelated. Flows are. That's a big problem for machine learning. Okay? Just thought I would tell you. I didn't know this before working on this. Okay, good. Is there a question about that?
So what you're talking about is ergodicity in turbulence,
Yeah.
right? So are you suggesting somehow that I have to wait to have a statistical steady state solution on a turbulent flow? So let's say I have a turbulent statistically steady state problem. So should I wait to have the averages and the moments, statistical moments, to be converged in time before starting picking samples to train my machine learning? Is it oversimplifying or totally?
That's not exactly what I'm saying. That's kind of what I'm saying. What I'm saying is, depending on what architecture, what learning architecture and what representation you're using, you may or may not have learned enough about the flow to be useful in the future. If I build a POD model based on the first 40,000 snapshots of this thing, it only describes 40% of the next 10,000 snapshots. It's just not enough information in that, at least that POD representation. There might be other representations that are better, but for our shallow decoder, for POD, for other algorithms we've tried, like that is a big problem, is just reaching stationarity. Also the decorrelation length, I think that's another fundamental item here, and that's of course related to kind of this chaos and uncertainty amplification, is that there is simply not information enough here to be able to make a determination of what is happening here. Like if you try, maybe, okay, I'll put it out as a challenge, and if anyone proves me wrong, I'll be very happy, but I think if you try, you'll fail, because there's just not the information there. It's like you can literally see multiple things downstream with the exact same flow upstream. And that's something that, you know, is just fundamentally different about these problems. Question there, and if you say it, I'll try to repeat it. Yeah?
Can you repeat the question?
Okay, I'll repeat the question. The question is, there's a concern in the earlier example of the interpolation that maybe what you're getting out is just pretty pictures, but you're not getting new information or understanding about the flow. I mean, that's an extremely valid concern. But I mean, it depends on what you're going for. If to some extent, I could take my Navier-Stokes solver, and I could take that low-res downsampled image, and I could write some other optimization to fill in the details using my solver, but it would be much more expensive than that neural network we trained. So somehow there is this compression of information and processing to take a low-res image and lift it back to a high-res image. That could be useful in an interpolatory task. But you're absolutely right. The bigger concern for me is that we probably are breaking all conservation laws. So if you actually took that solution and ran it through the code, it would not be happy, because we have completely gone away from the Navier-Stokes equations. And I know there's a lot of people who are carefully thinking about how to do kind of generative models. Can I generate a flow field from a low-res image that is going to satisfy my basic conservation laws by construction? That's an open problem. That would be very transformative. That's what you need for kind of closure modeling, I think. Yes?
Does it depend on the amount of resolution? I mean, if we have different resolution images, then the result would be something different or better?
Absolutely. It strongly depends on the resolution. You can imagine, let's do a thought experiment where I have 1 pixel, right? You don't have enough information to tell anything about what the image is. So at some point, there's not enough information to uniquely specify. Again, that would be kind of like this decorrelation length argument. There's just not enough information to uniquely tell what's between the pixels. I'm sure that we have looked at that. I don't remember off the top of my head where we are, but you can kind of double and halve the resolution until it breaks or until it like trivially works. Yeah, I think that's actually one of the nice things about these architectures is that they're pretty flexible. You could take different informations at different scales and probably use those to fill in the gaps. And that would be harder to do with some other algorithms, I think. I don't know. We didn't do that. Yes?
As we are talking about trade-offs, you could, when you have to trade-off, for instance, how much fluctuation energy you resolve, or what is your prediction horizon of your model.
Right.
There's your prediction horizon is always much more important than the fluctuation energy resolved, because you can always link what you are not resolving. If you have something like a peephole which tells you the future on some subspace.
I think this is an interesting point. So to some extent, expert knowledge of what matters is the most important part of any machine learning optimization, is writing down, like, you pose a problem, you get the data you think is representative of that problem, and you train some representation of a model that you think will model that problem. And you need expert knowledge to figure out how to determine what matters to you. Okay, I'm going to talk about a different topic now. I'm going to move on and talk about reduced order models. And Bernd's going to talk a lot more about reduced order models. I'm just going to kind of briefly touch on this in one vignette. This is actually work with Jean-Christophe Loiseau and Bernd and others, Nathan Kutz and Josh Proctor. So we're going to go back to our Reynolds number 100 cylinder, which is dangerous because we know that this is overly simple. Okay, we've applied this to more complex flows, fortunately, in the meantime. And of course, we've learned from Bernd and collaborators a while ago that you can model this flow using 3 modes. You've seen this before. Yes? Yes? No? I'm assuming you have. So you have your shift mode, you have your 2 POD modes, and essentially you can write down the dynamics of the flow in those 3 coordinates by this simple differential equation. Very simple, surprisingly simple. And essentially it describes both the periodic vortex shedding behavior in the limit cycle, these are in POD 1 and 2, and transients as it converges onto that limit cycle. And I don't know, I love this model. So remember yesterday we talked about nonlinear dynamical systems. This is the first model that my PhD advisor put me on for modeling airfoils, was to try to model it a la Bernd. And so remember, we had the Hopf bifurcation. As you increase the Reynolds number, you go from a steady solution to periodic vortex shedding. That Hopf normal form had cubic nonlinearities, right? It had a cubic term. But our Navier-Stokes equations are quadratic. This is one of my favorite parts of this whole modeling thing, is this idea in this paper that this shift mode, this z direction, is very, very fast compared to the x and y dynamics. And so lambda is really fast, which means that rapidly z equilibrates to equal x squared plus y squared. Which means if I start off this manifold very rapidly, I zip up to the manifold, and then I slowly move on the manifold to vortex shedding. And so if you take z equals x squared plus y squared and plug it in here, you recover the effective cubic nonlinearity from your Hopf normal form. And this was really important to rectify how you could observe a cubic nonlinearity Hopf bifurcation with quadratic Navier-Stokes. It's a separation of timescales argument. Okay. So essentially what we did, the first thing we did was just apply this SIND sparse identification of nonlinear dynamics to this data. And remember, the hardest part was knowing what to measure. We built on Bernd's work. He told us what to measure. We knew exactly the 3 coordinates to measure the time series of to get the right SIND model. So that we should be very honest about. But once you measure the right variables, x, y, and z, it's a relatively simple optimization procedure to develop a model that looks a lot like this from that data. And so, you know, the identified system, if you just give it measurement data with some transients, your identified system picks up this slow, fast separation timescales. It has quadratic nonlinearities, and it has this, this parabolic slow manifold. Okay, so you can learn these structures in a kind of unsupervised way, as long as you start with the right coordinate representation. Yes?
Is it really unsupervised?
No, it's very supervised. I mean, we, like, to some extent, it's a little unsupervised. We collected measurements from a simulation. We extracted time series of the relevant coordinates that an expert had told us are the right ones. And then we plug it into a generic algorithm and turn the crank and models pop out. It's not entirely unguided. It can be used by an expert human to build a useful model. That's more accurate. Good. And we were super excited. We thought this was pretty cool. You could get, I mean, because this is a rich history story. So the NOAC paper was 2003. These models had been posited since the 70s. And there had been these major breakthroughs. You know, this is not a simple story. This had taken a long time to develop. And so the fact that you can take just measurement data, informed measurement data, and run it through an optimization and get a model that took really, really sharp people decades to find, it's pretty useful, okay? And now the story gets interesting. The reason I'm telling you this is because of the next piece, which is when Jean-Christophe Loiseau emailed me. So he was a postdoc at KTH at the time, and within 2 weeks, I think, of getting this archive paper out, he emails and says that there were some fundamental problems with our model. Okay, we had the wrong unstable growth rate. There were some issues with the model. And so what JC, you know, I was a little bummed out, but I was still pretty encouraged. He emailed back a couple of weeks later and he said he fixed it. And so I want to tell you about how he fixed it, because I think it's an extremely good example of the types of things we should be doing when we do machine learning in fluids, okay? So what JC realized is that we have a lot of prior knowledge in the system. It should not be unsupervised. We know that this incompressible Navier-Stokes equation is energy conserving. We know how the nonlinear term, the quadratic term, conserves energy by mixing the energy between modes in a particular way. There's a symmetry in the quadratic terms that determines how energy is conserved. And so what he realized is that you can enforce known constraints in that Cindy regression. You can build a set of constraint equations that, if they are satisfied, your model is conservative by construction. That's amazing. He baked in energy conservation to this machine learned model through one extra set of constraint equations. And that's one of the things we like about the Cindy model, is it's basically a least squares regression with a sparsity term. And constrained least squares is essentially trivial. It's like a little bit more expensive. Okay? The other thing JC realized, and I think this is super cool, is this idea that we were trying to get quadratic models because that was the cool history story of how you get cubic nonlinearity with a quadratic model, and you know that was interesting at the time. What JC realized was that if you relax that assumption and you allow yourself to have higher order terms, cubic, quintic, septic, nonic terms, I don't know what an 11th order model is called, essentially what you get these higher and higher and higher order terms that approximate the POD modes, the effect of the terms you're truncating in your Galerkin expansion. It is a rudimentary closure model, albeit for a laminar problem, but for all of the energy that you're neglecting by truncating at mode 2. It's remarkable, and you get much more accurate models doing it this way than if you did Galerkin projection onto a second order model. Okay? So this is kind of just to show, we did this on the cavity flow also, and JC's applied this to a lot more sophisticated fluid flows. So this has scaled to much more complicated flows at this point. But so what we see here these are basically proxies, in this case for the drag coefficient. And in white is the true DNS solution. In yellow and blue are POD Galerkin models of order 3 and 7. And you can see that they kind of qualitatively match. They're not terrible, but they also have overshoot, steady state error. You know, they're not like different wrong growth rates. When you include either the energy conserving constraint on Cindy or you allow it to have cubic nonlinearities, you almost perfectly match the growth rate almost no overshoot, and the right steady state behavior. Just by giving, so we call this Galerkin regression. Instead of projection, you're regressing and you have a little bit more flexibility, a little fudge factor to scooch your model to account for all the things you're truncating. Okay, but I really think that the energy conservation is the coolest part about this. And so JC was able to write down a very simple model. This is the model he got for the cylinder after developing this all in terms of his 2-mode model. This is the simplest model I've ever seen for flow past a cylinder. It is a spring mass damper with nonlinear damping. It's essentially a van der Pol oscillator. Remarkable, and it's more accurate. That's crazy, okay? I think Bernd's gonna maybe tell you a little bit more about some extensions to doing this based on sensor measurement, maybe? Good. Okay, so just so that you see how you actually do this energy conserving law, this is all JC, to be honest, I didn't know about this before meeting him, is this idea that we know how the convective nonlinearity in the Navier-Stokes equation conserves energy. This has to be true. This is what it looks like in my reduced coordinates and my POD coordinates, the A vector of coefficients. And you can write this out in kind of components here. And what this means is that you can derive a bunch of constraint equations so that this all adds up to equal 0. And when you do that, you get a small handful of constraint equations on the Cindy coefficients that have to be satisfied for any model to be conservative. You then write that into an extra constraint using a Lagrange multiplier formulation. And with the KKT least squares, you can basically just solve this like that, super simple. Deriving the conservation laws, I have a student now who's doing this for MHD problems, very challenging. So deriving these conservation laws, this is where all the magic happened. This is trivially easy to enforce them. Okay, and I think Bernd will talk about doing this on other measurements for more complex systems. Okay, good. Any questions on that? If you have questions, ask JC. Seriously, I recommend everybody should meet him. He's awesome, and he works in the center of Paris, so go visit JC. Okay, latent variables and deep learning. So this is another big area that we work on. Remember, you have the problem of discovering nonlinear dynamics. That's reduced order modeling and system identification. You have the problem of learning coordinates where your system can be simply represented. And so that's where if you have latent variables, if you either measure too much and you don't know what to extract, or you measure too little and you want to build a model, you can use these architectures. So remember that we can write our POD or our principal component analysis as a shallow linear autoencoder. Okay. So the loss function here would literally be, I should have written this out, but what this autoencoder does is going from X to Z is multiplication by a matrix U. That's my weight matrix of this layer. And then going from Z back to the high dimensional space is multiplication by this matrix V. That's another weight matrix. So you would literally say X hat equals V times U times X. And my cost function is the difference between V times U times X minus X. That's what I want to minimize. I want this to be as faithfully representative as this as possible, knowing that I'm crunching down to a 3-dimensional space in the middle. And if you solve that optimization, you recover your POD. Now, I should be a little bit clear about this. Every time I've ever tried this, you need more data. The SVD is an optimal solution. If you do this, kind of ad hoc neural network optimization, you need more data, and the modes that come out are not ordered, so you still need to do some kind of a factorization at the back end. But it's in principle like a POD. And you can generalize that to these deep autoencoders. Okay, so this is really, really powerful for fluids, and you can use convolutional autoencoders. You can put a convolutional layer on the front end. You can use variational autoencoders, so you have some statistical variability, so you can sample from a distribution for turbulent solutions. People have dabbled with this for a long time. The first solid work I've seen on this in fluids is Milano and Koumoutsakis in 2002. Not a lot of work broadly after that for a while until the second wave of deep learning, and now there's a lot of people building deep autoencoder networks, but I think there's still a ton of opportunity here. There are, in the molecular dynamics community, protein folding, they have similar high-dimensional, nonlinear, multi-scale stochastic problems, and they have, I think they're ahead of us in using these variational autoencoders to generate statistically realistic high-dimensional data that could fool a physics engine. We should be doing that, okay? This is work by Kathleen Champion, who was, this was when she was a PhD student with us. You can tell that I made this at APS and forgot to delete my, my note. But what she did was basically combine this autoencoder network with a SINDI parsimonious modeling procedure in the middle. So what you do is you have high-dimensional data, you want to learn a low-dimensional representation through this autoencoder, but then you want to develop a nonlinear dynamical systems model for how those latent variables evolve together in time. Okay, so this is a joint optimization trying to find a coordinate system and a nonlinear model. Okay, it's a kind of a hard problem. It took us a long time to train this network because it's pretty, it's got a lot of constraints on it. Okay, but in principle, you can learn these coordinates and models. You know, we did this on pretty simple systems. I want someone to do this on a high-dimensional turbulent fluid flow where you really do need a pretty sophisticated network. Okay. Bethany, this is actually work that came before. This is Bethany Lush, who's now a scientist at Argonne Labs. This is when she was a postdoc with us. She built a deep autoencoder network to learn Koopman transformations, Koopman eigenfunctions. Okay, so you can basically build a coordinate transformation into a space where your nonlinear dynamics become linear. So you can learn the coordinates and the linear Koopman model. And this is actually something that lots of people in the community are doing. This is actually an out-of-date list. I was at a BAMP workshop in January 2017, and there we were all working out, you know, how machine learning is going to change our field. And one of the things that came out was, we know we could do POD with deep learning or neural networks. Can we do DMD? And then very quickly it became obvious that the 6 groups doing fluids in the audience were all going to go do this independently. And so we all kind of raced for the next 6 months to try to build these Koopman autoencoders. And there's lots of other groups that have done this for their physics systems, a lot of them in fluids, a lot of them in molecular dynamics, but now there's a pretty vibrant community learning these coordinate transformations for their data. And so that's pretty exciting. Okay, so that's kind of these coordinate systems and representations. I'm going to talk about something that's a little bit outside of my, personal, what we do in the lab, but this is something of interest to us, is this closure problem. So lots of us, how many of you are interested in closure modeling? Good, I am too. Closure modeling is a huge deal, right? Like, this is the challenge of complexity we talked about. As you crank up your Reynolds number, you have to pay attention to more and more and more scales in space and time, and it just gets worse and worse and worse. And so what we would love to do is figure out how to get the effect of scales that we want to neglect in how they act on the scales we care about, the large scales. We want to know how the large scales evolve without explicitly modeling the small scales, but including an accounting of them on how they affect the large scales. It's like the most convoluted way of saying that. And here's how you would write it down in math. This is just one way of writing this down in math, but this is a nice way, is that you have a really, really, really high dimensional system of equations and everything depends on everything, right? But at some point, I want to just neglect all of these pink variables. I just don't care about them. I care about how they affect the blue variables, but I can't keep track of all the pink variables. And so what I want to do is I want to find some model of essentially how those high frequencies would depend on the low frequencies, and then how the low frequencies depend on the high frequencies, and build this model so that basically everything is a function of my large coherent structures here. That's what I want. That's the SINDI regression, the Galerkin regression that JC worked on, is one possible route, but there's many, many, many possible routes of learning these models. Okay, and I'm not going to talk much about this. This is a vibrant field, lots of groups doing this for LES, for RANs, for various types of closure modeling. And there's a ton of stuff out there. There's a really great review paper by Durasame, Yacarino, and Shao, I think about 2 years ago now, where they talk about kind of this field of turbulence modeling and closure modeling using machine learning. And there's just such a rich variety of papers on this topic, and I mean, this is a tiny fraction. These are the ones I've paid attention to recently. The Ling and Templeton work is particularly interesting in my opinion. So this is a picture from Julia Ling's paper, JFM 2016. And essentially what she was able to do was, instead of just building a deep, naive neural network, which is what you would do naively, she modified her network structure so that she embedded Galilean invariance into her model. So she knew that there was this kind of physical symmetry, and she modified her network so that by construction it was satisfied in the network. And that's the spirit of what we want to do. I will always prefer these models where a really, really sharp person has put in their physical knowledge. Okay? And actually, I think this is a great paper. How many of you have read this paper or seen it? Okay, good. So those of you who haven't, this is your required reading. It's really good. And I believe what they do is they go back to seminal closure modeling work from the 70s. And this is such a good strategy. You should all think about this in your field. You want to go back to the 60s or the 70s or the 50s. There were such brilliant people, and they didn't have TensorFlow, right? They were not just cranking shit through a neural network. They were really thinking hard about the physics of their problems, and they would derive these beautiful progressions of things that were true until they hit a wall where their mathematical tools were no longer sufficient to go farther. And that's where you get to pick up. That's where Julia Ling picked up. Okay? She found where it was no longer possible to model with the math of the time, and now she has replaced those approximations with better approximations. Okay? You should read this paper. It's really good. Okay, good. So for the last 15 minutes, I'm going to talk about flow control. I love flow control. So remember, machine learning is not magic, but we want to control fluids. Wouldn't that be cool? All right, so again, this is from the review paper with Barrett and me from 2015. Flow control is a really, really hard optimization problem. When I say that we have a non-convex optimization problem, does everyone know what that means? Would anyone like me to say what that means? So a convex optimization problem is easy. It's where there is a smooth mountain with one hump, and all you're trying to do is walk to the top. And how do you do that? What's the steepest approach to the top of a mountain? You compute the gradient, and you go in that direction. Okay? Non-convex optimization is where there are many, many mountains and valleys, and I can't even see past my mountain, and I have no idea where the global optimum solution is. And I can't just walk uphill because I might reach a suboptimal solution and get stuck there. Okay? It's really hard. And these high-dimensional problems have many, many, many local minima and local maxima. It's very complicated. And so there are emerging techniques. Machine learning is really great at non-convex high-dimensional optimization. Stochastic gradient descent is really good at this. Neural networks are massively non-convex optimization problems, and we're getting really good at finding them. One approach that I think is really interesting, this is the genetic programming approach that Barrett has been advocating for a while in experiments, is to learn your control law through some kind of a highly expressive function representation algorithm like a genetic programming tree, a function tree. And so the idea here is that it might be very expensive to run simulations of your fluid flow and optimize, but it might be relatively cheap to run an experiment and tell if your control law did a good job. So I think in this mixing layer, this was Barrett's mixing layer in Poitiers, where you have a splitter plate that is highly actuated. There's a bunch of pressure ports on the splitter plate. And you have a rake of hot wires, so you can tell if mixing was enhanced or decreased downstream. I think it only took about 10 or 20 seconds for every control law to tell if it did a good job or not. Like you get a pretty clear signal if mixing went up or down within 20 seconds. And that means in an 8-hour workday, you can try thousands of these controllers. And so the idea is you start with a bunch of random controllers, you run them, and then you breed the ones that are the most effective. You rank them, and then you do some kind of genetic operations to make them better and better. That's a form of non-convex optimization. It's been very powerful. Okay. Another optimization I really like, this is work with Ben Strom, who is a PhD student with Brian Palagi and me. This is work in Brian's lab, where he was trying to optimize the performance of a cross-flow turbine. And a cross-flow turbine is just a vertical axis wind turbine that's knocked on its side and put in a river. Okay? And this is kind of a big example of a cross-flow turbine that's going to go in a river in Alaska. This is a little lab-scale device that's about yay big. Okay? And so the idea here is you want to optimize the performance of this turbine to pull the most power out as possible. And we've known for a long time in helicopters that one way to do this is to dynamically pitch the blades in advance and retreat. Right? That's what you do in a helicopter. Why do we not want to do that in a remote river in Alaska? I always ask my engineers this. It's going to break immediately. Like, helicopters have the most maintenance costs. They are constantly being broken down and rebuilt because of these moving parts. Put that in water and it's a disaster, right? So you can't do it. It's a non-starter. And so what Ben realized was that instead of actually pitching the blades dynamically, as you can accelerate and decelerate this turbine through the different phases of its period, and it gives you the effect of a changing angle of attack because of this rotating frame. And so now this becomes a big optimization problem. He needs to optimize the rotational acceleration profile as a function of the phase angle to get the most power extraction. You can see here, this is a good example where he has pulled this large leading edge vortex in the power stroke. And in this case, I think we get 59% power increase over industry standard control. Okay. It's a big optimization problem. It's not a fancy optimization. This is a downhill simplex method, okay? But it is a data-driven iterative optimization technique, and you get massive performance bumps with relatively simple optimization. And then you can interpret the output. What's happening is basically it's aligning the formation of this vortex, the kind of maximum torque with the maximum velocity, giving you, at the power stroke. And the follow-on work, this is not related to machine learning, it's just super cool, and this is something Isabel's working on, is now taking these turbines and figuring out how to pack them densely in an array. Because again, in Alaska, you want to get as much as you can out of the resource you have. So now you're going to put these in an array, and you're going to try to have them work together through some coordinated control. And actually, this is a machine learning effort. We need a model for how this affects this, and it's very complicated and nonlinear. Okay, so this is like a Lagrangian coherent structure visualization of the wake of one of these turbines. This is a video Ben Strom made. And so now you have to start thinking about, if I was going to put an array of turbines together, where would you want to put them to get a maximal impact? Think about birds in a flock or fish in a school. Okay, that's what we want to do with these. So another area where machine learning is really useful for flow control is in building surrogate models. So this is work with Katharina Beeker and Sebastian Peitz. And actually, I just got an email. This, I think, paper was accepted today, so that's good news for us. Basically, we're trying to do flow control and flow past a cylinder or flow past the fluidic pinball. So we can rotate these things, and we're trying to track a lift profile or a drag profile. Running these full simulations with model predictive control is far too expensive. Model predictive control basically requires you to be able to run a forecast of many, many, many scenarios. I try this control, what happens? I try this control, what happens? At every time step. And that's far too expensive to do with a full fluid model. And so what we can do is, instead of running the full MPC controller on my Navier-Stokes solver, we build a deep learning model as a surrogate. It's much faster. It's not as accurate, but it's good enough. Okay? And then we can use that surrogate model to get very accurate control. In this case, we're trying to track the lift coefficient on these three cylinders to be 0 for the leading one, +1 for this one, and -1 for this one. And within a relatively short amount of time of turning our controller on, we get pretty good tracking performance. What you can do then is, as this evolves and you collect new data, we trained this model for just natural vortex shedding, no control, random control. And so we had not seen this solution in our training data. So you turn your controller on, and often what happens is you steer your system away from the region where you trained it. But you can use that new data to get better and better and better models, and you can get better and better and better tracking if you adaptively update your network weights. Okay? There's some kind of interesting not follow-on work, related work by Ulrike Kaiser. She basically compared how good model predictive control is with different types of models, SIMD models, neural network models, and DMD with control models. And what's remarkable, this is on a log scale of length of training data, almost immediately, within less than 10 data samples, the dynamic mode decomposition with the control model learns enough about, this is a low Lorentz system where linear models suck. DMD with control learns enough about the system for model predictive control to be nearly optimal within less than 10 data snapshots. The takeaway here is that DMDC, model predictive control, is so forgiving, you can often use linear models for very nonlinear systems. I highly recommend trying that before you build a neural network. Okay. Good. A lot of our perception of machine learning in fluids is inspired fundamentally by biology. We observe animals who are expert flow control systems. I mean, these animals have such exquisite capabilities that in many cases go beyond our best engineering attempts. And to our understanding, they do this without knowing the Navier-Stokes equations. They don't have full three-dimensional wake measurements. They're extremely robust to different weather conditions, rain and all kinds of things. Moths are particularly interesting. They have a sparse sensor network, a sparse set of strain-sensitive neurons distributed on their wings that they use to feel their fluid environment and the strain field that it generates on their wings. And so a lot of learning and flow control in many areas is inspired by biology. We at UW have a new wind tunnel that essentially we can create odor environments upstream of a moth and visual environments. We can measure the full three-dimensional wake downstream using PIV. One of our colleagues builds little backpacks that go on these moths and tap into their central nervous system so we can see what neurons are firing in their muscles. Very cool. And then we're trying to back out models for how this is a sensory motor processing system, how it's accumulating its information and making flow control decisions. This is work by Kumit Sakas et al. That I think is really interesting. They're using deep reinforcement learning to figure out how fish can swim and how they can school together and track each other. And there's a whole series of beautiful papers. This is kind of schooling fish or trailing fish using some of these ideas from deep reinforcement learning. This is a cool video that I got kind of inspired by Frank Noe. He showed something like this. I mean, just watch these dolphins hunt. Has anyone seen this before? This is pretty cool. So they're really hungry, and they're going to work together and use flow control. Look at, so he's beating his tail, creating this disturbance, and he's going to trap a school of fish. He or she, I don't know. Okay. And so the fish really don't like being in this enclosed space. And they basically created a feeding pen here. You're going to see in a minute all the fish jumping out right into their mouths. I mean, this is the kind of out-of-the-box thinking you only get by having creativity that we don't currently have in machine learning systems. Okay, so the last part of my talk is going to be completely speculative. So nothing I say here, you shouldn't hold me to anything. There is this massive and interesting trend in in machine learning to build these generative networks. So remember our Mona Lisa speaking. Can we generate flow fields? Can we generate from a distribution of observed flow fields new flow fields that would trick a fluid solver? Okay, and I don't know what that'll look like. This is one of my favorites. This is a deep dream of Arcimboldo's La Primavera. So this was around the same era as Tycho Brahe was collecting his astronomical data. Arcimboldo was an artist with Emperor Rudolph II. I think this is actually a picture of Rudolph II, the Holy Roman Emperor. And if you think about it, Arcimboldo, this was like the original Deep Dream. He made pictures of people out of like lettuce and fruits and stuff. That's exactly what Deep Dream does. Is it generates representations of images using dogs and cats and other things, peacock feathers. And so I think that's kind of interesting. Can we do that with fluids? Can I take my low resolution fluid, remember that picture of the flow past the mountain in Japan? Can I take something low dimensional and paint it with texture, the texture of turbulence, in a way that is conservative, that satisfies governing equations, that would trick an expert classifier? Okay, I have no idea if that's possible. I know people are working on generative fluids. I don't know what they're doing, but I'm very interested to see. I think that's going to be neat in the next couple of years. Okay, so with that, I'll take some questions, and then we can all grab lunch. Thank you.
First, thank you for this amazing talk. And I've got a question on extrapolation. You said that we can't extrapolate. I mean, these systems are really bad at extrapolating, but my question is that in fluid dynamics, this is what we do all the time. Like, for example, we take a canonical system like a flat plate and develop a model, and then we use it in an engine or something like that. Mm-hmm. And so we know we are missing somewhat some stuff. And my question is that I get the sense that this is not exactly the same, but how is it not exactly the same?
Yeah, I think that's a really interesting point, that you're absolutely right. We are expert extrapolators. That is our training. We are trained to be expert extrapolators. And we have, and there's some people are better at extrapolating, some people are less skillful at extrapolating. I mean, it's a skill. Oftentimes, you resort to things that you know fundamentally are true, right? We know that the Navier-Stokes equations will extrapolate and will be useful. We believe that it will be useful even in regions I haven't tested it before. And you have this deep knowledge of the literature and of what people have historically tried and succeeded and tried and failed. And so we are somehow a large interpolation. I'm not sure it's as much extrapolation as interpolating the history of all the experiments we've heard of that. I'm not sure. Maybe that's philosophical. Does that make any sense? Like, you're kind of interpolating the literature of how things are connected. So how do you use a Reynolds number 100 blade in a compressor? Right? Like, how could you possibly use that information in this scenario? Well, people have looked at that for a long time, and so we have a lot of information that we're collecting. I don't know. That's maybe not the best answer, but. This is when something is really well known. I mean, at first it was extrapolation. Yeah. So okay, when something is not well known, oftentimes, like, okay, so the process of conducting a research project oftentimes is not a straight line. It's not like, okay, I want to develop this technology, I'm going to build these pieces and it all works. Usually you have a hypothesis, you collect some data, it doesn't entirely agree with your hypothesis, so you design a new experiment, you run a new experiment to test your new hypothesis, and you eventually iterate to something interesting. So that is something that is an active field of machine learning research called active learning and design of experiments. That's kind of the classical statistics field. And that's something that we can absolutely use right now in our experiments, is some of this active learning. So you make some assumptions of what your model structure is, which is a hypothesis. You collect data, it doesn't necessarily agree. And so now you design experiments to maximally refute two equally valid hypotheses. And then you can kind of design experiments. That's what a human expert does. That's well within our grasp in machine learning, and it is a rapidly developing field. Yep.
Maybe I can have a question. You've shown a beautiful example in the case of turbulence modeling where physical ideas have been introduced in the neural network to do something where, let's say, humans could not, let's say, to overcome a limit where humans could not overcome. Now, yesterday we talked a lot about Koopman, which promises to linearize nonlinear dynamical systems, so possibly even Navier-Stokes, I don't know. But it's extremely hard to derive Koopman functions, so the autoencoders, which are nonlinear mappings, might do what we didn't manage to do. So my question for you, from a perspective point of view, do you think that they will change the Koopman framework or enable it for fluids, let's say?
Yeah, so I think that time delays and autoencoders are the most promising representations for Koopman theory in nonlinear systems that we've found. And I think it's not just us, others have also found this. So I think that's a highly kind of promising avenue of research, and it is something that probably scales to more complex systems. So autoencoders are likely to be able to handle more complex systems in that general framework. Now, I am starting to have some kind of philosophical questions about Koopman modeling and SIMD modeling and just dynamical systems modeling in general. So on the one hand, Koopman, you're putting in a tremendous upfront cost to find a coordinate transformation that makes everything simpler forever after. But that upfront cost might be tremendous to find that coordinate transformation. We spent a year optimizing our network for a pretty simple system. Okay, so that's really hard. You're spending all of your effort on coordinates so that your dynamics are simple. On the other side, on the SIMD side, we don't change our coordinates at all, and we're building this, fancy optimization to get the dynamics, which might be complicated. The coordinates are simple. I think there's a sweet spot in the middle, and this is kind of what Kathleen's SIMD autoencoder does, where you try to find a relatively simple coordinate transformation that doesn't linearize your dynamics, but it kills as many nonlinear terms as possible. It's like a sweet spot. And for those of you who remember normal form theory, this is how we tackle dynamic, that's how we understand bifurcations, is through the normal form. These near identity, simple transformations that sequentially kill nonlinear terms until all that's left is like the skeleton of the nonlinearity that you need. In my mind, that's what's going to happen. That's what we're doing. Yep.
Coming back to this question, whether you can extrapolate or not, is it the answer? I mean, I also wonder myself in the research I do, is the answer related to the fact that you made constrain a reduced order model more or less into a physical model, so that you can extrapolate and do science exploration with it?
Yeah, I think that your ability to extrapolate is strongly dependent on the assumptions you bake into your model. I think that's absolutely true. I feel much better extrapolating a model like a Galerkin model that has the physics in it than a neural network model. That's actually why we like these SIMD models, because when you only allow yourself to have the fewest terms required to describe the data, generally they generalize better because they're not overfit as much, but that's not always true. But yeah, in my experience, the structure of the model and the assumptions you put in and how much, if you bake in energy conservation, you can trust that model a lot more than if you don't. Yep.
Very interesting about your trying to optimize the energy from water turbine or water-based turbine, but actually, from my understanding from industry, the issue is actually the opposite. The issue is that they have very nasty gust response. And so the question is, have you also tried actually to do the reverse of what you've been trying to do?
To mitigate the
to basically
extremes.
limit the amount of torque which the machine experiences.
Yeah, so in a river, it's maybe a little bit less extreme. And in the applications that Ben was looking at, I think that's not necessarily as important as in wind applications. But so Ben's an exceptional engineer and designer, And immediately he saw that one of the problems in this accelerating turbine is that he needed basically like a beefier motor and gearbox. It was going to be more expensive to get those responses. And so he designed a coupled system so that the power stroke of one coincided with the low spot of another so that they could balance out the load in pairs. And he designed kind of a custom gearbox for that was really nice. He has a wind energy startup company with a colleague who graduated from Stanford. And they're thinking a lot more about kind of the more practical wind concerns. So they're definitely on it. Yeah, you can check out XFlow Energy. That's what it's called, right? Yep.
Other questions?
You said that there are certain problems, say for example, the spatially developing mixing layer, where if you train your model on only the initial few snapshots, it won't be able to predict what is happening further downstream. So, there are certain kind of turbulent flows in which you have invariants, in which the flow further downstream still remembers how it was generated upstream.
Sure.
So, whether these sort of information coupled along with the machine learning can help in regenerate things, like say for example you have Saffman invariants or something, and then you couple it along with the machine learning model and try to extrapolate.
Yeah, I think invariants are one of the absolute best ways of keeping your machine learning faithful to the physics. There was a really interesting, in the US Navy, there was a multidisciplinary university research initiative, a big research grant on trying to extract invariances from ocean flows to improve future prediction. I think this is a really, really great idea, that invariance or near invariance are extremely useful in modeling. Like those kind of pin our models. And I think the more we can learn about invariance, the better our models are going to be. Like absolutely, that's a good, and learning, this is a great idea. Like when you're driving down the road, I don't know if this happens to anyone else, but sometimes I wake up and I realize I've been spacing out for 5 minutes. Everyone's done that. And none of us have like driven off the road or we're still pretty safe. Why? Because we have an incredible sense of what is normal. And when something is not normal, you immediately put attention on it. You detect it and you focus attention. Our models should be doing that too. And there is an abstract concept of an invariance that goes beyond energy conservation and angular momentum. There are other invariants that we have not written down or given name to, and some of these architectures can start to uncover those invariants. Actually, the Koopman autoencoder network is an architecture we're using to discover invariants, because eigenfunctions with eigenvalue 0 are invariants. So yeah, I think it's a really interesting direction. Okay, everyone, we need to eat lunch. Yeah? Okay, one more question.
Yeah, I have something on the unrelated question to this. So you said that you can use the SINDI network to basically come up with equations using the flow field, and these are mostly trained for, say, dynamical systems. So now suppose if I have mostly, say for example, from a very engineering perspective, I have developed some experimental setups at, say, under very restricted conditions of, say, Reynolds number, Prandtl number. And now I want to scale up this problem to a more real-life configuration. So you have, say, for example, rocket engines which are developed in very scaled-down versions, and then you want to scale it up, and now you need some sort of scaling relationships, say, geometric scaling and, say, dynamic scaling, which helps us to scale up these engines. So whether the SINDI framework can help in sort of coming up with these scaling laws, since these scaling laws are mostly power law monomials and they are not.
So scaling in general is quite challenging. I think that when Bernd and I were talking about challenges for flow control, like industrial flow control, scaling to industrially relevant flows was one of the biggest challenges. And I think every method is going to have a challenge with that. In a lot of these algorithms, regression-based algorithms, SINDI algorithms, and so on, you can incorporate as one of your features a parameter that you measure that varies. So I can build that cylinder model with a Reynolds number parameter, but my library has to be expressive enough to understand how the Reynolds number comes into that model. And so you absolutely can do it for regions, but it's not obvious, how complex those functions are going to be.
So you can just keep on populating the matrix with as many
Yeah.
combination of Reynolds number, Prandtl number, and then different dimensional numbers that you can think, non-dimensional numbers
Yeah,
that
absolutely.
you can think of,
Um,
and then let Cindy figure out, say, some sort of scaling relationship.
That's exactly right. Yeah, so we're actually working on that right now.
I guess the scaling is not an easy issue there, no? If you increase too much the...
Not at all. I mean, that's a huge problem. I don't know how we're going to handle, and we can do it for small ranges of parameters, large ranges. I mean, Feynman said it. How would you ever predict, a thunderstorm from the Navy? Like, it's a hard problem.
Okay, so I propose to close. Thank you very
Thank
much,
you.
Professor Bratton. And we can go to lunch.
take a few photos of me? Sure.
You will log into my Chinese expense report.
Sure.
They want me photos which show me at work.
I think it's fair
And
enough.
then I ask them, what about my afternoon siesta? No, they want to see me teaching. Sorry.
Yeah, but I can sit here from here. I think
Okay.
I have better angle and take pictures.
Okay.
I put it here
But-
for the moment. Okay.
Okay,
You need
no,
to
no,
look
for-
for,
no, no
for a
problem.
kebab. But
Yes,
I
yes.
will. I will. I will. You have everything here.
So how does this one work? Like that?
Yes.
So, well, it has worked already once.
Duplicate?
Pardon?
C'est dupliqué?
Look here. So otherwise you would see this side.
I don't have signal.
But last time I had signal, so with the same configuration. So and there was a small trick. So what was the small trick? Maybe I have to log out and in again. I don't know. So maybe log out. Yes. Another trick is going out and then in. Oh, this looks promising. Okay, fine. Perfect. Thank you. No. Why do I thank you? I did it myself. I'm kidding.
I will sit here. Okay.
Yeah, of course, please. Okay. Go.
Call people first to make sure that everybody.
Okay. Does it work?
Wait, maybe because it's Tupac.
Oh, work. Are you sure?
No, it's okay. It was just off. It was off.
Okay, so I give you this back. What was off?
So if this.
Okay, fine. This is better, best solution.
Okay, so welcome back. We now move to Machine Learning for Reduced Order Modeling by Professor Noack. The floor is yours.
Thank you. So I would like to take a photo of the audience, or more precisely, a movie. Yeah. So I hope you have had a good lunch break. And this morning we have heard two really fantastic talks by Steve. Yes?
On this one. This is good. Try now.
1, 2, 3. No.
Maybe you have to take it this closer. You have to chew it. Try now.
Hello, everybody. No.
I think you not. It works.
Okay, it works.
Can you hear it?
So can you turn on the volume? Ah. Hello, everybody. Okay. Now it's the right echo. So, this morning we have heard these fantastic talks of Steve, and you can ask what I can possibly add to these nice talks about machine learning. So, attempt number 10. Clack. So the question is, what can I possibly add to these beautiful talks? And number 11. Can you hear me? Okay. Well, I will focus, I will try to present a spectrum from reduced order modeling starting from first principle, Navier-Stokes based, to purely data-driven. And there are a number of more things we can learn. And as mentioned already in my first talk, I would not be here without the phenomenal support of smart students and equally smart colleagues. The package which I'm going to present for the reduced order modeling has been developed together with Daniel Fernet and Richard Zeman. Guy is a mastermind of machine learning control, and Nang is a pioneer in deep mean field modeling. Arthur Elot did the locally linear embedding, and these Luc Pastor, François Lusserang, Navid Nayeri, Marek Mosinski, Steve Brunton, and Ulrika Kaiser, they are my senior colleagues who have opened me the eyes to many different directions, and we did very nice joint work. First, I will motivate why we need reduced order modeling. We have seen already a couple of examples. And then I will acquaint you with a method, proximity map. Who knows proximity maps of you? Okay, a few. So after this talk, it will be many more. And I think before doing anything else with your data, you should do proximity map, because they really tell you a lot about your data. If you have outliers or not, you can color and use them in many different directions. And then I will plunge more deeply in Gajokin modeling, Navier-Stokes-based Gajokin modeling, and present our programming package. Then I will give you a couple of examples of PUD models, more examples, and some critical enablers. Then I will continue what Steve has discussed this morning. Manifold models, 2 ways of arriving at these manifold models. And then I will end with cluster-based model, which is a purely data-driven model, so you do not need to know anything about the Navier-Stokes equation. This is something which you can fully automate. So this gives you a spectrum of reduced order models for different purposes. So why could we be interested in reduced order models? To some extent, this question has been answered by the previous speakers. I will add one perspective. So you could say that the reduced order model is kind of the glue between your theory, where you have equations which are which have limited validity, to your data. And so in the theory, you have understood a lot, but you have a very low accuracy. And if you look at your flow data, you can be very accurate, but you understand very little. And so these reduced order models kind of lifts your understanding by focusing on the gist. You can also take a computational view. So these may be the coherent sizes of the coherent structures which you want to resolve. So these are the finest structures, maybe the Kolmogorov vortices. These are the large-scale structures. If you want to resolve all of them, Navier-Stokes based, then you have to do a direct numerical simulation. And we know that this is extremely costly. And even when I'm walking here up and down, I create a von Karman vortex shading. It will be next to impossible to solve this numerically. So one simplification is you remove the small-scale structures and replace it with a model. The Smagorinsky model, and you assume that this transition is universal enough so that you can deal with one closure model. And you can go a step further and you can say, okay, I will take the unsteady runs equation. Your dynamic resolutions is now limited to something like an oscillatory flow. So it's very, very limited. And the reduced order models are somewhere in between. They resolve less than large eddy simulations, but they resolve significantly more than unsteady runs. Of course, you pay for this accuracy a price, and the price is that these are more configuration specific. And this is the range where you also want to do control design and optimization. At the moment, you do run simulation. Essentially, you believe the coherent structures are not interesting to you. You only want to know the mean flow here. So this is a computational perspective. Then there's another perspective, understanding. If you read Prandtl's paper, the fluid dynamicists at that time were very inspired by the Orr-Sommerfeld equation. And there was a hope that by understanding the instabilities of the flow, you can also learn something about the coherent structures, and you can also learn something about turbulence. And one of these passes have been mentioned by Steve this morning. One pass is the following. Of course, you know that the flow, the dynamics of the flow changes with the Reynolds number. If the Reynolds number is small enough, you have a steady flow. So you have a fixed point. At some point, at some critical Reynolds number, it becomes oscillatory. We have seen the cylinder wake already. Then this instability is called Hopf bifurcation. And one scenario which has been hypothesized by Landau and Hopf, 41 and 48, is that you find more and more of these Hopf bifurcations, in fact, infinitely many as you increase the Reynolds number, and turbulence can be understood as a sequence of infinitely many Hopf bifurcations, creating more and more frequency. So this looks very appealing, but this picture is wrong, because At some point, you have something like a cascade. So you have an activation of many frequencies. So at the moment, for instance, you have a vortex and you have a vortex filament deformation, you create turbulence. And this is not a bifurcation anymore. So nice scenario, good to have these smart people on board. But this was not a good theory. Then there were some theories in the 80s from chaos theory. So the question is, how can a limit cycle become unstable apart from exhibiting another Hopf bifurcation? You can have a period double Feigenbaum scenario or a period doubling scenario. These have been observed in a very narrow data range. And you end up with some chaotic flow, which might be described in similar spirit like the Lorentz equation, from which we have learned this morning. You can also have an intermittency scenario where essentially you create a larger and larger spikes. And this leads to the strange attractor. And you have also passes from the 2 torus and the 3 torus. That means from 2 oscillations and 3 oscillations. The problem with this, I would claim, the strange attractor has never been found in fluid mechanics. If you look at the correlation dimension, the people have always measured the length of their data. And fluid mechanics is the following. You have an orchestra with almost infinitely many players. And when there are some leading violinists, and everybody tunes in, and it's impossible to get them somewhat synchronized. So everybody adds stochastically now the flow. And if you look at the data, essentially you see it's much closer to a deterministic stochastic system than to a strange attractor. So these are dreams with a termination date. So it was the end of the 80s. But they have still inspired some approaches which turned out to be right. Now we go a bit engineering, and we want to do turbulence control. So with turbulence control, we need some actuators and some sensors. And the question is, of course, where do we place these actuators and sensors? What type of actuators should we use? Where do we place them? Which amplitude range should they have with frequency range? And so on. And you can ask the same thing for the sensing. For the sensing, it's easy. But if the actuation is wrong, you have lost. And now we do not have time for myriads of high-fidelity simulations. So one approach is typically you make, say, few well-chosen large eddy simulation, or you use a plant you truly believe in. And from there on, you try to distill some reduced order model. And the reduced order model allows you to explore new, better minima. And of course, at some point, you have to test them. So essentially, the reduced order models has less accuracy, but a broader range of operating conditions or control laws. And actually, this approach occasionally works. Now, the next question is, how should we characterize coherent structure? And Xavier did a wonderful talk on the first day. I will remind you how the vortex shedding behind the cylinder wake has been viewed. So here you look at a smoke visualization around a cylinder, and if you would not know anything about a Gajokin model, you would say, oh, there are vortices. There's a vortex here, which goes like that, another vortex here, and so on. So the vortexes move downstream. By the way, it's called von Karman vortex street, because von Karman has built the vortex model describing these shedding. So here you adopt a Lagrangian view. You say these coherent structures localized are important. You look at the vorticity and you characterize the vortices with maybe a Rankine vortex and some circulation. And the dynamics is described by Biot-Savart. So this is our vortex. Is a vortex model. So these vortex models are the models of the first hour, and hundreds of them have been constructed. They are very robust. We even use them in industry because of their robustness. But there are some disadvantages. The disadvantage is typically they are limited to 2 dimensions. For 3 dimensions, they essentially become CFD. Another approach is you look, for instance, at the V component here on this x-axis. So these two vortices, essentially, they create a downwash. This one creates an upwash. This one creates a downwash. So it does not create much fantasy to see that, oh, there's a traveling wave. It goes like that, 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 that. If you have a traveling wave, say cosine x minus t, you know you can write it as cosine x times cosine t minus sine x times sine t. So you have your space-dependent modes and your time-dependent mode amplitudes. And of course, you can generalize this concept by saying, okay, you have a modal expansions. We have seen this already. So this would be the Gajokin approximation of the flow. And then you have to find a way how to derive a dynamical system for these mode amplitudes, but the Navier-Stokes equation can help you in this respect. And of course, there are many other ways of characterizing coherent structures. We have seen the Lagrangian coherent structures. They don't lead to a dynamical model. There are also other dynamical models, but I do not want to give a complete review about this. Anybody knows another reduced order model than Gajokin and vortex model? Well, we have heard already one. Parabola stability equations. So here are some milestones of low-dimensional modeling or reduced order modeling. You can argue that it may have started with Leonardo da Vinci. He has pictured the vortices very nicely, and with most of his work, so 50% of the pictures were right and 50% of the pictures were wrong. Helmholtz has laid the foundation of vortex methods with his famous Helmholtz vortex laws. Gajokin has pioneered Gajokin methods, not in fluid mechanics, but for membranes. And then Lorentz essentially made us aware of that there could exist, that chaotic motion is something which we consider as generic. So that means if we have two states which are close, we should expect them to exponentially diverge. As you can see, the photos have become increasingly better over the last 500 years. Now we go to a tool which we are using essentially in every application, proximity map. And the main idea is very simple. So you have, say, you have your snapshot data. Maybe you have 10,000 snapshots, 1 billion grid points each, and you would like to see how much sense they make and how close they are. So what you are doing is you consider here your original snapshots in a high-dimensional state space, and they have a certain distance from each other. So it could be done measured with a Hilbert space norm or whatever. So they have a distance from each other, and you would like to project it in, let's say, a two-dimensional plane such that the distances are preserved. If you have only 3 snapshots, it can be done. It's very easy. If you have more, of course, you can only do this job approximately. These coordinates are called feature point, and they typically give a very good guidance on the proximity of your data, but they can, of course, also fool you. So here is the mathematics behind it. So the optimization is the following. You say, okay, try to find a mapping from the high-dimensional space to the low-dimensional space such that the error which you make, average error on the distances, is minimized. So these are the snapshots in the high-dimensional space. These are the feature vectors in the low-dimensional space. This is the distance between the M snapshot and the M snapshots. This is the same for the features vectors. What you want these two differences to be small, and in fact, you want the cumulative error to be minimized. So find a t that E is minimal, and this problem can be solved. It turns out if you don't add further constraints, then gamma 1 and gamma 2 are the first two POD modes. But typically, you would add more constraints, and then you would link your feature space also to your performance and other things. So what did I do? Well, the executive summary for professors is look in Wikipedia, and for students, apply a CMD scale in MATLAB, there are several degrees of freedom. So 1 degree of freedom is you can move the point in the feature space. What do? You center them so that the average is 0. There's also rotational degree of freedom. You can rotate the feature space as you want. So essentially, you make sure, like in PUD, that the largest fluctuation happens in gamma 1 and then gamma 2 and so on. And you have to live with mirror symmetry, so you can reflect the triangle or the configuration around some axis. So gamma 1 could be positive or negative. There's no way how to fix that. Again, like with PUD. Now I show you one example. And wake behind an Ahmed body, this is where you see UX. You see a lot of fine scale structure. What you don't see, there are also large scale structures. And here you have the feature coordinates. So each dot corresponds to 1 point of the simulation. Now we want to interpret this a bit. So what I did, or what we did in addition, we clustered the data, and we looked for every cluster. We looked at the drag. So this is the drag. This is the lift, and this is the side force. And when you look a bit closer, you see here on the left, the lift is negative, the side force is negative, and here the side force is positive, and here it's nearly neutral. Essentially, what we see here in gamma 1 is kind of the bistability of the flow. And the alpha 2 is related to some base flow variation of the flow. So this gives you one example of the proximity map, and we'll see others in the future. In this talk, you can also apply it to functions, to many other things. We apply it to controllers, as we have seen in my first talk. So now we go to the first real reduced order model, the PUD Gajokin method. And it started with Boris Gajokin. He was born 1871 in some small town. He was his family was poor, and so initially he struggled by being the writer in the court. And then at some point, his interest was always engineering and mathematics. At some point, he made his way to the technical university, and was also an engineer at the Kharkov locomotive industry. So in 2006, he was part in an anti-Tsar demonstration where a policeman got killed. And the Tsar was much nicer than Stalin, so he put him in a prison where he could work. So he says this was the most productive 1.5 years he had, where he got all the ideas for his future. So this could be considered as a Russian sabbatical. And then he had problems getting a job. But at the end, he entered at the Polytechnical Institute. 8 years later, he has published his book about his work about the Gajokin method. He became head of the faculty. He became corresponding member of the academic society. He became part of the academic society. So one of the 48 academicians top ranked in the US. And at some point, he has died a natural death, enjoying a lot of fame afterwards. So these methods have been used everywhere, so they are the basis of any CFD method. Lawrence was the first who suggested proper orthogonal decomposition in some report. Lumley has coined the word. It took them something like 20 years to get the first model, the first dynamic model of the fluid flow. What was interesting about that, this model was much more complex than any of the following model in the next couple of years. And when I taught reduced order modeling, I had to read this paper every time, again, 50 pages, condensed with a lot of valuable information. And you see there were few people who are really ahead of the time and have anticipated a lot of problems and have partially solved them in this model. And then there were a couple of activities using this for flow control. And here, an example of a Gajokin method. So we want to solve this equation. You know what it is, convection equation. Flow goes from left to right. And you have a boundary condition. So let's say it's periodic from 0 to 2 pi. We have an initial condition. Let's say it's cosine x. And of course, you do not know how this equation evolves, right? And now we make an ansatz. We say, okay, let's say maybe we can represent it with the first two Fourier modes and some mode amplitudes. But now we have a problem. So we have parameterized our solution in terms of two parameter, but we have a PDE. So the best we can hope for is that we can minimize an error, but not that we can actually solve the PDE. So what are we doing? So one method to do this is using the inner product, so projecting the residual of this equation on the two modes. So we need two equations for two unknowns, which are the mode amplitudes, and we take the underlying equation, so we project it here on U1, and you can see what happens. So first we see the residual, then we put in the solution in the residual, and at the end we get A1 dot equals minus A2, and we do the same with U2. We get A2 dot equals A1. So this is our Gajokin system. Our initial condition with cosine x is A1 equals 1, something like that. And this has a solution. The solution is A1 cosine t, A2 equals sine t. If you put these things together with cosine x minus t, so we are lucky, we get the exact solution of this convection equation. So this is this is the spirit of the Gajokin model, and we can embed it in a space portrait. Here we try to envision everything in terms of A1 and A2. The POD mode amplitudes, when we are on this point, we have the cosine. When we are on this point, we have the sine minus cosine, a minus sine. So I'm moving around. So as the wave travels from left to right, we are moving on a circle, and at some point we go to the initial part. Of course, when we go to the Navier-Stokes equation, we have a bit more work to do. We have to find an approximation here, and we have learned already one approach, POD. And we have to find a system, a Gajokin system for the Navier-Stokes equation, and this is what I'm going to derive. Now it's very simple. What you have to keep in mind, now our inner product is essentially the two velocity fields with an Euclidean inner product integrated over the domain. So standard inner product of L2. So first, we will first we compute the POD modes, and we take the average of the we take a basic mode as a mean flow. Does anybody of you have an idea why we do this? Well, it will become obvious in the next step. So now Scott has asked what is the request for the data. What we are doing a second order statistical order analysis of our flow data. So at minimum, the first moments must be right, and the second moment must be right. And just as a reminder, if you have the cross correlation between u prime, the fluctuation at x and y, this can be expanded like this. So this is a simple representation in the POD modes. So the next step, what we are doing, we are building the correlation matrix. So here you see we take this M snapshot, we subtract the mean, and the N snapshot, and we subtract the mean, and we divide by M. So this is our correlation matrix, just a volume integral, not very difficult. And I want to emphasize we are subtracting here U0. And I see a lot of publications where this has not been done. The price which you pay if you do not look at the fluctuation, but if you take the whole velocity field, is large. So number one, your first POD mode is likely to be something like a mean flow. Number two, the fluctuation now has to be orthogonal to the mean flow. This is not what you typically have. In a second. And the convergence of the POD mode is not guaranteed. The lambda I cannot be interpreted as variances anymore. The POD approximation does not fulfill the boundary condition for any AI. So and now you have to make an extra constraint on the mode amplitudes. The POD model is not physical. For instance, if you do the Gajokin projection, then you suddenly have a varying oncoming velocity in your dynamical system. So this is a real screw up and misuse of the approach. So all the beauty of the POD modeling is lost if you do not subtract U0 in your expansion and in the fluctuation. So the next step, what you are doing is very easy. You solve the Fredholm equation. So essentially, you look at the, you do a spectral analysis of your correlation matrix. You get a couple of vectors. This C is positive semi-definite, so the eigenvalues have to be all larger or equal to 0. The modes have to be orthogonal. And so you have a real non-negative spectrum. You had a question?
Yeah, my question is about the mean subtraction. If you have a stationary flow, of course, but if your flow is not stationary and so your mean is not converged, what is your point of view about that?
Good point. The question, there's another reason why you should remove it. And the assumption which I make was that we have stationary boundary conditions. For instance, you have a cylinder wake, you have the no-slip condition on the cylinder, and you have uniform flow at infinity or far away. So the mean flow now takes away the uniform flow condition. And the remainder, U prime, satisfies the homogeneous Dirichlet condition. And if U prime satisfies the homogeneous Dirichlet condition, that means all the fluctuation must fulfill it. That means the POD mode must fulfill it. And now you can, in the expansion, you can choose the POD mode amplitudes arbitrary. And that's what you want. You want a Gajokin system without constraints. So this is what you have to do to arrive at this point. Good. So now you have the eigenmodes, and essentially what the POD mode is, the POD mode is nothing but a linear combination of your snapshots done in a smart way. And of course, the more snapshots you have to rescale it somehow, and you remove some of the fluctuation intensity in the direction. So at the end, you have also normal modes. And you can check this also by looking at the trace. So that the sum of the trace of the correlation matrix should be the sum of the eigenvalues, should be the average fluctuation energy in the flow. So these are the POD modes. And now you have the AIs. And these are the amplitudes, again, are somewhat proportional to the modes. So if we have, again, a couple of properties, so the POD modes can be obtained by projecting the fluctuation on UI. The average should be 0, and the second moment should be centered. So you have not only also normality in space, you have also orthogonality in the frequency, in the POD mode domain. Good. Now we go one step further. So what can we do having this fluctuation? We can get a lot of inspiration when we look at Munin-Yaglom. And so all the equations which you see there, where you have the flow decomposed in a mean flow and a fluctuation, can be written much more accurately in terms of a POD mode basis. So we start now with a Reynolds decomposition. I will remind you of an equation which you should know from the from fluid mechanics. The Navier-Stokes equation is written like this. The Reynolds equation is essentially the residual with the Reynolds decomposition equals to 0. A weak formulation means you take the residual and you can multiply it with any test function, and you should get 0. Why is this effort? Well, you can include, for instance, now shocks in your solutions. And if you multiply the residual with U prime, then you get an interesting equation. You get the equation of fluctuation energy. And here you see the Navier-Stokes equation. It can be expanded with a Reynolds decomposition. Now it looks something like that. So it always has some constant and linear quadratic terms here, a constant and linear terms here. If you average them, these are the survivors here. So this is the Reynolds equation. If you now subtract the Reynolds equation from the Navier-Stokes equation, you get an equation for the fluctuation energy. If you multiply this now with u prime, you get these volume integrals. So this essentially is your production term. So this leads to the production term. This leads to the convection term. This leads to the transfer term. This leads to the dissipation. And this leads to the pressure power. So just a reminder of your Navier-Stokes of fluid mechanics lecture. Now we can do the same thing with the modes. Here's a picture, the fluctuation. There's one term called production. So this essentially determines how much energy the fluctuation gets from the mean flow. There's one term called dissipation. This is how much energy the heat reservoir or the molecular structures get from the coherent structure. And there are two terms which are determined by the boundary. One is the pressure power and one is the convection. So in an infinite domain, a periodic pipe and so on, these terms would vanish. And now you can do the same thing also with, you can do the same thing mode-wise, but what you have to do now, you have to expand u prime in terms of the Gajokin expansion. Instead of projecting this residual on u prime for the global energy balance, you project it on AIUI. And what you see immediately from the structure, if I'm adding up all these contributions here, then this becomes u prime. And essentially, this gives a basis why we interpret this as a modal energy flow balance. There's another equation which is vital. If you project it on UI, we again get the Gajokin system. And as seen in my last lecture, the Gajokin system has some linear term, it has some quadratic term, and it also has some pressure related term. Just, you can make many more variations with this. For instance, you can, in principle, project the residual on EX, the unit vector in X direction, and this gives you the equation for the drag. So now you are capable of explaining the drag in terms of your Gajokin expansion, or you can multiply it with EY, then you can interpret the lift, you can look at the Reynolds stress term, and so on. So there's a lot of equations which you can derive just with this simple ansatz. Here I want to focus just on the modal energy analysis. We do again the analysis here and here. The Gajokin system looks like that. And if we multiply with AIUI, we get these terms using all the PUD properties. So there's one term left over, this one here, which leads to the production. There's another term from the Gajokin system times the energy leading to the convection term. There's a irreducible term, essentially this is the essence of turbulence, which leads to the transfer term, and dissipative term, and some other terms. You see that the modal production, convection, and dissipation scale are proportional to the fluctuation energy in each of the modes, and the Gajokin system essentially determines something like the gain, and these nonlinear terms are the one which are the troublemaker. The picture which now emerges is the following. So you have the different modes here. There are some terms, essentially they get some energy from the mean flow, lose it to the dissipation, they lose it at the boundary. The most important thing is the transfer term. If you remove the transfer term, the nonlinearity, maybe the first mode will explode. The modes will either explode or they will decay. You have no sociology. So you need the nonlinearity in order to have this sociology. And here this is just the remainder that the averaged global energy flows are the sum of the modal flows, and they all should add up to zero. And so this is the recipe now. So you have something like M snapshots. You have to write routines essentially for these three things, for an inner product, for a trilinear form from the convective term, a bilinear form which comes from the dissipative term, and maybe you want to consider the pressure power as well, then you need the surface integral. Compute the mean flow, compute the correlation matrix, determine the spectral analysis, compute the POD modes, compute the Fourier coefficients. You see these operations are very simple, and if I show you my Fortran code, it's only something like 3 pages long. So as an augmentation, you can look at the dynamics. So this is your dynamical system after the Gajokin projection. You can perform a modal analysis for each of the mode, and the modal analysis will tell you, for instance, what is anything is missing in your in your approach. For instance, you can see from Fi if you should include the pressure term. You can see from the difference to 0 if you should add some stabilizing terms and so on. Any questions so far? Oh. You have to choose. So again, hands up. I will try to start from here.
Questions?
No. Good. So I've shown you now a procedure which I think most of you can program easily yourself, say on one weekend. Does it typically work or not? Well, there are a couple of things which you should keep in mind. There are some things which make your which you may have to add to stabilize your Gajokin system. The first thing is maybe you are missing some modes in the POD which are stabilizing. So in my first lecture, I've shown the shift mode. If you don't add the shift mode to the POD Gajokin model, it will be inherently fragile and potentially robust. So the shift mode is one possibility. Essentially, this is a difference from the steady solution to the mean flow. Now there's another aspect which Steve has mentioned. You can derive from the Navier-Stokes equation, from most boundary condition, that the quadratic term should be energy conserving. And that said, it's energy conserving if the contribution at every instant to the whole fluctuation energy is 0. And you can show that this coincides with another condition. So you can decompose the Qijk, so the 3 tensor, in one quantity, which is the average, and another quantity, which is the remainder. So you need to remove this part, because you will always have some numerical error to be Navier-Stokes consistent. This is the remaining part. And this often stabilizes an otherwise unstable Gajokin system. Because the further you go with your mode number, the smaller structures you have, the larger the numerical error, and at some point you will inevitably get noise.
I have a question concerning the shift mode. In case you have a transient problem, for example, is it to be meant in terms of simply low frequency, or is it to be meant in terms of ensemble averaging? And if it is in the first case, how do you choose how low is low frequency?
Good question. Now, we've written one paper where we showed 4 different definitions of the shift mode. And for instance, you can say it's the difference between the steady solution and the mean flow. Nice. You can say the shift mode is the one which you derive from the Reynolds equation. So essentially, you look at the linearized Reynolds equation and look at the fluctuation. So in which direction would you go based on the Reynolds stress? This would be another way. Another possibility is you take away the fluctuation and you look what remains. So now your shift mode is the first POD mode of the low frequency remainder. You can also take the one frequency average. So it's left to your engineering ingenuity. And there are many possible choices, but most of them lead to Rome. And even the first model, the model of Nadine Aubry, has included something like the shift mode. So essentially, she has always recomputed the mean flow, the base flow, as a function of the fluctuation which she has resolved. So you had the cubic terms explicitly in her approach. Good. Now there's something which may be a little less known. You can look at your Gajokin system, and without any integration, you can say you have a necessary and sufficient condition if all your solutions are globally bounded. Of course, we agree, this is desirable, right? You don't want to go to infinity, because the further you go away from the origin, the less physical your model will become. So there is a condition for boundedness, which has been derived by Michael Schlegel. And I can tell you the essence of the criterion. It's really analytically very beautiful. So a sufficient condition is the following. If you find one point in the state space where the linearized Navier-Stokes equation, the linearized Gajokin system is stable, then it guarantees boundedness. So there's a very easy way to test the sufficient path, and the necessary path is difficult to prove, so I could not have done it. Another point, we can also play with a nonlinear model eddy viscosity, which I will introduce later, and under some conditions it also guarantees boundedness. And if you want to know any more tricks, there's an expert in the front row. There are many more tricks which could be useful. And now we go to get our hands a bit dirty with a small tutorial, XROM. So at some point it was called XAMC, but it has been completely rewritten. So you go the standard path of the Gajokin system. You include some additional calibration, which includes something like a modal eddy viscosity, and it scales with the fluctuation. It has to scale with the fluctuation energy. There are strong arguments for that. So this system has many features for large volume data processing and flows, most common in grids, parallelizable, and so on. So if you want to have more than, say, 100 2D snapshots, but have a high volume, this may be a path you may want to go. And of course, there's a documentation around it. And now I want to show it to you. So now I can't show it to you anymore. No, I'm kidding. so here's the package. You have to unzip it. You find the link on the chapter. So you see something has been unloaded. There's something which is a package. I'm a bit excited. So I've tried it something like 10 times, and I was successful in half of the times. So now the program has become an executable, and now I let it run, and probably now it needs something like 2 minutes. So Daniel has written such a good wrapper around it that I get scared of my former code. So here, essentially, you have to click what you want. So this is here. Now you have computed the PUD. Cool, isn't it? We can go a bit further. And so here you find a configuration file. So now I say I get ambitious. I say, okay, we have the Gajokin expansion. I also want to get the dynamical system. And to save a bit time, I also include where is it? Why can't I go lower? Ah, here it is. Good. So my kids don't allow me to use a computer anymore, so I'm a bit struggling. One of Steve Brunton's postdocs asked me, Jibai, with which software do you solve your scientific problems? And I explained to her, email. There's an upgrade to this. So there was a Nobel Prize winner who was cloning one of the sheeps. And he was asked how he does his work, and he says he does cloning by phoning. So the next level is you use your cell phone. Of course, you need a good database, an address database, over there. The same data which almost everybody is approximately using. Good question. It's a cylinder wake data for one period. So now we need to wait a bit, maybe 1 more minute, and then I can show you what we have computed.
To summarize a bit what the code is doing, so you're computing the POD modes from a set of snapshots of a.
Yes. I just have the snapshot, okay. Nothing pre-computed.
Then you create your dynamical system.
Then you compute the POD, and after the POD you compute the dynamical system. Then you integrate the dynamical system, and then you also use calibration for the eddy viscosities.
So you produce more snapshots using the projected dynamical system, or
not more? Well, you'd use the same snapshot. I will explain the modal eddy viscosities in a second. Good. So what do you want to see? This is input data. This is not interesting. Let's look. Output data, run 1. So we managed to do it in one attempt. That's good. We have the Gajokin expansion. POD mode amplitudes. So what you see here, essentially you see the mode amplitudes. So this answers your question regarding the input. And there should be, oh, asked me to do something. Good. So now we also have the POD mode spectrum. So you see the energy, first mode, second mode, and so on. So it rapidly decays. Very simple flow. You can go to the dynamical system, and let's look what we have. So what we essentially have here, we have dynamicals. Initial is a Gajokin system, and then what the dynamical system gives us. 1, 2, 3. So you see that there's some small deviation with the higher order modes, but it's reasonably well. So this went much better than I expected. Do you have any questions? Okay, you can try it yourself. So it's a really fast code. You can use multiple meshes. And so if you have heavy volume of data, it could be interesting in the add-ons like clustering, CROM, and so on. Good. Yes?
I'm not really sure if I understood correctly, but just tell me if I'm right. What you're basically doing is start from a database, you build your POD modes,
yes.
And then you, instead of finding the evolution of the coefficients versus time projecting on the pod modes, you integrate over the pod modes and you compare with the actual solution.
First principle, you ask the Navier-Stokes equation for the dynamical system.
Okay.
Yes. So this is not data-driven approach. This is
exactly. That's what I want.
Navier-Stokes driven approach.
Okay, very good. Thank you.
Good. So essentially, this does what I've been teaching. So I will skip these POD slides. So now we will see some examples, and we are all a fan of the cylinder wake. It's so easy. I've explained these modes already in my first talks, and we've seen them many more times. So essentially, the first pair, first harmonics, second harmonics, third harmonics, fourth harmonics, with rapidly decreasing energy. The Gajokin model works very much like Charm for one operating condition. And we can learn a bit about it. If we purify our Gajokin system and we take away non-linear terms which have a small value, then we get something like a coupled dynamical system, which looks something like that. So first harmonics, second harmonics, and so on. We also have a quadratic term, which is shown here. And now, if without a linearity, this one would explode, so the growth rate is positive, and this one would decay. So you need a social welfare system. And this is communicated by our transfer term. If you multiply this with A1 and average, you get the fluctuation energy here and the modal transfer term here. So you get these equations. You see, in order to keep these modes alive, the transfer must have the opposite sign. And the sum of the transfer term is 0. So you get as much energy out as you invest in it. So you have harmonically related oscillators with this growth rate sequence, and the quadratic coupling is energy preserving. Again, energy preservation of the quadratic term. This is another picture how to show it. Here you see the fluctuation energy again as a logarithm. First pair, second pair, third and fourth pair. These are the corresponding frequencies. These are the growth rates of each of the oscillators. So what the linear interactions, so production and dissipations do, they feed the first one and they dissipate the other modes, but the social welfare system essentially takes care that they all stay alive. And there's one aspect which is very troubling. So this sigma is something like 0.007. So we have seen already identified growth rates which are of the order of 0.1. So we are missing more than one order of magnitude in the growth rate. And this shows how fragile these Gajokin models are if they do not have additional stabilizers. Next thing, here we see the modal energy. First mode, second mode, this is the production. So they take energy out of the mean flow. The other modes are negligible. The dissipation also happens in the mean flow, but also in the other mode, convective term, so a lot of energy leaves the domain. And the transfer term essentially takes energy from the rich and feeds it to the poor. And there's some residual term of the pressure. And there's another way how to plot it. You can now take the production and divide it by the energy. You get something like the energy efficiency. So if you give a mode a certain amount of energy, how much energy does it extract from the mean flow and how much does it loses? So the energy efficiency here are plotted here, all get energy. The first from von Karman vortex shedding, these here from the shear layer structures. But now you see something interesting. The dissipative, the higher order modes are very good in dissipating their money, while the transfer term essentially gives them essentially the money. The convection term has little effect, and the pressure also has little effect. Essentially here we see the Kolmogorov cascade already in a periodic flow. Now we look at another flow. Shear layer ratio, velocity ratio 3:1. Essentially what Steve has shown in this morning, but a much smaller domain. These are the streamlines of the fluctuation. You do a POD, first mode, second mode, first harmonics, second harmonics. This should not surprise us anymore. When we do the energy, when we do the Gajokin system and ignore the pressure term, essentially we get this limit cycle here for the DNS, and this is the limit cycle for the pressure term. So we are far off. And when we add the pressure term, we are again on the limit cycle. So here we need to include the pressure term. So just some warning for the practitioners. Now you can ask, why is the pressure term so important? Well, You look at the total balance. You have a production and convection. This is something like what remains now is something like 80%. And so 10% are dissipated and 10% are lost by the pressure term. So the pressure term is as dissipative as viscosity. And this is a laminar flow. And this is why we would not sacrifice the dissipation term. And hence we shouldn't also not omit the pressure term. This is a energy flow a diagram, mode number 1 and 2, now combined to 3. So they get all the energy from the production. Then they lose around 10% by dissipation, 10% by pressure work, 80% by the convection and transfer. This mode is only kept alive by the energy from the first pair, and most of this gets convected and only part of that gets dissipated. So these diagrams can be rather revealing in terms of the energy flow. Now, not all the flows which we have can be fully resolved. If you have any turbulent flow, you will be lucky if you can resolve something like 50% of the fluctuation energy. So maybe you can only resolve 30% of the fluctuation energy. So you have your Gajokian expansion, and there's a residual, and you know the residual is significant, but you would like to account for it anyhow. How can you possibly do it? Well, there's a solution to that, the busyness approximation. So essentially, you use that the stochastic fluctuations take energy out of the resolved modes. How can you describe it? Well, you can describe it with an additional eddy viscosity here in the linear term. So the picture which is emerging is the following. We have some modes living from the mean flow. They don't dissipate anymore. They lose everything to the transfer term. You have some dissipative modes which you don't want to resolve, and this dissipation is modeled by this eddy viscosity here. So using a modal instead of a global eddy viscosity has been suggested by Dietmar Rempfer. You look skeptical? No. Okay, good. So here we have a large eddy simulation. Flow left to right. Here we see the V component. Of course, some Kelvin-Helmholtz structures. We see a bit of vortex pairing, large eddy simulation ratio against 1 to 3. So this was a particular LES where the Reynolds number is effectively infinite. And you see some irregularities. PUD mode amplitudes. The first two modes essentially describe the Kelvin Helmholtz structures. The next two modes describe the vortex pairing. Here you see this structure becomes this structure, becomes this structure, becomes this. So you can imagine if you are moving around, you are describing a vortex pairing. And these are the PUD mode energies are plotted here. And of course, you can plot more and more. At some point, you get a continuous spectrum. So again, what has been outlined earlier. So what we are doing now, we do the energy flow analysis. And now we try to keep track how much energy, excess energy, do we have in each of the modes, or not excess energy. And we compensate this by having an eddy viscosity, which takes into account that the modal energy balance should be 0. So this is a simple trick. So essentially, we derive our modal eddy viscosity from our original data, and then we get already pretty good agreement between, for instance, the first PUD mode amplitude in the LES and the first PUD mode amplitude in the Gajokian system. And I could show much more, but this shall suffice shall suffice. So my focus on this talk is automated methods, which typically work. There's another example of, I would call it a deep mean field modeling of the fluidic pinball, which Nang Deng has derived. Now we see one reduced order model which encaptures 3 different steady states, 3 different periodic solutions, all the transitions between them. And you see this is a type of models you can not automate for a certain period of time, and you can ask none and go to his a poster. Just a small disclaimer. There are some things, when the model become really beautiful, there is always some thought process behind it. Now we go to another way of presenting our data, locally linear embedding. I've briefly reported it in my first lecture. So it's a way of mapping all the high-dimensional data to a low-dimensional manifold and the way back. I've shown these results already in my first lecture. So steady solution, limit cycle, and here you see the transients are going outwards. And you can go backwards from the from these feature vectors to the original flow, and you have something like a 1% of representation error maximum. Now, if you do this locally linear embedding, you assume already you have your flow structures, and you did CFD. Now I will present you an example where we derive something similar for experimental conditions. And in experimental conditions, we have some data. Typically, the flow structures are not time resolved. There are some ensemble, but we may have some sensor signals like the lift being time resolved. And now we have to find something like a feature. So something, we have to lift this sensor signal so that there are no false neighbors. So if you look at neighboring states, they evolve according to the same dynamics. So if you have, for instance, a cosine t is indicative of an oscillatory dynamics. Now you look at the time delay, you have cosine t and sine t, and suddenly you can plot things in a two-dimensional state space diagram, and you can build a dynamical system. And the dynamical system is shown here. So you build your dynamical system with your sensor signal, but you use essentially the PIV data first to get a mapping from your feature vector to the flow. So this is our feature-based manifold. And then you do the reduced order model, which have been beautifully introduced this morning. In principle, you can also get POD mode amplitudes. Here we see again the lift coefficient and our phase portrait. So essentially the derivative is our way of lifting it. You see the trajectory has no crossing points, so we can fit a dynamical system here. At this point, we see in the vorticity fluctuation feed this structure, and then at this point, this structure here. So you see the structures change. This should not surprise us from my first lecture. And with Steve's SINDI, we arrive at a very simple dynamical system, which Steve has already presented. So essentially, it's something like a van der Pol oscillator, which describes our dynamics here in this plane. So now we have a system, dynamical system, for our feature vector, and we can do the mapping from the features to the velocity field. And the mapping, we simply do k nearest neighbors, and this is as accurate as you can possibly imagine. And in addition, you can derive some modes, which are as good as the POD modes. So here again, structures for different times in the numerical simulation, locally linear embedding. It's perfect, so our estimator is wonderful. If you do a Gajerkin expansion, you lose a lot. So essentially, this looks much more than the high amplitude states. So this is clearly wrong, and this becomes right. If you look at the residual, now we look at the residual and normalize it with the fluctuation energy over one period. So at the end, our local linear embedding gets things wonderfully right. Even with 25 POD modes, so the red curve here, we are far worse. We are more than 3 orders of magnitude worse. And at the beginning, for instance, POD is completely wrong. You make something like a 20, or here you make a 50% error with 5 POD modes. And locally linear embedding always outperforms our POD modes and some other modes which I don't want to discuss. So at the end, after 30 years of research, the solution of reduced order modeling is very easy. You determine your feature space. Then you make k nearest neighbors from your feature space to your snapshot data. And if you want to know the dynamical system, very easy. You look at the evolution of your data and reproject it in your feature space. You have a dynamical system here, and then you do k nearest neighbors on the evolution in your feature space. So 2 times effectively linear interpolation solves the reduced order modeling problems. This is as cheap as it can possibly get. And if this approach does not work, something is wrong with your data, or something is wrong with your model identification approach, or you have inserted a lot of prior knowledge. So now we go to another model, cluster-based model. So this is fully automated. And I want to give you now an appetizer. Okay, I know the problem. So let me. Has anybody an idea what this flow is? Well, turbulent boundary layer. We have seen already the nice simulation of a turbulent boundary layer of a Philipp Schlatter. This is a simulation of the Aachen group. The flow is in this direction, in X direction. You see essentially the omega isosurfaces of the omega structures color-coded with U. So a lot of these hairpin vortices or half-hairpin vortices and so on. And you want to have a drag mitigation by a traveling wave. So the surface is shaking. You get up to something like 31% drag reduction just with this mechanism. And in our project, we have promised a reduced order model for that. So in the proposal, we have said we want to do a reduced order model like POD. And our reviewer have said, we don't see how it can possibly work, but we give them the benefit of the doubt. These are leading experts. And of course, we knew that this approach would not work. So what could be a good reduced order model for this turbulent boundary layer? So to see the actuation effect. I will show you now a really beautiful brute force model. So what you are doing, as you take your original data. You take your original data, you cluster it. As a number of clusters, you count the number of fingers on your hand. Then you have 10. This is the engineering approximation of infinity. Now you have an infinite number of clusters, and you put your snapshots into the corresponding bins. And so every bin has, for instance, some POD mode amplitudes. We see, for instance, here A1, A2, A3. And so every core switch you see here corresponds to the centroid, the average of the representative state of the clustering. And our dynamical system, we look in our dynamical. So we look in our simulation and we figure out what is the probability going from one centroid to another centroid. You see it here. And what is the average time going from one centroid to the other centroid? And this is our very simple reduced order model of the flow. And we cannot fail because we always stay close to the data. And we have no problems with eddy viscosity or anything like that. This is the purest data-driven approach, which can be fully automated, and you can never leave your domain. And you can also include other actuated states and so on. So, of course, I can now elaborate on the equations which we are using and so on. I would like to focus more on the method of clustering, because this will become more useful to most of you. So now I continue. Why is this close? What about this? Yes. So now I continue. I'm using now slides which Ulrika Kaiser has prepared with an alternative strategy of reduced order modeling. So if you look, for instance, at the mixing layer here, what we do, this is a feature, it's a feature plane of the mixing layer. So you find we are moving around, then we are moving here, moving around, and so on. So in one two-dimensional plane, we now see the dynamics. We don't need to do anything but doing the feature plane and looking at our original data. For instance, if we can immediately see bimodality. So here we would start here, then we could go here, and then we got here. So we get, from this simple proximity map, we can get a pretty good idea of the qualitative dynamics. So what we are doing here, we take the mixing layer snapshots, we cluster it in infinite number of centroids, representative states, and then we build a dynamical system. And let's first do the cluster analysis. If I ask you, what is the number of clusters here in this plane? What would you answer? 3, yes. So this is obvious to the eye, but now the question is, how do you teach your computer, and how do you arrive at this if you cannot look at your data? So there's one algorithm which is very beautiful, k-means. So what you say, you start with a guess of your number of representative states. I will call them now centroids or clusters. So these are 3 centroids. And of course, it's a very stupid choice. So you say these are the representative states. In the next step, you look at the points which are closest to this centroid. So these are the yellow ones. To this one, these are the blue ones. To that one, these are the magenta one. And now you take the average of yellow, average of blue, average of magenta, and you get new centroids. Of course, they look better. And you iterate this until it converges. So at some point, you will have the centroids here, and now these look as reasonable representative states. So this is a k-means algorithm, which I find very beautiful. And what we hope to have solved, an optimization problem. We want to minimize the average representation error with respect to the data. So if you have a snapshot, and this is the corresponding centroid, then this is the error squared, and we sum up all the errors over all the snapshots. So what we would like now, we would like to determine the centroids in order to minimize this error. So it's a bit like PODs. In POD, you have you also want to minimize the representation error in a statistical average sense.
In this case, you said to the algorithm that you had 3 clusters, right?
Yes.
And so the barycenter would be such that if you tell that you have 4,
yes,
what will happen?
Good question. I would assume you will resolve the other one better. You will resolve the lower one slightly better.
And if you say that you have 10?
Well, then we probably have maybe 6, maybe 5 and the lower one, and then 2 and 3. Of course, the number of clusters. Now the question is, how do you determine the number of clusters? And there's a sweet spot. The sweet spot is the following. If you say, if I really want to be sure that I determine that my dynamic model, which I built on top of the clusters, is always right, then I say, okay, I take 1 cluster. Then I know I will always be in cluster 1, cluster 1, cluster 1, cluster 1. So any dynamical model which I make will be infinitely accurate and 100% boring, but the error which I make will be as large as the diameter of my data. Now I can say I'm not smarter. I take as many clusters as I have snapshots. So suddenly I have 2,000 centroids. To some extent, I have no compression. And now I have another problem. I know already I go from snapshot 1 to snapshot 2 to snapshot 3. Keyword companion matrix. And at some point, I have to decide what I will do with after the last one. I do not know how I return. So the problem which I have now, the transition matrix, which I would determine now with this maximum number of centroids, would have an extremely large error. So it's only 0 and 1, and we know already if I would have new data, I know already that the transition matrix would have values maybe between somewhere between 0 and 1. So if you do a cross-validation, you get a sweet spot of the error which you are making with your, say, dynamic model. So not the representation error, but essentially the error in your temporal evolution.
Suppose you have 2,000 snapshots, and as you were saying in your example, you choose, let's say, 1,000 clusters.
Yes.
How does the result will differ with respect to a moving average filter with the kernel of size 2? you're just going to take the mean between snapshot 1 and 2 probably, because the 1 and 2 are the closest one.
Yes.
And then maybe the average between 3 and 4 and 5 and 6.
There's no concept of a moving window here. I mean, this is ergodic. You do not know when the snapshots were taken. So it's like POD. So the order of the snapshots does not matter.
So I guess that the main difference is that while in the moving average you're assuming causality between one and the next, here maybe it can be that the snapshot 5 is very similar to snapshot 900.
There are two things. One thing is a in-sample representation error, which of course increases. Then there's an out-of-sample representation error. So this is the error which you get with cross-validation. For instance, you take 1,000 snapshots to determine the centroids, and then you have another 1,000 snapshot where you determine essentially the error of your representation. Of course, the out-of-sample error must be larger than the in-sample error, but at the end, what you really want to do, you want to have a dynamical model representing your future. So it's essentially the uncertainty of the error which your dynamical model makes in the future. This is a critical thing, and this could be measured, for instance, with an autocorrelation function. I will not go too much in the deep, but there are methods for determining the optimal. There must be a sweet spot. This is clear, and there are methods to determine the sweet spot. Good. So this is it. These are our 3 centroids. Note, centroids, they are the average of the corresponding snapshots. So essentially you can say cluster analysis puts the snapshots into bins. You can also say you have a Voronoi diagram. So you have a decomposition of your state space into different regions. So clustering could mean a centroid, putting things in bin, or having different regions. If you want to do it if you want to use it for other data, for new data, of course, the region is the only relevant, because this can be generalized to new data. Good. So now we go to the mixing layer. These are the feature points of the centroids. You see the one centroid here. These are the snapshots in the corresponding clusters. There are some which are very close to the centroids and some which are reasonably far, but essentially they represent similar states. Then you can look at the transition. So we have a stroboscopic view. We go always a fixed time step further. So when we need to identify something like a transition matrix. The transition matrix tells us the probability if you are on stage in cluster 1, what is the probability to go to 2, 3, and so on. And I will show you how to do this. This is a simple counting. Let's assume we have the clusters 1, 2, and 3, and these are our data points, and we have time resolved our data points. So what is the probability to go from cluster 1 to 2? So 1, 2. Well, you take the number of points here, so 1, 2, 3, 4, 5, 6, and 3 of them go in this direction, so your probability is 3, 6, right? Very, very sophisticated. And what is the probability to stay in the cluster? Okay, there are 2 who do not move, so this is 1. What is the probability to go from 3 from 1 to 3? It's this. So very simple. This is our transition matrix model. We can plot now the probabilities. Our time step has been small, so with a large probability we stay in the first cluster, so, and second, and so on. But say we start with the second, there's a large probability that we go to the third. In the third, there's a large probability to go to the fourth. In the fourth, we go back, so it's second. So here's a limit cycle. And here's also a limit cycle. And how can we leave these 2 limit cycles? Well, if we are here, we can go to with some probability to cluster 1 again, and then we are here. If we are here, we can go with some probability to cluster 1 again, and then we are here. If you are on 1, we can go back to the large limit cycle or to the small limit cycle. So we see a structure in our data, which we may have missed otherwise. We find the same also for the Ahmed body. So 2 oscillatory cluster groups. This is what we call flipper cluster, because this decides if you go right or left. If you have seen the Lorentz system, once you go to the intersection of the 2 ears, you can also go right and left. And if you want to do control and you're like this limit cycle, you have to look when you are getting close to your to your 8 centroids, because you don't want to go from here to 1 to here, because you would like to stay here. So you have to find a control strategy which avoids this transition. So it guides you also in your transition. So this is the corresponding dynamics. There are 2 modes, 3 centroids which represent high frequency Kelvin-Helmholtz structures, 6 which represent vortex pairing, 1 which is a flipper cluster. Here are the corresponding modes. You see high frequency states which are convecting in that direction. So essentially you have a phase average here, and you have a phase average here with larger scale energy, and you have the flipper cluster somewhere in the middle. So you now know which game the data is doing. So this is our cluster-based reduced order modeling, distilling this the corresponding dynamics. And I could have added several other things where we got some interesting insights which we would have missed otherwise. So I know I'm a bit over time, but I inquired advance permission. That's why I've answered already a number of your questions. And to summarize, so what did we learn? We learned that reduced order models can be very useful for multiple purposes. Proximity map is a very cool strategy which you should with which you should visualize all your data. Suddenly outlier detection, dynamics detection, and so on becomes so easy with it, and you can mold it in many forms. For instance, if you have a simulation, an LES simulation and experimental data, an experimental evolution, so you have 2 trajectories, 2 attractors, how would you compare those? So if you look in our literature, so clustering allows you to have a pretty objective comparison of 2 different attractors in terms of their overlap and their corresponding dynamics. So I've elaborated the POD Gajokin method and have introduced one of our codes. I've shown a couple of examples. Our most complex POD model was for the Ahmed body weight, where we needed something like 100 modes to resolve very low frequency dynamics and very high frequency dynamics. And under some conditions, manifold models may be good. I would say when you have oscillatory flow, or when you have flutter, or when you have few frequencies, then you can expect that the data lies on manifold, and this type of model gives you essentially a kind of an optimal auto encoder. And under experimental conditions, you can apply something like our feature-based manifold model. And if you want to fully automate your modeling procedure, you may want to consider clustering. Clustering is really so brute force data oriented. You cannot do anything wrong, and you will learn a lot. And at the end, you can always build a reduced order model, a subspace model based on your clustering. And with this, I want to conclude my lecture.
So questions? Yeah, I have like 100 more or less. But
I like the response. Everybody raising the question.
Maybe I will ask you mine at the coffee break.
Yes, in the examples you gave, your number of modes was always 2. What happens when you have 20 or 100? I mean, how do you do K-clustering then, and how do you interpret K-clustering then?
Very nice question. You would always like to interpret your clusters, but there's no guarantee that you can. So what you are effectively doing with a clustering, you are looking at something like short-term averaged or something like ensemble averaged coherent structures in a certain neighborhood.
Well, I mean, it's time and things that may be happening in different places in the flow field. I mean, assume that you are trying to see thunderstorms in the Midwest.
Yes.
There's one here, there's one there, that happen at different
But
places.
good point. So what you do with the clustering, you assume that you cannot afford to have sparse data. You have to be full data. So if you need to have one centroid for the cluster for the thunderstorm here, and one centroid for a cluster at another location. So if you have anything which is distributed, you suddenly need a lot of centroids. And you have the same problem also with a POD. If you have just a moving vortex, you may need of the order of 100 POD modes just to describe a single moving vortex, and clustering comes with the same disadvantage. So here you would rather like to use some Lagrangian structures or something.
Just worried because you said that this cannot fail, and I can see cases in which
of course,
it can fail.
It can fail. And what you are typically assuming, you're assuming that you have something like an ergodic situation, in the sense you have your data, and somehow your data points are visited again after some period of time. When I looked already originally at the data, for instance, of Wolfgang Schröder or LES data. So initially, in the proximity map, the data looked a bit like a worm. So you go from here to here to here to here. So now you cannot identify any model, any dynamical model, because after a half circle, you may go in this direction, you may go back, you may decide to stop. So everything is now left to your fantasy. So what you need to have, you need to have essentially enough data so that you can go back or to your original data. So the data points need to be something like recurrence points.
But that's not ergodic. Ergodic means that you go through all the points in the phase space. You're dense. Your
yes,
trajectory. You're saying
you're
dense. Speaking about the cycle.
You're reasonably dense in your state space, and you can't be too dense, because then you are losing on your prediction again.
But then you're thinking of something like a cycle, which is a single structure.
Well, it works for the turbulent boundary layers. So for all the turbulent boundary layers which we have, we can. After sufficient amount of data, we can build something like the cluster-based reduced order models, and they have this ergodic property.
I mean,
of the transitions between the coherent structures, between the centroids. So
but there are many. I mean, in that picture that you had there, you had a thousand structures. Yes.
You're referring to that one. Very nice. Well, so what we see, so we average over a significant portion of the domain. So it's something like I think over one streak length and the whole spanwise length and one boundary layer thing. A lot of things. So what we are effectively seeing, we see the flow response to the traveling wave. So we do not see the rip vortices and sweeps and
okay, so you're thinking of the wave.
Yes. But in principle, you can add 100 centroids, and then you can see more structures.
But then you cannot see it. I mean, you cannot see 100 things. I cannot see 100 things.
No, but you can process it.
Yes, but I cannot. I mean, what's the point of doing a K cluster then, if I'm going to be lost in these 100 clusters, these 100 centroids?
Well, number one, for instance, you can see what are the high drag states, what are the low drag states, what is the dynamics going from, how do you go to these high drag states. So essentially you can identify precursors to undesirable events. So there are some events where you have significant drag increase, and you can pinpoint them to a few centroids. And you can see, and you can look at your dynamics, and you see you are entering these undesirable events from this set of.
You're still thinking of a low-dimensional space in which you can see things.
Not necessarily. No, where you can compute things.
How?
Well, let's assume one thing. Let's assume there's one. Let's assume you have one state which is very undesirable, very high drag. Let's assume this. And let's say this state is called is a cluster number 1. So what you can do, you can go back. You can say, how do you go to cluster number 1? You will go over cluster number, let's say 2, 3, 4, 5, 6. So now essentially you have created the trajectories. You have coarse-grained your trajectories to your undesirable event. And now you can ask yourself, what do I need to do so that I do not go on this trajectory? So this is where your human experience comes in.
My human experience will not help in a high-dimensional space. I know that. I mean, more than 3, I just cannot see things.
No, but you don't need to see things.
Well, then how do you interpret them?
But it's very easy. For instance, if you are
for example, in this
if you are interested about drag, you look at the drag of every centroid, and you sort them correspondingly.
But, I mean, it's never going to be as easy as that. There will be a high drag region here and a low drag.
Yes. And then you can average, and then you can distill the events. You can do something like conditional sampling, and
because
so
they're
on.
going to be jumping around.
For instance, you can do conditional sampling in a very beautiful way. But you always need some auxiliary models on top.
The chairman getting there.
Okay.
We can continue here. We stay here. You can go. Yeah, there is another one, and then probably we go and we continue. We queue for the questions.
Very beautiful, and this is the purpose. Essentially, what you can now do, you can look at the transition times through your clusters. You can look at the cost function of the clusters. If you have a cluster, the advantage is you can average over all the snapshots in the clusters, and you get the corresponding coherent structure. So you filter out the noise. So the centroid is essentially a noise filter over your neighborhood. And my view on the cluster-based model is they do a nice job of pre-processing your data, and from there on, everything is based what you actually want with your data. For instance, you may decide to make your POD model in certain regions. So this has been done by Gunzburger. So you decide you want to have some representation of the high drag dynamics, some representation of the low drag dynamics, or maybe you want to figure out where are your quasi attractors. So essentially a group of centroids in which you quickly rotate and where it takes a long time to move out. So this is the social dynamics for which there also exist a beautiful analytics. So now on top of the cluster-based models, you can do many analyses, and these many analyses become very easy after your discretization, because you just need to count your fingers on your hand and the corresponding variables, and without it, it would be next to undoable.
Okay, so there's one last, and then those that want to stay, and the other can go.
My question is about the dynamic part.
Okay.
You mentioned the probability, and I got it, but you mentioned the average time going from one cluster to the other.
Very good, very good. So you caught me already that I was talking about two different models. So there's one model where we essentially have a stroboscopic view, where we say every delta t, we determine the transition probability. Now, the problem with this ansatz is it's a bit too diffusive in time. It's very good for the statistical averages, but it's a bit diffusive in time. If you want to, for instance, model the autocorrelation function more accurately, then it's then we resolve. Then we don't have the stroboscopic view, but we look at the trajectories. And then we characterize, we go from trajectory 1 to 2 in this period of time. So we have a much more accurate representation, and we can also have a linear interpolation between centroid 1 and centroid 2, and then we go from 2 to 3 and so on. And now we go one step further. We say, okay, why do we go from centroid to centroid? We can start anywhere, and now we just use the centroids for local interpolation. And now we go one step further. We say, okay, we do local interpolation between the different centroids. Why don't we add our actuation, our control laws? So there are different control laws with different parameters. You can consider them as being different dynamics and different flaws. And now if you change, you have another actuation parameter, we move between the centroids, between two operating conditions. So now this becomes a very, essentially, a versatile tool for also including your being able to interpolate your actuation. So we did it for the turbulent boundary layer, and it has very much surprised us. So At the end, what you are saying, you try to be as true to your data as possible. It's not as brute force as k nearest neighbors, where you just look at the nearest neighbors. Essentially, you coarse grain things in bin. But from there on, you do the interpolation between your centroids, coarse graining the snapshots in the corresponding bin. And I would argue if you have 10 centroids, your resolution, if you allow yourself to interpolate between the centroids, your resolution is not much worse than if you take 10 PUD modes. But you have one advantage: you will always stay close to your data. You can never go to infinity. Could also be considered a disadvantage, but for model robustness, this is an advantage.
Okay, so I propose we have a 15-minute break and we start again at 4. Is it okay? Thank you. Thanks again to Professor Noah.
Number one, your lecture was fantastic.
Okay.
Number two, I have so many questions that I don't know if I do them now or because there are things that on which I'm skeptical, to be honest.
Yes.
So basically, we are saying that the dynamical system perspective is removed. So we have only
La stanza non è ancora disponibile quello di videoconference.
Che vuol dire non è ancora?
The room videoconference is still not available.
Cioè non esiste.
Quindi c'è il building K, il building J.
Andiamo al K. Ma quindi come facciamo a collegare col computer?
Metto il mio forse. Ma non ho capito che è 100% necessario. Possiamo, perché al USB non è.
Cosa è necessario?
I'm Sadat Gazet from VKI.
Nice to meet you.
Nice to meet you too. After your presentation, may I have your 5 minutes about
Yeah.
PhD position?
Yeah,
for
we can
ABM?
talk.
Okay, thank you.
Bye, see you later. Che cazzo si chiama?
No, ma perché USB non è necessario che tutti i commenti installano. Cioè,
No.
anche con Skype, cioè, non devono.
Non devono essere là. Ma non viene quindi Turanio?
Non lo so, cioè, non mi ha risposto.
Vabbè,
bene.
non fa niente.
Cioè, dice, non ho capito, ho scritto fammi sapere per le tue preferenze, non mi ha risposto. Forse scrivo un nuovo mail e chiedo
No,
se
non
voleva.
c'è.
No.
Basta. Non è che deve venire per forza.
Non ho capito bene.
Vabbè, poi parliamo dopo.
Vabbè, sì. Vabbè, ma rispondo a Lucina, dice uno di quelli di K va bene.
Mhm.
E poi forse scrivo pure ad Alessio a chiedere se è 100% necessario con Skype. Se è,
Mhm.
cerchiamo di organizzare con il mio computer, non so.
Ma quanti siamo presenti?
De Gre, Contino, tu, Alessio, quindi siamo già 4
Mhm.
da 6.
Va bene.
Quindi Alberto Turani, Alberto non viene. E poi Turani forse no.
Ok, va bene.
Quindi secondo me va bene.
Yeah, for sure. I think everyone is going to share all the lecture. Hello. Hello, 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 hello. Hello. Yeah, I think it's too far. But if I put it as it should be, it's far. Okay. Yeah, that's okay. Yeah. Yeah. Good.
Okay, so welcome back to the last lecture of the day, which is going to be dedicated to reduced order modeling for very complicated situations, reacting flows, and it's going to be given by Professor Parente.
Thank you, Miguel, and thank you for this opportunity as well. So before I start, I would like to thank to acknowledge the co-authors on this paper, on this presentation. Many students from my group, as Ben was mentioning before, this wouldn't be possible for any of us without very good students. So what I want to do before is I would like to know how many people have worked or work in combustion? Okay. Not zero. This is good. So what I will try to show today is some techniques that we have been using for reduced order modeling in combustion. I will explain why. I hope that you see ways that these techniques can be useful to you, and so I would be interested, in the end, to see this kind of feedback from your side. But I am interested in applying these approaches to problems that I've seen this week. So to start, we have discussed about the place that machine learning is taking in our work and in our approaches today. And you're probably familiar with this sketch of the scientific method. We go through a reality, the definition of conceptual model and computer models. And what I really think is the key for using machine learning in the future and to make the best use of machine learning in the future is that of bringing it inside the scientific method circle, which means coupling machine learning with computer models, embodying in machine learning tools all the a priori information that we have about problem physics, and improve these machine learning tools based on the feedback that we have from validation experiments. But the other very important question that we have to ask is what are we after? And I think this is a very critical point, and it was pointed out by Professor Brunton in the morning. So we have to define the questions that we want to answer. And based on these questions and our intended use, our objective, we will define the approaches that we have to use. It was mentioned that machine learning is not neural networks. It's true that most of the time you will be better off with approaches that are different than neural networks. Okay, so this is something that it's really important, and I wanted to point it out. Also, you're probably familiar with this quote from the statistician George Box. So all models are wrong, but some are useful. Professor Jimenez, that I don't see here, also taught us on Monday that the data will tell us if the models are wrong. But I would add something to this sentence. I would say that the data will tell you if the models are wrong, given the intended use of the model that you have in your, the objective that you have for your model. And this is very important because there isn't a best model. There is a model that is useful for your application. And I think that this is really interesting to see the use of machine learning and data in building the generation of models. I think a way that we should see the development of this model is in hybrid models which couple physics-based information with the exploitation of data in several different ways. And we have seen that there are many important, very, very interesting algorithms to do so. And this is really important to go towards very complex problems. That could be multi-physics, multi-scale simulations, or digital twins for control and sensing closures. This is a big problem in many applications. Okay, so let's move on. This doesn't work. Okay, so why is data-driven modeling interesting for combustion? So for the people who are interested in combustion and no combustion, maybe this is trivial, but I would like to motivate why this is interesting. So combustion is intrinsically multi-scale and multi-physics. You know that it combines heat transfer, chemical kinetics, fluid dynamics. Moreover, if you look at chemical kinetics, this scales 12 decades of scales, which can be more or less coupled with the fluid dynamic ones. So you see that you have a very complex process, because if you have to take both of them into account, then it becomes very complex to do so. We have a curse of dimensionality in the sense that we have very large dimensionality of the state space. Chemical kinetics for standard fuels involve hundreds of species and thousands of chemical reactions that are tightly coupled in kinetic mechanisms. And then you have, on top of the nonlinearity of turbulence, you have nonlinear turbulence chemistry interactions, and the evolution of the state space is highly nonlinear because mainly of the Arrhenius kinetics. Okay, so you see that you have a number of challenges that make the use of machine learning, data-driven modeling, reduced order modeling very appealing for these applications. So to show you a little bit what this multi-scale, multi-physics challenge is, you see here the 12 decades that chemistry can span, and here are the fluid dynamic ones. And so based on the overlap or not of the two processes, you might have combustion process which are slow chemistry, finite rate chemistry, or fast chemistry. And we denote them by using a number which is called Dunn-Keuler number. And so if the Dunn-Keuler number is very very large, it means that your chemistry is not the limiting process, it's a very fast chemistry. If it's very small, you are in a slow chemistry kind of regime. Otherwise, you are in a finite rate regime. So guess most of the time in which regime we are. In the finite rate, and so it means that we don't have any chance. We have to take both of them into account. Okay, so because of course, if you were here or there, it would be easy. We can decouple the two phenomena, but we can't because we are in the middle. Okay, and then this was the second issue. It's the dimensionality. So you see it very clearly here. You see that the number of species in a kinetics mechanism increases very strongly with the number of carbon atoms, and unfortunately, the CPU time also increases with the number of species, but with the power of 2.5. So you see that this makes the whole problem really challenging. Okay. Now, in combustion, there has been an increasing interest in the use of data-driven approaches. I made this search very recently, and if you make that at a 10 years span, you see that there is a very strong increase in the use in the papers that actually report either machine learning, feature extraction, data mining, and combustion. So this actually shows that there is a momentum in using this, and this is clearly motivated by the 3 reasons that I showed before. Okay, so what is the 2 things that I will talk about, and what are, in general, the things that are interesting in our community. There is a lot of data interpretation and feature extraction. I will talk a lot about that. And this is important because we want to identify low-dimensional manifolds in turbulent reacting system, meaning we want to find a compression, optimal compression for our state space to reduce the number of variables that we have to account for. And then the second one is that we want to reveal key features of new combustion modes that are interesting, for instance, because they are less polluting, but they are very, very complex. And so the use of high fidelity simulation and data mining approach can help us in this respect. And then, of course, we want to predict stuff. And so we want to develop new closures. We want to replace or couple a data-driven approach with the physics-based one. Or we want to develop reduced order models for uncertainty quantification, optimization, like digital twins. And so I will talk about digital twins in the end of my presentation. Okay, so many tools for feature extraction. Some of them, many of them have been mentioned in this during this week. So PCA or POD, nonlinear principal component analysis, isometric mapping. Do you know anyone has used IsoMap? Do you know what it is? Okay, TSNE. Autoencoders, yeah, I think many of you. Okay, and I will talk in particular about a technique that we have developed, contributed to develop. It's called local POD or PCA, and it has actually, it shares some similarities with the clustering approach that Professor Noack was mentioning before. Okay, so I don't want to go, I will not have equations, but I just want to say how we assemble our matrices if you will be using our codes. So we have a state space that consists of temperature, pressure, compositions, okay? So we assemble the data in this way. We have each row is an observation, and then each column would be a different state variable. And then I can skip this very easily. You have had all the introduction to PCA. Then we call, you will see that I mention some things that are called principal component scores. These are the projection onto the eigenvector matrix. We have a scaling matrix because our data are scaled, and I will come to that in a moment, since we have different units and different scales in chemical species. And we also center our data, as was pointed out before in the presentation of Professor Noack, okay? And so you have a centering matrix, scaling matrix, and eigenvector matrix. And so we have, we talk about principal component, truncated principal component scores, and a low rank approximation of our initial matrix X of data. Something else I want to point out, why we center just as was mentioned before, because we have to convert observation to fluctuations. And we also scale because in our problems we have temperature, we have stable species of combustion, we have radical species. So they span scales which are very different. And so to take all of them into account, we have to scale appropriately the metrics. And so I don't have time to go into the details of that, but this is a tutorial that we have written with Einspeech at Aachen. And so if you are interested, you can look it up. And something else that we do, it was mentioned today, again, I will not go into the details of that in this presentation, but we also pre-process data. We use principal component classifiers as approximation of the Mahalanobis distance to see from the empirical distribution of the data, what are the outliers in the data. And so this is very important when you have experimental data. And so we have in our field a lot of experimental data coming from the Sandia National Labs or many other labs in the world. And so it's really, really important to detect both the univariate and multivariate outliers that you might have in a data set. Okay. This is just for you. This will be uploaded afterwards. So if you are interested, you can go and look at all these references if you are interested in looking at those. But so, as I was mentioning before, PCA and other approaches have been applied to a large number of experimental and numerical data sets. Numerical data sets are increasing every day. So you have DNS data that are generated maybe as we talk. And here you see some of the references that I have collected, but basically this is this kind of this is not a problem anymore. It's probably the opposite. We have a booming of data, and so we will have an increasing availability of data in the future. But you see, you have simple flames. This is a simple jet flame. This is a piloted flame. This is a lifted off flame, and this is a diluted flame. And then you have different configurations. Flame vortex interactions, premixed flames, and so all sorts of things that you can imagine. Now, when you do PCA, of course, you do this eigenvalue decomposition. You find the principal components that will explain a certain amount of variance that you want in your data, and then you get this best multilinear approximation of your data. So it's multilinear because you have different linear contributions. And of course, I mean, you have this approximation, but you know that most of the time, especially in combustion, your data present non-linear features and non-linear interactions. So the fact that you're using a multilinear approach might be problematic because you might actually find additional dimensions just to make up for the non-linearity of the manifold. Okay? And so this is important because this explains why people in combustion have looked into other approaches of to perform PCA. And so one of them, for instance, is kernel PCA. And so the idea is very simple. You perform a PCA in a feature space where the relationships are linear. So very similar to what was mentioned for POD. The problem is that the computation of this kernel can be very expensive and can become unmanageable for large data sets. So this has been used, but on very small data sets, and not DNS-like data sets, because of this problem of dimension. And you see here it was applied on a one-dimensional turbulence approach. So it's the equivalent of the linear eddy model. Anyone familiar with that? It's a one-dimensional turbulence simulation where the three-dimensional mapping is built using a statistical approach. Okay? And then you see ISOMAP, isometric mapping. Anyone has used it? So this is also another approach which is very similar to kernel PCA, but here the difference is that the kernel is the geodesic distance between the points. And so this is very interesting because you know that Euclidean distances may not be the correct metric in high-dimensional spaces. And so the idea here is that you keep the distance between points the same in the original and in low-dimensional manifold. And you see here an application from the group of Jackie Chen at Sandia. You see here a DNS of DME combustion. You see here an interpolation in space, and then on the left and on the right side, a 2D, a three-dimensional LDM application. The other problem here is that you have to build a graph to find the shortest path between 2 points. And so this path search can be very, very expensive. And so this is also why this approach is limited in use for data sets which are very, very large, like in combustion. Other approaches which are similar to that, it's the TSNE, so it's the T-distributed stochastic neighbor embedding. So it's very similar to the ISOMAP, but it's a probabilistic version of that. So you have points which are close to each other, and you want to be sure by minimizing the likelihood that the probability that two close points are close in the original space, they will be also close in the final space. Okay. Now you see that this has very nice features because here you are looking at 13 different premixed flames, and you see that the approach is able to set them apart one by one. So it has very nice feature of putting these feature of the different features of the database apart. The problem, like in many neural network approaches, I think, I mean, this is at least my point of view, is that you have many hyperparameters to tune to get these results. And sometimes it can be very messy, and you don't know why, and then you have to do trial and error and so on. And then autoencoders. Autoencoders have been presented today, so we have applied also them on combustion data. You also know that if you have a very shallow with the linear activation functions, you have nothing but the principal component analysis, or PRD. But here the idea was to compare these autoencoders to locally linear PCA approach. Okay, and so we applied that to a DNS jet. So you see here the original temperature field. This consists of 12 state space variables. The grid points are about 2.5 million per time step. And you see here the autoencoder reconstruction. You just see the reconstruction of the relative error with 4 layers. So it's not a shallow network, 2 components only. So from 12 to 2. So you see that it's pretty okay. You have some regions where you have some error, but still it appears to be quite reasonable. Okay. Now, why don't we look at approaches that are based on PCA? So what we have seen here is that the limitations of PCA have prompted let's say the development of approaches which are based on nonlinear search into let's say nonlinear data set to parameterize these nonlinear manifolds with fewer dimensions.
The problem with these approaches is that they can become computationally intractable, and this is the point. This is, for instance, the case for kernel PCA or isometric mapping, or they can involve a large number of hyperparameters. And this is, I think, personally the case of both approaches like TSNE and autoencoders. And the other observation that I also make is that when you use these nonlinear approaches, you get features that are very difficult to interpret. If you try to interpret autoencoders' codes, then you have to use correlation analysis. You have to see which are the variables in the state space which are mostly correlated to the codes. So it becomes quite difficult to get a clear understanding of what is going on. So this actually prompted us to look into linear formulations of PCA. So imagine you have this nonlinear manifold. You have a multidimensional point. So what you can actually do is to imagine to do a piecewise linear PCA reconstruction by minimizing what? The reconstruction error of each point to the one of the four directions in this case. And of course, this can be generalized to any number of clusters and or to prescribe a predefined reconstruction error. And the idea is that you get, in the end, an optimal decomposition of your system into different regions, a little bit like was presented by Bernd before. Yeah, maybe it's very similar, but what we, I'm not sure that in that approach we can actually prescribe, because what we do is that, you will see in a moment, we perform iterative algorithms that minimize a cost function that we define. Okay? And so we can define the cost function to suit our purposes in other means. Okay? So now imagine that you have this original field from the DNS. In this case, we are not looking at temperature now. We are looking at the OH radical. Okay? And you see that it's here you have the fuel region, on the sides you have the air, and then you have a very thin layer of OH. Now, if you try to apply global PCA to get this field, you need at least 5 eigenvalues, and you still get, a decent approximation, but it's not perfect. While with the local PCA, a certain number of clusters and 2 eigenvalues, you get a perfect reconstruction. This is actually more visible when you look at the parity plots. So you see here that you still have an error which is above 14%. Now, when you compare these two autoencoders, it's also remarkable that you are able to get with local PCA results that are better than what you would get with the same dimensionality of an autoencoder. Now, I want to be very clear here. I'm not saying that, so autoencoders, neural networks are universal function approximator. So it means that there should be a setting of the autoencoder that will give results which are better than local PCA. But the number of hyperparameters that you have to train and to optimize to get this result become very large. And so at a certain point, it's not even interesting to do so. This is at least what we have observed in our work. So you see here the reconstruction error for the different variables. This is the DNS flame of reference. And so you see the results obtained with the different approaches, PCA, local PCA, and the the different autoencoders. And you see here this very clearly. You see the global PCA results. These are all relative error on temperature. You see very clearly how these performances of local PCA are improved, and also on the reconstruction of a very small radical species. So a radical species is in combustion a species that wants to react because it has an unpaired valence. And so it's not stable, it will react to form either another radical or a final product, okay? So you see here that also these minor species get really, really well with this approach. Now, of course, someone could say, but in your approach, you also have hyperparameters, right? Do you think that I have in local PCA hyperparameters to tune? Yeah, but I have only 2 of them. I have the number of clusters and the number of principal components. And the metric, okay? But the metric is the reconstruction error, okay? Okay, now, before we move forward, I have to introduce a variable, because otherwise, nothing that I say will be clear. So I have to introduce a variable that is very important in combustion. It's called mixture fraction. And this is the ratio of the mass of mixture leaving in the fuel side compared to the mass of mixture in a control volume. Basically, the mixture fraction will tell you how much fuel you have locally inside your domain. So it's a measure of the stoichiometry of the system. Why this is a so important variable in combustion? You see it here. When I plot temperature as a function of the mixture fraction, I have this kind of behavior. You see that you have a maximum. This is where I have a stoichiometric condition, more or less. But something which is remarkable is that most of the nonlinearity in the data is captured by this variable. Okay? So you see that you have this nonlinear behavior, and this nonlinear behavior is mostly captured by mixture fraction. Of course, you have a simpler data set where almost temperature is only one function of mixture fraction, but then you have very complex ones when the mixture fraction alone cannot explain everything in your system. You see that here you have a scatter. In this condition here, I can have points which are ignited, non-ignited, and so on. And it means that I still have most of the nonlinearity in the mixture fraction, but I also need other variables to explain my process. Okay, so this mixture fraction will be used in the following as a variable that best parameterizes combustion systems. Okay, now this is important because I want to talk a little bit about the two algorithms that you could use for doing this local PCA in combustion data. And of course, you might think also at applications in your cases. One of them is that I do this completely unsupervised. And I have to use, let's say, an approach or a metric to define how iteratively I converge to a certain cluster separation. Okay, so what we do is that we initialize centroids randomly or uniformly in mixture fraction space or from k-means. This is our initialization. And then we partition into the clusters, and we build this reconstruction error. So we are looking at, for a given dimensionality or number of eigenvectors, we see what is the error between the original data and the projected one. And then we iterate to minimize this distance. So what will happen is that the data will be assigned to clusters that minimize the reconstruction error. So you will have an optimal reconstruction of your data into clusters. Of course, you could say, okay, you know that mixture fraction is a good variable. Why don't you cluster on mixture fraction? We said before, this mixture fraction has most of the nonlinearity in the data. One possible option is to say, okay, I split into bins on mixture fraction. This is my ideal clustering. Problem is that this is not always ideal. As you saw before, for data like this, you don't know if working into these bins of mixture fraction is optimal or not. So to give you an example, looking at the same data set I had before, if you do a mixture fraction partitioning, so a supervised partitioning of this data, what you get is simply that I'm splitting the data into the rich side, so the air side, and the fuel side. But if I ask VQPCA to extract or find two clusters, you see that it's very clever because it will extract the reacting layer from the non-reacting one. So it's really getting an important feature of my flame. But then this was my presentation before I saw Professor Jimenez's talk on Monday, and he was saying, are you really sure that you are getting a good feature? How can you say that you're getting a good feature? So this is, then I went back home and I called all my PhD students, and then we sat together. And basically, we decided to make a test to see if on manifolds that we know, we could prove that we were extracting the good features, okay? And so we did that. We took two manifolds which are famous in combustion. One is the Burke-Schumann. and one is the equilibrium manifold. Why they are interesting? Because in this manifold, we know exactly the state space. I mean, we know what the state space is function of. We know that these are both state spaces which are only function of the mixer fraction. And so you see that, for instance, for the Burke-Schumann, this is a case of a very high uncolored number, one global reaction, first law analysis, so no equilibrium involved. And so you see that you have piecewise linear relationship for the temperature and also for the species. In the equilibrium manifold, we use the first and second law analysis, and we minimize the Gibbs free energy of formation. And this is how we get it. And so these are the two manifolds that we get. You see that in one case, it's a piecewise linear function of Z. In this case, it's more complicated because it also involves dissociation reactions and so on. Now, if VQPCA is really a good feature extraction method, what do you expect when you apply it to this manifold? What do you think? What should I expect? That it picks what as... Yeah, so what would you expect if you apply this vector quantization approach on this manifold? First of all, do you expect that it finds more than two clusters? Yes or no? It shouldn't. If it was a good clustering method, it wouldn't find more than two. And should it find more than one important variable? I think the answer is no, right? It should only find one important variable. And so let's see if this is true. So when we apply this to this manifold, no matter, so let's say you initialize with 100 cluster, in the end, your VQ partitioning approach will give you only two clusters. It will say cluster 99 is empty, remove it. Cluster 81 is empty, remove it. And then you will end up with just two of them, and regardless of the number that you put in the initialization, okay? And the other thing which is interesting is that if you start putting noise in the data, and this actually found it remarkable, it actually clusters the noise. It doesn't cluster as splitting, in this region. It starts clustering the noise so that when you look at the correlation between the first principal component and the mixer fraction, you get an R square which goes to 1. So it means that the first principal component explains 99% of the variance, and it's the mixer fraction. Yeah.
Could you explain how you compute the distances in the previous case? Maybe I missed this part.
Yeah. Let's go back. I compute the projection. So the error, the difference between the original data and its low-dimensional projection. Okay? Okay, so what would happen if you apply a supervised conditioning? So if I just do FPCA and I say I want 4 clusters, then I have to split here, 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 and here. And of course, the more you split, the more you lose correlation with the mixer fraction. And this, I think it's a sign that this is not a very good partitioning or supervised partitioning approach. I mean, unless you know that you have to choose at most 2 clusters. Because of course, if you choose 2 clusters, you have a 100% R square. But of course, if you start adding clusters, then you get, you lose correlation between the mixer fraction and your principal component. Yes? So we create a million realization using the equations. We know the equations. Temperature, CO2, H2O, N2, O2, CH4.
And you don't have Z, the mixer fraction?
No, we don't. It finds it. So that's
Okay.
cool that it finds it.
No, I didn't get it. So this makes a very big difference.
Yeah. Okay, what about the equilibrium manifold? We get the similar result. So you see the same with more or less noise, just to see what happens on the data. And you see that you have the same conclusion that it identifies that the only variable which is important in the manifold is the mixer fraction. So it correctly finds what we knew, of course, before. But this is actually good because we know that when we apply to another system that we don't know, we will find a good feature. Okay, so I want to also point out one point briefly. So I mentioned before that I see this locally linear reconstruction to be superior to autoencoders for the simple reason that you have less hyperparameters to train, and you can get interpretation of the features. Because of course, once you have a cluster, you can go into cluster, you have the eigenvectors and eigenvalues, so you know what the features are. And so we wanted to see, on the other end, if the autoencoder and the local PCA were finding similar structures. But this is difficult because you have understood that our local PCA, you have clusters, and so you have a local coordinate system in each cluster. And so to do so, we used an approach which is called procrustes analysis. Anyone knows about it? Okay, so this is a comparison of shapes under translation, scaling, and rotation. So it means that you might have two features which are very, very similar, but they are translated, rotated, and scaled. And so if you apply translation, rotation, or reflection, and scaling, you end up understanding that they are not so different after all. Okay? So this is the principle of procrustes analysis. And so when we do that, it's kind of interesting that we find out that in fact the local PCA reconstruction tends to be an autoencoder reconstruction as the number of cluster tends to infinity. Infinity 128 here. Okay? So this is actually interesting because it means that we kind of find the same nonlinear code that autoencoder finds, but with a locally linear approach. Okay, so to conclude this part, we have a broad range of methods for size reduction and feature extraction. Nonlinear methods, of course, outperform PCA in terms of accuracy for a given number of dimensions, but I personally think they're very difficult to interpret and they cannot be directly translated into predictive models. What I like of local PCA and locally linear models that were presented before is that they combine size compression and interpretability. Of course, they also have problems of being translated directly into models because then you have different regions that have to talk to each other. And as Bernd was mentioning, maybe the challenge of the future will be to know how these talk with each other, to develop really predictive models based on those. But still, they can be used. I think you see that they can be still used very efficiently for classification approaches, which is one of the machine learning, one of the two things that machine learning have to do. And I also think that in machine learning, there is still need to further develop and automate the approaches for the analysis of massive data set, which is not yet the case. Okay, now that, is there any question up to now? Because I will change subject in a moment. Okay. Now, you have seen that we have found, we can find, yes, sorry. You have a
So the beauty of your approach, having first the clustering and then the PCA, is that you can also tune the dimension. So you may know that in certain dimensions, the dynamics is simple. You need 2 dimensions here, maybe 10 dimensions there. This is something you could never do with locally linear embedding. But the unnice thing is that you have the same problem as in discontinuous Gajokin methods. I mean, if you consider your thing as an autoencoder, then on the boundary, so let's say the Voronoi cells, you have discontinuities.
You're right.
And the discontinuities would be, you don't have discontinuities in locally linear embedding. But of course, you can have other interpolations which remove the discontinuities, but this require an additional step. So there's an advantage of your approach, but also a challenge if you consider this as an autoencoder.
You're right, and in fact, we have looked into that into one dimensions, in ways we can actually enforce continuity at the boundaries. But as you move to more dimensions, it becomes more complicated, of course. But this is exactly the trade-off that you mentioned is exactly what we have also observed. Now we have identified these principal components, and now we can claim, and we can actually wonder whether we can use these principal components to formulate models. Okay, now. As I mentioned in the beginning, that in these combustion systems you have hundreds of species, but of course you might imagine that there is some degree of correlation between them, right? I mean, at least you would hope, because otherwise it's a big problem. Huh? And so, indeed, we know that these reacting scalars are correlated in state space, and so what we want to explore is whether we can use PCA to find the best progress variable or reaction variables that describe the system in a low-dimensional manifold. Okay, so this brought us to formulate a model that we call PC transport. PC transport approach back in 2009 with my colleague James Sutherland. At the moment, I didn't know I was doing machine learning, but now they told me afterwards that I was doing that. So the idea is that you start with a transport equation for the scalars. The difference with a passive scalar is that you have a source term, and here this will make a big difference, you will see. And then you do this projection onto the principal components, and you get a fewer number of transport equations for your principal components that are a mapping from your original state to the reduced state. Okay, now you have fewer equations, but you have a few problems as well. First of all, you have this transport term. I will not talk about that today, but you have to do something to express the transport terms in the principal component space. So there are ways to do that. You have to do some assumptions as well. But the biggest problem is the source term. And why this is a big problem? Because of course we know that the source term depends linearly on the source terms of each of the species in the original data. So in principle, you might be able to reconstruct this source term using recomputing all the state space, then using Arrhenius equation to compute the source term of each species, and then computing the source term of the principal component. The problem is that the mapping between a state space and the source term is nonlinear. Okay? And so as you do a small error here, this is magnified in the nonlinear mapping of the Arrhenius equation. And so this is a real problem. It's a real problem because it reduces the number of components that you can retain. So it means that you have to use more components to make up for this nonlinear error propagation. So there is a way out, of course, and it would be to use a machine learning approach or a regression approach, which is the second task of machine learning, is regression, as we learned in the morning, to directly relate the principal components to their source term. And so there are different approaches that have been used by different groups. So Stephen Pope, Jackie Chen have been using multi-adaptive regression splines for doing that. Other people in North Carolina have been using artificial neural networks. Of course, we had to do something different, and so we used Gaussian process regression. We like, joking apart, we like a Gaussian process that is a semi-parametric regression approach, and also as a measure of uncertainty associated to it. Okay, so we have used that, and we have applied it to different problems of different complexity. So we have started from very, very simple reactor. So a 0D reactor is a well-mixed reactor where only chemistry is involved. And now you see here on the left the evolution of a few radicals, OH, and you see that, in fact, if you don't use this regression for the source term, out of the 12 original variables, you need quite a few variables. You need 7 to get good approximation of these scalars because of the nonlinearity of the manifold. And so it means that you are paying for this nonlinear error propagation. but when you go to this regression, you see that you can go from 12 to 2 without loss of accuracy. Then we expanded this to very complex mechanisms, still in 0D reactors. So the original mechanism here was 162 species, and you can do everything with 2 components, although you have to formulate your regression locally. Otherwise, you have to add more components. And then this is, of course, interesting, but it's still a toy problem because you are not interested in running 0D reactors. You are interested in running real simulations, okay? And so what we then came up with is this framework when we have to simulate some very complex multidimensional flame, and then we have to generate a model based on the transport of principal components. And so to have data to generate our models on, we use very simple reactors. So this is a month of CPU time. This is seconds of CPU time. And of course, this makes sense at this point because the part of generating data is very cheap compared to the function evaluation. But then, of course, there is a problem. No, not a problem. There is a you have to be careful that the data that you use to generate the data to generate this reduced model must be representative of what you will explore or visit in the state space of the real simulation. Okay, so I give you an example to see how this works. So these are important cheap valuations. These are very expensive function evaluations. So I want to show you 2 examples. The first one is the first question that you have when you see this approach is, can I use simple reactors to model complex or more complex configurations? To answer this question, we first performed this study that was published in 2016. So what we did was basically to take a laminar flame, reduce our model on a laminar flame, and we applied it on 7 turbulent flames. Okay? So now, of course, this is a quite challenging problem because we didn't even use multiple laminar flames. We just used 1 laminar flame. And we wanted to explore the possibility of reconstructing flames in turbulent conditions. So this is, by the way, called a Borghi diagram. This is a diagram that describes the regime in which a premixed turbulent combustion takes place. So what is interesting is that we were able to do so, and you see here some snapshots of the simulation. So for point 1, 2, 3, 4. Point 1 is, of course, very close to the laminar one. So you see that the flame front is unperturbed. And then as you move in this direction, you have flames which is that are more broken, and here you have flames which are more elongated. Okay. So what is interesting here, and this is one of the movies for this condition, I think. Yeah. So you see the formation of these big structures. What is interesting here was that to compare the results, we were looking at conditional PDFs of a scalar. In this case, we took 1 chemical species, which is representative of the reaction process. And we could see, you should look at the results of the SCORE PCA approach, that this conditional PDF was matching very, very well the DNS PDF. So showing that, in fact, we were able, with this reduced order modeling approach, to capture exactly the state space observation with the DNS. And then something else I would like to point out is an LES simulation that we recently performed. This is also a very famous, so for the people working in combustion, this comes with no surprise. This is a flame which is usually used for benchmark. It's called flame D. It's a piloted flame. So you see here the flame which is established. All these small flames here are piloted flames for igniting the flame. Okay, and then you have air on the sides. Why this is often used? Because flame D, it's very easy. So everyone wants to show that his model can work or her model can work on flame D because usually it works. The real complexity is to get flame F, because flame F is a flame which is almost extinguished. And so a flame which is close to full extinction is very complex to capture. So what we did was to train data, and this is something that should be important to retain. We use the transient laminar counter-diffusion flames, and we performed a steady simulation by perturbing with the sinusoidal input the flow velocity, and we collected a number of observations for generating this model. And when we use this model to perform 3D simulations with OpenFOAM, what is important to note here, beside the other settings, is that we transport only two variables, so the two principal components. Of course, we transport momentum, but in the state space, we transport two variables, and we get all the other ones from the PCA approach. Okay, so something I wanted to point out again is that when we look at the principal components, again, we find this idea that they they pick the features of the flame. And so you see that, for instance, mixer fraction F is very correlated to the first principal component, while the second principal component is somehow related to the progress of the reaction, which is indicated by the CO2 in the fluid. Okay, so this is what we solve for, and this is what we get, just part of it. Of course, we get all the state space, all the 50 chemical species in the mechanism. And of course, we can compare. Everything works very well for flame D, which is a sanity check, if you want. But this is also working quite well for flame F. As I told you, this is a very complex flame that to model. Okay, I think more interesting than this is this picture. I think this picture tells a lot about why this model works and how what you have to do to make it work. Yeah.
Dimension of your.
Sorry.
Can you remind us of your dimension of your reduced order model?
So it's a we transport two.
Only two features, so two-dimensional.
Two transport equations. Yeah.
Wow.
So this is actually interesting because it shows very well why and what you have to do to make it work. So when we train our manifold, I said we were performing transient simulation with unsteady counter-diffusion flames. By doing so, we were able to cover the full state space that could be visited during the numerical simulations. And then when you see the real simulation, the actual simulation that we perform, you see that, of course, when you run on flame D, I told you this is a flame which is easier to model. You see that you have most of the branches which are on this ignited side, and you see that for flame F, you really visit most of the initial space. But if your initial space was not containing this part, your model would have failed. It's clear. So you have to be sure that your model, that your training manifold contains the data. And this is related to the comment of Bernd. It's very easy to interpolate. It's not easy, but it's easier to interpolate than extrapolate. Okay. So what is nice of this approach, and we like it a lot, is that we get for a system the most important progress variable without expert judgment. We don't need an expert saying, oh, take the mixer fraction, take this progress variable. PCA does this for us. And we also couple this approach with nonlinear regression. And of course, using nonlinear regression removes some generality of the approach, but allows to get very good size reduction in a way. Okay, so, and also we see that this approach is also very good in predicting complex systems. So is there any question on this part? Yeah.
The yes, I repeat.
So
the diffusivity in the transport equation of the two components.
Yeah, so when we did this simulation, we took Lewis number equal to 1, but in principle, you can treat that. So if you assume Fickian diffusion, you can project the transport term on the eigenvectors, okay? And you get a transport term in the principal component space. The difficulty, of course, is that you have to also generate your training data with non-unity Lewis number definition. But I mean, this is possible, what I mean. Okay, but if you want, I can show you the details after. But in this case, we just consider turbulent diffusion. That's for the simulation that I showed you. Okay, so I want to go back a little bit to the classification problem that we had before, and I want to show how this could be useful in a predictive simulation. So I told you that local PCA can give you an autoencoder representation of the system, and this is one thing. But it can also give you the, let's say, what are the most important regions in the flame, and how they are, let's say, locally homogeneous in a way. And so why this is very interesting, I think it's because by doing so, you can say, okay, if I have an optimal subdivision of my domain, and now you can also think if this can apply to your problem. You have a flow and you want to clusterize it somehow. You can say, oh, this is interesting because I see that I have a cluster which is probably related to the flame region where I will need all the species in my mechanism, okay? But maybe in this region here, which is just on the oxidizer side, I don't need all of them. I just need oxygen and nitrogen. And so I can reduce significantly the size of my problem. Okay, so this is interesting and explains an approach that we have developed with the Politecnico di Milano, and it's called SPARC, Sample Partitioning Adaptive Reduced Chemistry. So the idea is the following: in all this machine learning approach, you need data, right? So we need data to train our approaches. So we have some data, and I showed you that you can reasonably use 0D reactors as long as you select them appropriately. Of course, if you have available other two-dimensional co-flow simulations or also even DNS, you can use them. And then what you do is that you perform some classification. We have used our VQPCA, but we also benchmarked VQPCA with SOM, self-organizing maps, SOM coupled with k-means. There is a paper which is being published now if you are interested. And then what we do is that we have these optimally clustered regions, and then in these regions we do some mechanism reduction. So this can be done with different ways. Could be done with the approach that has been developed by my colleagues in Roma, computational singular perturbation, or with the graph kind of approach with the graph search. But the idea is that you have a collection of regions, and in this region you have a collection of chemical mechanisms, and these mechanisms have different sizes, optimally tailored to the different regions. This is the beauty of that. And you see an application of these on a temporally evolving syngas jet. So you see here the clustering, and you see here the temperature contour, the H2 contour. If you look these at the final final time step, you see that we are able to capture features that are present in different state variables with this kind of clustering. Okay, now just want to show you how this applies to a real simulation. So you see here we applied SPARC to an unsteady co-flow methane flames. You see here on the left a detailed simulation, on the right an adaptive one. You don't see, I think, any difference between the two. And this let's say, good comparison or matching between the two stays in time, and it doesn't blow up in time. And you see here the error that we make. It's very, very low. Here I'm reporting this as a function of the threshold error that we use in reducing the chemical mechanism. But what you see is that this is very well behaved for the major species. And the speed up is also interesting. I should point out that we're using here a mechanism that only includes 80 species, 80, and so we have a speed up of 50. But when you go to very large mechanism, you can have speed up of about 20, 25. And this is what I'm showing here in the next slide. So we have noticed, and this is something I really didn't know, but we also found a proof in the theorem. When you have very large dimensional data, computing distances is very difficult. And so we realized that our classifier based on VQPCA was actually not optimal. It was still performing, but it was not optimal when you go in very large dimensional data set. And so what we did was to do a two-step. We were using a VQPCA for the training of the classification, and then on-the-fly simulation we are doing now with deep neural networks, because they are better in finding the match between the region and the new point. And so when we do that, I show you here for a normal-heptane simulation. So this is a quite complicated one. It's a very large mechanism, and here I'm looking at a very small species, the O radical. So it's a very, very small species that we are getting with great accuracy. And you see that here the speed up, I want to point out, can be very, very large. We are in the order of 15, 16. So we are saving a lot of computational time because we're using this optimal classification of the system, and we apply an optimal approach in every cluster. Okay. If you are interested, we will share a code for this classification, so you can use it. It's already on a GitHub repository. It's quite easy to use. I don't know if I have time to show how to use it, but I prefer to finish, and then maybe if there is a couple of minutes, I show it. Okay, so I want to touch with the last part of my talk. It's about the development of digital twins. So what are these digital twins? So imagine you have an experiment and simulation. What you would like to have is a digital twin that can be used to troubleshoot, optimize, even optimize the design or make a new design of a system. And so to build this digital twin, of course, you need to have both experiments and simulation. You have to do feature extraction. And then you have a model that can be used for real-time evaluation of a complex system state. So what is the definition? Because if you look online, there are thousands definitions of a digital twin. So this is our definition of a digital twin. It's an integrated multi-physics, multi-scale simulation that uses the best available models, the sensors information that you might have, the input data to mirror and predict a physical twin. Okay. And so the objective that we were pursuing in developing this was to combine CFD simulation with real-time sensor data to get prediction of unexplored states of a system. In this case, of a furnace because we have this furnace in our lab, and so I will show this in a second. Okay, a little bit about the approach that we use. If you are interested, this is in this publication. So what we do is basically to do a model decomposition, and then we take the eigenmodes and the coefficients, and we say, look, the eigenflames, we call eigenflames, are physics-related information. We don't touch them. So this is our physics-based information. For us, this is invariant. And then we have the coefficients, and then we model the relationship between the coefficients and the input parameters. So imagine you are changing your flow velocity, you are changing your fuel composition, you are changing your temperatures, okay? So this variation we model with a machine learning tool. And again, we use GPR. We could use ANN, we use GPR. And then we combine the two, and we get what we call the reduced order physics-based model. So you see, I think this is very clear. So you have, imagine you have temperature, so you have 3 eigenflames, you have 3 coefficients. The coefficients are a function of x. X are your input parameters, okay? Now, something that I wanted to point out is that when we do PCA, we constrain some physical properties. We constrain, so we have mass fractions. We know that mass fractions should sum up to 1, and they should be positive, right? So this is something that we constrain inside PCA. So we constrain positivity and conservation of mass, because otherwise you have problems in predictions, of course, okay? And then I want to show you very briefly an application on our furnace. We have this furnace at ULB. So it's a fairly large furnace. It's very close to a furnace that you would have in an industrial plant. We have a lot of experimental access. So the idea was to have a validation furnace, something that you don't have in industrial application because the quality and quantity of data is very limited. Something scale bridging between the lab scale and the industrial scale. And so what we wanted was to have this digital twin, as I was mentioning before. So what we did was to perform CFD simulation. The CFD simulation were validated with experimental data for 8, 9, or 10, infinity experimental conditions that we double checked in our system, and you see here just one of them. And then we performed this design of experiments, and so you see this design of experiments depicted here. This is our design space. We want a digital twin that can work in a range of H2 mass fraction in the fuel from 0 to 100%. The rest is methane, so we are looking at fuels, methane, hydrogen. We want an air injector, or we want to change the air velocity within these bounds. We want to change the equivalence ratio, so the stoichiometry within these bounds. And then you have the different simulations, and what you are seeing here, so these balls or spheres, this is the importance of this simulation in the modes of the system. Okay, so this is the importance of, if you want, of this simulation. So not all simulations are equally important to define the reduced order model, in other words. And so here we did standard stuff that is done in this kind of reduced order modeling. So we did this leave k out reconstruction error matrix, which basically means I have my simulations. I start to remove 1, 2, 3, 4, 5 from the reduced order model, and then I predict a state which is not in the original database, of course, a new state, an unobserved state, and I see how the error goes. And so you see that you have errors for the reconstruction which are very, very low. When you look at the predictions, of course you have errors which are larger, but you are, let's say, in the 10%, more than 10% range. So here I'm looking at the error to reconstruct all the variables, all the spatial fields inside the system. So this is quite challenging as a reconstruction, because this is something which is, of course, demanding. From a point of view, you have a system which is 35-dimensional in chemical space, and you are using a reduced order model, a real time, and you get error, but it's a contained reconstruction error. Another feature that you see is that, of course, the error increases, but the variance decreases as you increase the leave k out simulations. Because, of course, here you are maybe removing simulations which are very important, so you have a big scatter. And then as you move out, you have a lesser scatter, of course. But then the question is, if I have a digital twin, what is that I'm really interested in? Maybe I'm not really interested. Okay, I'm interested in looking at in an augmented reality kind of a way. I want to look inside, and maybe it's cool and so on. But what I'm really interested in, and if you talk to industrial people, what they are really interested in is to have to use these kind of things to predict stuff that they cannot measure, or to double check things that they measure. Okay, so for instance, in such a digital twin, you would be interested to say, okay, what is the max temperature? Where it is located? Maybe you don't have exactly the thermocouple where you have the max temperature. What are the wall temperatures? What is the flue gas composition? This is something you can double check. So this is something you could use to even improve your digital twin. Or things that you cannot measure, so soft sensing. What is the OH peak? So the OH measures the reaction region. What is the flame length? Flame length can be visually measured, but it's not. There is no probe that can measure the flame length. Okay, and so when we look at these things, the figures are much more interesting, because you get errors that are below 10% for most of the variables. So you see, you have error on wall temperatures, OH predictions, flame length, which are very, very low, but you have still an error of about 10% for the prediction of the actual value of a chemical species peak. But I would argue that this is still a reasonable value to have. 10% for an industrial application is good. Okay, and this is if you want to use the model to predict the full states. You see you have the original state and then its counterpart, the digital twin. You see, of course, some differences, but overall, I think you get what is happening in the system. Okay, so I'm finishing here. So I think that we have we can actually rely on data-driven approaches to do a number of things. in flows in general, and in turbulent flows, turbulent reacting flows, we can of course increase our knowledge, develop predictive model, reduce the cost, and even develop these digital twins that can help optimize existing processes and develop new ones. I would like to also point out very briefly what is going on now in the literature. There is a lot of work going on the closure in turbulent combustion. And so we are working on the closure of sub-Briggs quantities in LES. So for to solve the unresolved flame wrinkling, to model filter progress variable scalars and source terms for transport terms. And you see here a very nice picture from the work of Thierry Poinceau and co-workers on the flame wrinkling using deep convolutional neural networks. Also something which I find really, really interesting. It's the use of physics-informed adversarial, generative adversarial networks. This is a simulation that the group of Einspeech performed, and basically the turbulent closure here was based on this generative network, which look very powerful. So with that, I finish, and I thank you for your attention.
I had a question previous. I couldn't get in there fast enough. For the Sandia D flame, I just wanted to clarify. It's a turbulent flame, no?
Sorry?
It's a turbulent flame. Turbulent.
Yes.
Yeah.
It's turbulent.
And your simulation was an LES.
Yes.
So how do you capture the turbulent chemistry interaction in using this?
So we did two things. We tried with no model. And we also tried with the presumed PDF approach.
Okay. But then you have to solve two more equations, no?
Yeah.
Okay. All right. Thanks.
But these results are with no model. The results that I show. So we have both. In the paper that we submitted, we have both. The point is that our LES is very well resolved. Okay. But it's okay. What I mean is that the results here are with only the two transported variables, Z1 and Z2, but we also did with the variance of mixed fraction, and so we have an additional dimension in the table, basically.
Yeah.
Okay.
Yeah. So I would expect you would need 4 variables to solve this problem.
Indeed.
Yeah.
So let me congratulate you. You have shown us the future of reduced order modeling, and you have removed a main stumbling block of reduced order model. So your way of first clustering the states and then finding a model is something which you would probably need to do in most complex system, and you have sacrificed analytical simplicity for essentially smoothness. This is one comment.
Okay.
And another thing is, we talked about locally linear embedding. Maybe you have to use your approach, because what can happen is you may have a smooth, say, diffuse curve, something like that. So with a locally linear embedding, you would go through the curve and identify something one-dimensional. With your approach, you may identify something two-dimensional. So between 2 points, you may need the third direction where you have a small diffusion.
Yeah.
So the question now, of course, is, have you found another realization of locally linear embedding, or do you actually need to go to this, say, additional complexity and additional degree of freedom in order to solve your problem? I think both could be possible.
Yeah, I think, first of all, I would like to say that I would like to try local linear embedding because I didn't try before, and then probably I will be able to answer that, yeah. But it's true that I think you really pointed out the advantages and disadvantages of both of them. So we have this problem of continuity at boundaries. This is a big problem. And so, but for the application that we have in these reduced kinetic models, this doesn't matter, because it's just a classification problem then. Yes, yes. So I answer first to the second one. So I didn't show it, but people from my group, Dr. Bellemans, Aurélie, she has used this approach for, and she's using this approach for plasma-assisted combustion. Yeah, PC transport approach. So for plasma-assisted combustion, also in combination with physics-based model like DRG. So this is possible, it works. Now coming to your question, when you look at the manifold of flame F, I would say that I'm pretty sure this is not two-dimensional. But the reason why with two-dimension it works is that I'm using the regression, do the work of making it two-dimensional. So I'm putting all the non-linearity in the regression. That's what I'm doing. So I need a regression model which is good enough. That can handle this nonlinear complexity.
Maybe I have also a question concerning your last result, which is really impressive. You have 45 simulations, which I will not say it's a lot, but I can imagine that these are extremely expensive. So how expensive is one simulation?
So these are runs. These are not LES.
Okay.
So this is still expensive because it's a full chemistry model. So for this piece is it doesn't run in 8 hours for sure, but let's say a couple of days on a computer, on a supercomputer.
Okay. And you have excellent predictive capability thanks to the Gaussian regression problems. So how far do you think this could go? How many steps do you think you can predict in the future with this approach?
So what we are trying to do now is that at the moment we don't have an approach. So imagine you use this in a real furnace. You measure your temperature at the wall, your exhaust, and you see that there is a mismatch because you also have a prediction from the digital twin. And so what we want to do now is to implement some life learning rules that can shift or re-optimize the modes so that the model continues to improve as you use it in the real system. So this is one thing we want to do. And the other thing is that we have to see how the number of simulation scales when you increase dimensions. Maybe you want to use another fuel, 3 components. You want to add another geometric parameter. So it can become complex, but I think it's promising.
Other questions? Well, then thanks again to Professor Parente.
Thank you.